Hello and welcome back. I'm glad you're here. Maybe you had a long day. Maybe your mind is still turning over the small anxieties and unfinished tasks that didn't quite resolve before you decided it was time to rest. That's okay. You don't need to solve anything right now. Tonight we're going to take a journey together. Not away from those thoughts exactly, but past them, into something larger and quieter. Tonight we're exploring our solar system, not as a collection of facts to memorize for a test, but as a neighborhood we happen to live in. A small corner of space where the sun's light reaches, where worlds spin in the darkness, where ice and rock and gas have arranged themselves into patterns that took billions of years to settle. Before we begin, if you find these videos helpful, if they give you something to rest your attention on while sleep finds you, consider subscribing. It helps me continue making these, and it costs you nothing but a moment, but no pressure. Whether you subscribe or not, you're welcome here. Now let's begin. There's something quietly profound about knowing that everything around you shares a birthday. The ground beneath your feet, the moon hanging in the night sky, the distant planets you've only seen in photographs, all of it came from the same moment, the same cloud of material drifting through space. 4.6 billion years ago, in a region of the Milky Way galaxy not so different from where we are now, there was a cloud, a vast cold cloud of hydrogen and helium, mixed with heavier elements forged inside stars that had already lived and died. This cloud was just there, drifting, waiting. And then something disturbed it. Maybe a nearby star exploded in a supernova, sending shockwaves through space. Maybe the cloud simply reached a critical density where its own gravity could no longer be resisted. Whatever the cause, the cloud began to collapse. Slowly at first, then faster. As it collapsed, it began to spin. Conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. The center grew hot and dense, compressing until nuclear fusion ignited and the sun was born. The rest of the material spread out into a flat, rotating disk. A protoplanetary disk, we call it now. In that disk, dust grains stuck together. Pebbles became boulders. Boulders became mountains. Mountains became worlds. And here we are, 4.6 billion years later, resting on one of those worlds, looking up at the others. Everything you've ever touched, every atom in your body, every grain of sand on every beach, all of it shares this ancient origin. In a sense, the solar system isn't just where you live, it's your extended family, your very distant cousins, all born from the same cosmic cloud, all spinning together through the darkness. When we think about the solar system, we often picture the planets as equals, sharing space with the sun. But that's not quite right. The sun doesn't just dominate the solar system. It is the solar system almost entirely. If you could somehow gather up every planet, every moon, every asteroid, every speck of dust, every comet drifting through the outer darkness, and put it all on one side of a cosmic scale, it would barely register against the sun on the other side, 99.86%. That means everything else, Jupiter with its immense storms, Saturn with its vast rings, Earth with its oceans and mountains and forests, all of it together makes up just 14/100%. It's almost a rounding error, a footnote in the sun's mass budget. This tells us something important about how planetary systems form and what they really are. They're not a collection of equals orbiting in harmony. They're the leftovers, the scraps that didn't fall into the star, the material that escaped being consumed during the sun's formation. We live on the debris, in a sense, the remnants of a meal the sun couldn't quite finish. And yet, here on this tiny remainder, in this statistical footnote, life arose. Consciousness emerged. Beings capable of looking up at the sun and understanding, even approximately, what it is, and how it formed, and why it shines. There's something humbling about that, but also something quietly miraculous. The universe doesn't need to put most of its mass into interesting places for interesting things to happen. Sometimes the scraps are enough. Right now, as you listen to this, you're seeing the sun as it was 8 minutes and 20 seconds ago. Not as it is now, in this present moment, but as it was when that light began its journey across space. If the sun suddenly vanished, just winked out of existence, you wouldn't know for 8 minutes and 20 seconds. The sky would remain bright, birds would continue singing. The warmth on your skin wouldn't fade immediately. For those 8 minutes, Earth would carry on as if nothing had changed, living in the past, unaware that the future had already shifted. This delay feels strange to us because we're used to light arriving essentially instantly. You flip a switch, and the room illuminates. There's no noticeable gap between cause and effect. But space is so vast that even light, the fastest thing in the universe, traveling at 209,792 kilometers per second, takes time to cross it. 8 minutes and 20 seconds is the light travel time for the roughly 150 million kilometers between Earth and the Sun. This also means that when you look at the night sky, you're looking backward in time. The light from Mars left its surface minutes ago. The light from Jupiter took somewhere between 30 and 50 minutes to reach you, depending on where both planets are in their orbits. And the light from distant stars? Some of it has been traveling for years, decades, centuries. The star might not even exist anymore, might have exhausted its fuel and collapsed, but its light continues carrying the message. I was here. I once shone. In a sense, we're all living slightly in the past whenever we look at anything. Even the person sitting across from you, light bounces off them and takes a few nanoseconds to reach your eyes. It's an imperceptibly small delay, but it's there. We never see the present moment, only its echo arriving just after it's already gone. For 76 years, from 1930, when Clyde Tombaugh discovered Pluto, until 2006, when the International Astronomical Union reclassified it, our solar system had 9 planets. An entire generation grew up learning this as fact, memorizing the order with mnemonics. My very educated mother just served us 9 pizzas. And then in 2006, astronomers gathering in Prague voted. Pluto was out. The number dropped to 8. Pizzas were no longer served. It wasn't that Pluto had changed. The little world kept orbiting the sun exactly as it always had, cold and distant and unconcerned with human classification systems. What changed was our understanding. As we discovered more objects in the outer solar system, bodies like Eris, which is actually more massive than Pluto, we faced a choice. Either we had dozens of planets, perhaps hundreds as our telescopes improved, or we needed a stricter definition of what planet meant. The new definition included 3 criteria. A planet must orbit the sun, must be massive enough for its gravity to pull it into a roughly spherical shape. and must have cleared the neighborhood around its orbit, swept up or scattered the smaller debris. Pluto failed the third test. Its orbit crosses Neptune's path, and it shares the Kuiper Belt with thousands of other icy objects. So Pluto became a dwarf planet, a category that acknowledges its spherical shape while recognizing it hasn't dominated its orbital zone. Some people felt betrayed by this change, as if something beloved had been taken away. But here's the thing, our words don't change the universe. Pluto is still there, still fascinating, still worth studying. Whether we call it a planet or a dwarf planet doesn't alter what it is. A distant, complex world with mountains made of water ice and plains of frozen nitrogen. The universe doesn't care what we call things. Only we do. And sometimes, when we learn more, we adjust our language to fit what we've learned. Imagine standing above the solar system, looking down on it from the north, watching the planets spin. Most of them turn counterclockwise, the same direction they orbit the sun. This makes sense. They all formed from the same rotating disk of material, so they inherited that original spin direction. But Venus? Venus turns the other way. If you could stand on Venus's surface, which you can't, not without being crushed and incinerated, and watch the sun rise, it would rise in the west and set in the east, the opposite of Earth, the opposite of almost everywhere else. Venus is doing its own thing, turning against the grain, spinning backward through the solar system like a rebel who never got the memo about which way to rotate. Why? The most likely explanation is violence. At some point in Venus's early history, perhaps during the chaotic period when planets were still migrating and collisions were common, something massive hit Venus. Not a glancing blow, but a catastrophic impact, possibly from a planet-sized object. The collision was so violent that it knocked Venus's rotation askew, flipping it around entirely. Or perhaps there were multiple large impacts, each adding to the effect, until Venus's spin reversed. There's something almost melancholy about this. Venus, Earth's sister planet, similar in size and composition, might have been on a very different path. But a collision, or a series of them, changed everything. Its rotation reversed, its atmosphere thickened, its surface became a hellscape, and now it spins slowly backward, taking 243 Earth days to complete one rotation. Alone in its retrograde motion, a reminder that violence can reshape worlds in ways that last for billions of years. This is one of those facts that feels like it shouldn't be possible, like discovering a staircase that goes up and down at the same time, a day longer than a year. How can that be? Let's slow down and think about what day and year actually mean. A year is the time it takes a planet to complete one orbit around the sun. For Venus, that's 225 Earth days. A day, meanwhile, is the time it takes a planet to complete one full rotation on its axis, one spin. For Venus, that's 243 Earth days. So Venus orbits the sun faster than it rotates. It completes a lap around the sun before it finishes turning around once. This creates some strange effects. If you were somehow able to stand on Venus's surface, again, you'd be dead almost instantly, but let's pretend. You'd see the sun rise in the west, move slowly across the sky for months, and finally set in the east. Then you'd wait through months of darkness before seeing it rise again. A single day-night cycle would last 117 Earth days. You could watch the sun rise, celebrate a birthday, grow older, and still be waiting for sunset. This sluggish rotation is partly due to Venus's thick atmosphere, which creates drag, and partly due to that ancient collision we mentioned. Whatever knocked Venus backward also slowed it down dramatically. Now it turns so slowly that its orbit wins the race. A year passes. The planet has circled the sun, but the same face hasn't yet returned to point at the sun. The day isn't over. It's disorienting to think about. Our experience of time is so tied to Earth's rhythms, 24-hour days, 365-day years. But on Venus, time flows differently. A day outlasts a year. The universe doesn't care about our expectations. It arranges itself however physics dictates, and sometimes the result is something wonderfully strange. Sometimes you hear a number like this, and it just slides past. Another statistic about planetary size. But stop and sit with it for a moment. 1,300 Earths. Not 13, not 130. 1,300. Imagine trying to fill Jupiter with Earth-sized marbles. You'd need to manufacture 1,300 exact copies of our entire planet just to fill the space. Jupiter's volume is so immense that it challenges comprehension. And yet, despite this enormous size, Jupiter isn't particularly dense. It's made mostly of hydrogen and helium, the same light gases that make up the sun. If you could somehow compress Jupiter, squeezing out all that empty space between atoms, it would shrink dramatically. But as it is, it's a vast, puffy ball of gas with just a small, possibly rocky core buried deep inside. Here's another strange fact about Jupiter. Despite being so enormous, it rotates incredibly fast. A day on Jupiter, one complete rotation, takes only about 10 hours. 10 hours! This rapid spin stretches Jupiter, flattening it slightly at the poles and bulging at the equator. If you could measure Jupiter from pole to pole versus across its equator, you'd find it's noticeably wider than it is tall. The planet is spinning so fast that it's deformed itself. And because of this rapid rotation, Jupiter has the strongest magnetic field of any planet in the solar system. That magnetic field creates radiation belts so intense they'd kill a human in hours. The planet is beautiful from a distance, those swirling bands of color, that iconic great red spot, but up close, it's hostile. A churning, crushing, radiation-soaked giant that could swallow more than 1,000 Earths without noticing. In the cosmic sense, Jupiter is a monument to scale, a reminder that the universe builds on sizes our minds struggle to hold. When you see Saturn in images, those elegant, impossibly flat rings circling the planet, it's easy to imagine them as solid structures, but they're not. They're particles. Billions and billions of individual pieces of ice, each one orbiting Saturn independently, creating the illusion of solidity through sheer numbers. The particles vary wildly in size. Some are as small as grains of sand, glittering specks catching sunlight. Others are pebbles, rocks, boulders, and some are genuinely enormous, chunks of ice the size of houses, even mountains, tumbling through space in their own miniature orbits. All of them are water ice, mostly pure but with traces of rocky material mixed in, giving the rings their subtle color variations. And despite spanning 280,000 kilometers, a distance that could almost bridge the gap between Earth and the Moon, the rings are astonishingly thin. In most places, they're only about 10 meters thick. 10 meters. Imagine a disk stretching from Los Angeles to New York, but only as thick as a 3-story building. That's the scale we're talking about. If you could shrink Saturn and its rings down so the rings were the thickness of a sheet of paper. Saturn would be smaller than a marble. This thinness is strange and beautiful. It tells us the rings are young, cosmically speaking, and fragile. They won't last forever. Particles collide, lose energy, and spiral inward toward Saturn. The rings are slowly raining onto the planet, falling as a steady drizzle of ice and dust. In perhaps 100 million years, Saturn's rings might be gone entirely, and the solar system will lose one of its most iconic features. For now, though, we're lucky. We live in an era when Saturn wears its rings, when something delicate and temporary happens to exist, shimmering in the sunlight, beautiful because it won't last. Mars, the cold, desert world we've been sending robots to for decades, holds a record. It has the tallest known volcano in the entire solar system, Olympus Mons, a shield volcano so enormous that it defies easy comparison. At about 21 kilometers high, it's roughly 3 times the height of Mount Everest. If you stood at its base and looked up, you couldn't see the summit. It would be beyond the horizon, hidden by the curvature of the planet itself. The base of Olympus Mons is equally staggering. It's about the size of Arizona, around 600 kilometers across. This volcano covers an area larger than entire states, larger than many countries, and it didn't form quickly. Olympus Mons grew over millions of years, possibly hundreds of millions, as lava flowed from a single hotspot deep beneath Mars's surface. Unlike Earth, where plate tectonics move continents and redistribute volcanic activity, Mars's crust is largely static. A volcano can sit above the same magma source for eons, building higher and higher, layer upon layer, until it becomes a mountain that dwarfs anything on Earth. The slopes of Olympus Mons are surprisingly gentle. It's a shield volcano, not a steep cone, so climbing it wouldn't feel like scaling a mountain. It would feel like walking up a very, very long hill. The incline is only about 5 degrees in most places. You could probably hike it without even realizing you were ascending something so massive, at least not until you looked back and saw how far the horizon had fallen away below you. Olympus Mons is almost certainly extinct now. Mars's volcanic era seems to be over, or at least on pause. The magma that once fed this giant has cooled and solidified, but the mountain remains, a monument to Mars's more active past, a time when the planet was geologically alive, when lava flowed and built mountains that touched the edge of space. Now it's quiet, a vast, sleeping giant on a cold, dusty world, waiting for no one. Mercury is a world of extremes. It's the closest planet to the sun, so you might imagine it's uniformly scorching. And during the day, you'd be right. Temperatures on the sunlit side reach 430 degrees Celsius, hot enough to melt lead, hot enough to vaporize any water instantly. The surface bakes under unfiltered sunlight, with no atmosphere to soften the sun's intensity. But then the sun sets, and without an atmosphere to trap and redistribute heat, Mercury's surface cools catastrophically fast. Temperatures plummet to 180 degrees Celsius on the night side. That's a temperature swing of over 600 degrees, the largest of any planet in the solar system. Nowhere else does the thermometer swing so violently between day and night. Why? Because Mercury essentially has no atmosphere. There's a tenuous exosphere, a wispy collection of atoms temporarily kicked up from the surface by solar wind and micrometeorite impacts. But nothing you could breathe, nothing that could hold heat or create weather. Without an atmosphere, There's no blanket to keep warmth from radiating back into space. The moment the sun's light stops hitting a patch of ground, that ground begins losing heat directly to the void. And space is cold, very cold. So Mercury's surface temperature crashes. This means Mercury exists in a state of constant, dramatic flux. The same rock that was hot enough to glow during the day becomes colder than any night on Earth. If you could somehow stand on Mercury's surface during sunrise, you'd watch the temperature climb hundreds of degrees in minutes. The ground beneath your feet would go from freezing to melting hot as the sun crept above the horizon. It's a harsh, unforgiving place, a world without the moderating influence of air, without the cushion that makes Earth's climate survivable. Just rock and sunlight and the vast, cold emptiness of space. When you hear asteroid belt, you might picture a dense field of tumbling rocks, a navigational hazard where spacecraft must weave carefully between colliding boulders. Science fiction has given us this image, ships dodging and banking through a chaotic obstacle course. But the reality is far more spacious, far more empty. The asteroid belt does contain millions of objects, maybe billions, if you count the smallest fragments. They orbit the Sun in a broad ring between Mars and Jupiter, remnants from the solar system's formation that never coalesced into a planet. But despite these vast numbers, the belt is mostly empty space. If you were to fly a spacecraft through the asteroid belt, the odds of accidentally hitting an asteroid are vanishingly small. You'd see them perhaps as distant points of light, but they're spread across such an enormous volume that collisions are rare, even over millions of years. And here's the strange part. If you could somehow gather up all the asteroids in the belt, every single rock, pebble, and grain of dust, and compress them into a single object, that object would be smaller than our moon. The entire asteroid belt contains less mass than a single medium-sized moon. Most of that mass, roughly half, is concentrated in just 4 asteroids: Ceres, Vesta, Pallas, and Hygiea. Ceres alone, the largest, contains about a third of the belt's total mass. This tells us something important. The asteroid belt isn't a failed planet exactly. It's the remnants of a planet that never had a chance to form. Jupiter's immense gravity stirred the region, preventing the asteroids from settling down and clumping together. Every time objects began to accumulate, Jupiter's influence would speed them up, causing collisions to become destructive rather than constructive. Instead of building a world, the asteroids kept fragmenting, grinding each other down over billions of years. So what remains is a graveyard of planetary possibilities, a scattered ring of debris that marks where a world might have been, if circumstances had been different, if Jupiter had formed elsewhere, if the early solar system's chaos had played out just slightly differently. It's a reminder that not every planetary seed grows. Sometimes the garden produces empty spaces. There's something elegant about discovering a planet without seeing it first. Neptune's existence was predicted by mathematics, by noticing that Uranus wasn't behaving quite right, that its orbit wobbled in ways Newton's laws couldn't explain unless something massive and unseen was tugging on it. In the early 1840s, astronomers noticed these irregularities in Uranus's motion. Something was pulling on it, perturbing its orbit. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently worked out where this unknown planet must be. They used nothing but observations of Uranus, Newton's laws of gravity, and careful calculations. Pen and paperwork, no computers, just the logical machinery of mathematics grinding through the possibilities. Leverrier sent his predictions to Johann Galle at the Berlin Observatory. Galle pointed his telescope to the predicted location on September 23, 1846, and there it was, Neptune, almost exactly where the mathematics said it should be, a faint blue dot in the darkness, a world that had orbited unseen for all of human history until someone thought to look for it by following the equations. This discovery was profound, not just because it added a new planet to the solar system, but because it validated a way of knowing the universe. You didn't need to see something directly to know it existed. You could infer it. You could trace the effects and work backwards to the cause. Neptune's discovery proved that mathematics wasn't just a tool for describing what we observe. It could predict what we haven't yet observed. It could reveal hidden truths. And Neptune itself, it's a cold, distant world, an ice giant with winds reaching 2,000 kilometers per hour, faster than the speed of sound on Earth. It takes 165 years to orbit the Sun, so slowly that it has only completed one full orbit since its discovery. A single Neptunian year spans from 1846 to 2011. If you were born on Neptune during its discovery year, you'd only now, in 2011, be celebrating your first birthday. Time moves differently out there, in the cold and dark, where mathematics found a world that eyes alone could never see. Most planets spin like tops, their axes roughly perpendicular to the plane of their orbits. Earth tilts at about 23.5 degrees, giving us seasons but maintaining a general sense of upright rotation. Jupiter and Saturn are even more upright, their axes only slightly tilted. But Uranus lies on its side. Its axis tilts at 98 degrees, which means it essentially rolls around the Sun like a barrel, its poles taking turns pointing almost directly at the Sun. This creates the strangest seasons in the solar system. For about 42 Earth years, a quarter of Uranus's 84-year orbit, one pole faces the Sun continuously, bathed in sunlight, while the other pole experiences perpetual darkness. Then, as Uranus continues its orbit, the seasons shift. The illuminated pole gradually turns away from the Sun, and the dark pole rotates into view. Eventually, their positions reverse entirely. Summer becomes winter, winter becomes summer, and the transition takes decades. Imagine living on Uranus, hypothetically, of course, since Uranus is a gas giant with no solid surface and an atmosphere of hydrogen, helium, and methane. But imagine, you'd experience a summer that lasts 42 years, with the Sun circling the horizon endlessly, never setting. Then gradually the Sun would dip below the horizon, and autumn would arrive. Eventually, winter, 42 years of darkness, the Sun never rising, only the stars wheeling overhead. Then spring and the Sun's return, and another impossibly long summer. A single year on Uranus would encompass your entire human lifetime, and then some. What caused this bizarre tilt? The most likely explanation, again, is a collision. Early in the solar system's history, something massive, perhaps an Earth-sized protoplanet, slammed into Uranus, knocking it onto its side. The impact was so violent that Uranus never recovered its upright orientation. It just kept spinning, tilted, rolling through space in a configuration that no other planet shares. It's a reminder that violence shaped the solar system, not just metaphorically, but literally. Collisions determined which way planets spin, how fast they rotate, whether they have moons, whether their surfaces are cratered or smooth. The solar system's current calm is a recent development, cosmically speaking. For its first few 100 million years, it was chaos. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all named after deities, gods of commerce, love, war, kingship, agriculture, the sky, the sea. Ancient humans looked up at the wandering stars and saw divine figures, projected their mythologies onto the planets, and those names stuck. Even Uranus, discovered in 1781, followed the pattern, named after the Greek god of the sky. But Earth? Earth comes from Old English and Germanic roots. Eorthe in Old English, Erde in German. It simply means ground or soil, the dirt beneath your feet. There's no mythology attached, no god or goddess, just the land, the place where things grow, the foundation. This makes sense when you think about it. For most of the human history, we didn't think of Earth as a planet. It was the world, the fixed center of creation. The planets were those bright wanderers in the sky, special and strange, worthy of divine names. But Earth was just here, the default, the background against which everything else happened. It wasn't until Copernicus, and later Galileo and Kepler, convinced us that Earth was also a wandering star, also a planet, that we had to reconsider. And by then, the name was set. We weren't going to rename it. So Earth kept its humble, practical name, even as we realized it orbited the sun just like Mercury and Venus and all the others. There's something quietly grounding about this, if you'll forgive the pun. All the other planets carry the weight of mythology, of stories about gods and their dramas. But Earth is just Earth, ground, soil, the stuff you can touch, the stuff that grows food, the place where life happens. Maybe that's more honest. Maybe it's fitting that the one planet we actually know intimately, the one we walk on, breathe on, live and die on, has a name that simply means here, not some distant divine realm, just here, home. The sun isn't constant. We think of it as steady, rising and setting with predictable regularity, shining with unchanging brightness. But up close, it's dynamic, turbulent, cycling through moods that shift on an 11-year rhythm. During solar maximum, the sun's surface erupts with activity. Sunspots appear, dark patches where intense magnetic fields suppress the usual convective heat flow, making those regions slightly cooler than their surroundings. Solar flares burst out, sudden releases of magnetic energy that send radiation streaming across the solar system. Coronal mass ejections hurl billions of tons of charged particles into space. If these particles reach Earth, they can create beautiful auroras, but also disrupt satellites, interfere with communications, and occasionally knock out power grids. Then the cycle winds down. The sunspots fade, the flares diminish. The sun enters solar minimum, a quieter phase where its surface is relatively calm. But even this quiet isn't permanent. Slowly, the magnetic field rebuilds, new sunspots begin appearing, and within a few years, the sun is back to solar maximum, storming again. This 11-year cycle has been remarkably consistent. We can trace it back through centuries of direct observation. Ancient tree rings and ice cores, which record isotopes created by cosmic rays, which are modulated by solar activity, show the cycle extending back thousands of years. It's a rhythm the sun has been dancing for a very long time, perhaps for its entire life. What drives the cycle? The sun's magnetic field, generated by the motion of charged particles in its convective zone. But the details are complex, not fully understood. The Sun is a vast ball of plasma, ionized gas, rotating at different speeds at different latitudes. This differential rotation stretches and twists the magnetic field lines, creating knots and tangles that eventually burst through the surface as sunspots and flares. Over time, the field reorganizes, flips its polarity, and starts the process again. In a way, the Sun breathes. An 11-year inhale and exhale, a cycle of storm and calm, a rhythm that affects the entire solar system. And we, on Earth, notice, not just in the auroras, but in subtle changes to our atmosphere, to satellite operations, to the very top layers of our air that expand and contract with the Sun's moods. The Sun's cycle is our cycle too. We're all dancing to the same cosmic rhythm. There's a storm on Jupiter. You've probably seen pictures, a massive, swirling oval of reddish-brown clouds, larger than Earth, churning in Jupiter's southern hemisphere. It's called the Great Red Spot, and it's been there for as long as we've had telescopes good enough to see it clearly. Giovanni Cassini possibly observed it in 1665. If so, that means the Great Red Spot has been raging for over 350 years. 3.5 centuries of continuous storm, winds howling at hundreds of kilometers per hour, clouds swirling in a pattern that never quite dissipates. For comparison, the longest-lasting storm on Earth, a hurricane or typhoon, lasts maybe a few weeks. The Great Red Spot has lasted longer than the United States has existed as a country, longer than the Industrial Revolution, longer than the entire modern era of science. What sustains it? On Earth, storms die when they move overland or when they run out of warm water to fuel them. But Jupiter has no land. It's a gas giant, just atmosphere all the way down until you reach a core, if there even is a distinct core. There's nothing to slow the Great Red Spot down. No friction except with other atmospheric currents. And Jupiter's atmosphere is incredibly deep and energetic, with heat flowing up from the planet's interior. The Great Red Spot sits between two jet streams that flow in opposite directions, and this setup helps keep it stable, like a ball bearing caught between two conveyor belts moving in opposite directions. But the storm is changing. It's shrinking. When it was first measured accurately in the late 1800s, the Great Red Spot was large enough to fit 3 Earths inside. Now it's smaller, only about 1 Earth across. It's been shrinking steadily for over a century. No one knows exactly why or whether it will continue shrinking until it disappears entirely, or whether it will stabilize at some smaller size. In a few decades, maybe in your lifetime, the Great Red Spot might fade away. A storm that has raged for centuries, maybe longer, might finally dissipate, and Jupiter will look different. A familiar feature, a landmark we've used to identify Jupiter since the telescope was invented, will be gone. The universe doesn't preserve things just because they're iconic. Even storms that last for centuries eventually end. Pluto, the little world at the edge of the solar system, the one we demoted from planet status, has a family. 5 moons orbit it: Charon, Styx, Nix, Kerberos, and Hydra. And the largest of these, Charon, is so big relative to Pluto that their relationship is unlike any other planet-moon pair in the solar system. Charon is about half the diameter of Pluto and contains about 1/8 of Pluto's mass. That might not sound like much, but it's enormous for a moon. Our moon, by comparison, is only about 1/4 Earth's diameter and contains barely more than 1% of Earth's mass. Charon is proportionally much larger, much more massive, much more significant. This size ratio means that when Pluto and Charon orbit each other, they don't orbit around a point inside Pluto. Instead, they orbit around a point in the space between them, a barycenter that lies outside Pluto's physical body. Imagine two dancers holding hands and spinning around. If one dancer is much larger, they barely move, and the smaller dancer swings around them. But if both dancers are similar in size, they both move significantly, spinning around a point between them. That's Pluto and Charon. They're dancing together, neither one clearly the leader. This makes them more like a binary system than a planet and its moon. They're locked in a tidal embrace, each keeping the same face pointed toward the other forever. If you stood on Pluto's surface on the side facing Charon, Charon would hang in the sky, never rising or setting, always in the same spot, growing slightly larger and smaller as their elliptical orbit brought them closer and farther apart. And from Charon, Pluto would do the same, a constant companion, fixed in the sky, never moving. There's something touching about this. Two worlds, small and cold and distant, locked together, orbiting each other in the darkness at the edge of the solar system. They're so far from the sun that sunlight there is barely brighter than a full moon on Earth, but they have each other, forever spinning, forever together, a binary system at the frozen frontier of our cosmic neighborhood. This fact always surprises people. The moon looks close, hanging there in the night sky, close enough that you can see its craters and Maria with the naked eye. And in cosmic terms, it is close, only about 4,400 kilometers away on average. But space is deceptive. Distances that seem small are often larger than we intuit. If you lined up all the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, side by side, they would span roughly 380,000 kilometers. That's just barely less than the distance from Earth to the Moon. All 8 planets, including Jupiter with its immense bulk, would fit in that gap with a little room to spare. This tells us something about how much emptiness exists in space, even in relatively close distances. The moon isn't pressed up against us. There's a vast gulf between Earth and its nearest neighbor, a gulf so wide you could pack every planet in the solar system into it. And yet, from our perspective, the moon looks close. It's right there, a constant companion, rising and setting, waxing and waning. This discrepancy between perception and reality is common in astronomy. Things that look close are often unimaginably far. Things that look small are often incomprehensibly large. Our brains evolved to understand the scale of forests and plains, of horizons you can walk to in a few days. We're not equipped to intuitively grasp the scale of space, so we have to use math, use comparisons, use strange facts like this one to calibrate our sense of distance. And once you realize this, once you understand how much space exists between Earth and the moon, you start to appreciate just how much emptiness there is everywhere else. The gap between Earth and Mars? Vastly larger. The gap between Earth and Jupiter? Immense. And the gap between stars? Unimaginable. Space is mostly space, emptiness, void. And the things that exist, the planets, the stars, the galaxies, are rare, precious islands in an ocean of nothing. Mars has been called the red planet for as long as humans have noticed it in the night sky. Ancient civilizations associated its color with blood, with war, with violence. The Romans named it after their god of war, and the color is real, Mars genuinely looks red, not just from Earth, but up close, from orbit, from the surface itself. The sky is pinkish. The ground is rust-colored. Everything is shades of red and orange and brown. Why? Because Mars is rusting. Its soil contains large amounts of iron oxide, the same compound that forms when iron is exposed to oxygen and water here on Earth. Rust. The planet's surface is covered in it, ground to dust by billions of years of wind and meteorite impacts. This fine, rusty dust gets kicked up into the atmosphere, tinting the sky, settling on every surface, giving Mars its distinctive color. But here's the interesting part. Iron oxide requires oxygen and water to form. Mars's current atmosphere is mostly carbon dioxide, with very little oxygen. And liquid water can't exist on the surface today. The atmosphere is too thin, the pressure too low. So the rust on Mars is old. It formed billions of years ago, when Mars had a thicker atmosphere, when liquid water flowed across its surface, when rivers carved valleys and lakes filled craters. That ancient water, reacting with iron in the Martian soil, created the rust we see today. In a sense, Mars's color is a memory, a chemical memory of a wetter, warmer past. The rust is a scar, evidence of a lost era when Mars might have been more Earth-like, when conditions might have been suitable for life. That possibility, life on Mars, has tantalized humans for over a century. We've sent landers and rovers searching for signs of ancient microbial life, for fossils, for organic molecules, for anything that would tell us we're not alone. So far, we haven't found life, but we've found the conditions that could have supported it. And every time we look at Mars, every time we see that red color, we're seeing evidence of water and chemistry and processes that, on Earth, are intimately connected with life. The rust is a clue, a hint, a question mark, written across an entire planet, waiting for an answer. The sun looks bright and ethereal, a glowing ball of light in the sky. But its core, the region where nuclear fusion occurs, where hydrogen atoms slam together to form helium and release the energy that powers the star, is almost incomprehensibly dense. At the core, the sun's density reaches about 150,000 kilograms per cubic meter. That's roughly 150 times the density of water. To put that in perspective, imagine taking a volume of material the size of a pinhead, maybe a cubic millimeter, and scooping it out of the sun's core. If you could somehow bring that pinhead-sized sample to Earth and place it on a scale, it would weigh over a ton. A single pinhead of material. Over a ton. This extreme density is necessary for fusion. Hydrogen nuclei, protons, naturally repel each other because they're both positively charged. To overcome that repulsion and get them close enough to fuse, you need immense pressure and temperature. The sun's core achieves both. The pressure is about 265 billion times Earth's atmospheric pressure at sea level. The temperature is roughly 15 million degrees Celsius. Under these conditions, protons move so fast and collide so violently that they occasionally overcome their mutual repulsion and fuse, releasing energy in the form of gamma-ray photons. But here's a curious fact. The energy density of the sun's core, the amount of energy generated per unit volume, is actually quite low. It's only about 276 watts per cubic meter, roughly the same as a compost heap. The sun doesn't burn hot and fast. It burns slowly, steadily, fusing a tiny fraction of its hydrogen each second. The reason the sun is so bright is simply because it's so large. It has an enormous volume, so even a low energy density per cubic meter adds up to a staggering total output. And that energy, once generated, doesn't immediately leave. Photons created in the core scatter and bounce through the sun's interior, absorbed and re-emitted countless times. It can take 170,000 years for a photon to work its way from the core to the surface. And then once it reaches the surface, it takes just 8 minutes and 20 seconds to reach Earth. So the light falling gently on your pillow tonight began its journey in the sun's core long before human civilization existed, before the pyramids, before agriculture, before we even left Africa. That light has been traveling for longer than we've been recognizably human. And now it's here, warming your face, lighting the world. There's a boundary in the early solar system that determined what kind of planet would form where. Astronomers call it the frost line. And it's the distance from the young sun where temperatures dropped low enough for water ice to condense from the swirling disk of gas and dust. Inside the frost line, in the inner solar system where Mercury, Venus, Earth, and Mars formed, it was too hot for water to freeze. Water existed as vapor, and the solar wind from the young, active sun blew most of it away, along with hydrogen, helium, and other light gases. What remained were heavier elements: iron, silicon, magnesium, oxygen bound up in rocky minerals. These materials could withstand the heat, so they stuck around and gradually clumped together, building the rocky planets we see today. Beyond the frost line, roughly around where the asteroid belt is now, and extending outward, temperatures were cold enough for water to freeze into ice. And ice changes everything. Suddenly, there's much more solid material available to build planets with. Water is abundant in the universe, far more abundant than rock-forming elements. So beyond the frost line, planetary embryos could grow much larger, much faster. They became massive enough to capture hydrogen and helium directly from the surrounding nebula, accumulating vast atmospheres of gas. These became the giant planets: Jupiter, Saturn, Uranus, Neptune. This is why the solar system is divided the way it is. Small, rocky planets close to the sun. Giant, gas-rich planets farther out. It's not random. It's a consequence of temperature, of where ice could form, of what materials were available at different distances. The frost line is an invisible boundary, but it shaped the architecture of our entire planetary system. And here's something to think about. Earth formed just inside the frost line. We're a rocky planet, built from the materials that could survive the heat. But we're also close enough to the frost line that water could be delivered to us later, from comets and asteroids that formed farther out and then migrated inward. If Earth had formed just a bit closer to the sun, we might have ended up dry, like Venus. A bit farther out, and we might have become an ice world, like Europa. We sit in a special place, just the right distance for liquid water to pool on the surface, for oceans to form, for life to arise. The frost line didn't just determine what kind of planet Earth would be. It determined whether you'd be here, listening to this, thinking about frost lines and the origins of worlds. The moon is strange. It's unusually large compared to Earth. No other rocky planet has a moon so proportionally big. Its composition is oddly similar to Earth's mantle, but it's depleted in iron and volatile elements. For a long time, scientists debated where the moon came from. Did Earth capture it? Did it form alongside Earth as a sister body? Did it somehow split off from Earth's surface? The answer, according to our best current understanding, is more violent than any of those scenarios. The moon was born from a catastrophe. About 4.5 billion years ago, not long after Earth had formed and was still a hot, partially molten world, another, planet-sized object collided with it. We call this object Theia, after the Greek Titan, who was the mother of the moon goddess Selene. Theia was roughly the size of Mars, smaller than Earth, but still enormous, and it hit Earth not head-on, but at an angle, a glancing blow that was somehow both catastrophic and constructive. The collision vaporized Theia. It vaporized part of Earth's mantle. The impact was so violent that it melted the surface, possibly vaporizing much of Earth's early atmosphere. Debris, molten rock, vaporized metal, superheated gas sprayed out into orbit around Earth. Some of it fell back, raining down as molten droplets, but some of it stayed in orbit, forming a disk of debris circling Earth. And within that disk, over perhaps a few thousand years, the moon coalesced. This explains many of the moon's strange properties. It's made mostly of material from Earth's mantle, which is why its composition is similar to Earth's, but lacks a large iron core. It's depleted in volatiles because those elements would have been vaporized and lost during the impact. And it's large because the collision was so massive, so energetic, that it could eject enough material to build a big moon. In a sense, the moon is a piece of Earth, a fragment torn away in violence, reshaped by gravity, now orbiting the planet it came from. When you look up at the moon, you're seeing something that was once part of this world. It's a memorial to a collision that nearly destroyed Earth, that reshaped our planet entirely, that changed the course of everything that would follow. Without that collision, without Theia, there might be no moon. And without the moon, which stabilizes Earth's tilt, creates tides, influences our climate, Earth might be a very different place. Life might never have evolved, or might have evolved differently. The moon isn't just our companion. It's our sibling, our twin, born from the same violent moment that forged the modern Earth. The solar system today feels orderly. Planets orbit the sun in neat, mostly circular paths. They don't cross each other's orbits. They maintain stable distances. It's a clockwork mechanism, predictable and serene. But it wasn't always like this. For the first few 100 million years after the planets formed, the solar system was chaos. Planets migrated, moved inward or outward from their original positions, driven by gravitational interactions with the disk of gas and dust that still lingered, and with each other. Small planets collided and merged. Large planets scattered smaller bodies across the solar system. The whole system was unstable, rearranging itself, searching for a configuration that could last. Jupiter, in particular, was disruptive. Some models suggest Jupiter formed farther from the Sun than it is now, then migrated inward, nearly reaching Mars's current orbit, before reversing course and moving back outward. This inward then outward migration is called the Grand Tack, and it would have scattered asteroids, prevented a planet from forming in the asteroid belt region, and possibly delivered water to the inner planets by flinging icy bodies sunward. Saturn's formation and migration also played a role. When Saturn grew massive enough, its gravitational influence interacted with Jupiter's, causing both planets to shift their orbits. This reshuffling sent icy bodies from the outer solar system careening inward, triggering a period called the Late Heavy Bombardment, around 4 billion years ago. For a few 100 million years, the inner planets were pummeled by impacts, asteroids and comets smashing into Mercury, Venus, Earth, Mars, the Moon. The Moon's craters are a frozen record of this bombardment. Eventually, the system settled. The gas disk dissipated. The planets locked into stable orbits. The bombardment tapered off. What remains today is the survivors, the planets that didn't collide, that didn't get ejected, that found stable orbits and held them. But buried in the architecture of the solar system are hints of that early chaos. The asteroid belt that never became a planet, the Kuiper belt that might be the scattered remnants of a once more compact outer disk, the strange orbits of some asteroids and comets that still remember ancient encounters with the giant planets. The solar system is calm now, but it remembers violence. Every crater, every tilted axis, every backward rotation is a scar from those early chaotic days when worlds were still finding their places. Earth is a water world. Oceans cover more than 70% of the surface. Water exists in the atmosphere, locked in ice caps, trapped in rocks, flowing through rivers, pooling in lakes. Life as we know it depends entirely on water. But where did it all come from? When Earth formed, it did so inside the frost line, where temperatures were too high for water ice to condense. The materials that built Earth were largely dry, rocky, metallic, depleted in volatiles. So the water we have now likely arrived later, delivered by objects that formed farther out in the solar system, where ice could exist. Comets are obvious candidates. They're essentially dirty snowballs, ice mixed with rock and organic compounds, that formed in the outer solar system and occasionally get perturbed onto orbits that bring them close to the sun. When a comet impacts a planet, it delivers water. And early in the solar system's history, comets were far more common, scattered by the giant planets' migrations. But there's a problem. When scientists measure the isotopic composition of water in comets, specifically the ratio of deuterium, heavy hydrogen, to regular hydrogen, it doesn't quite match Earth's water. Most comets have too much deuterium. This suggests that comets alone can't explain all of Earth's oceans. Asteroids, particularly a type called carbonaceous chondrites, are a better match. These asteroids formed farther out in the solar system, where water ice could condense, and many of them contain water-locked in mineral structures. Meteorites from these asteroids have isotopic ratios that closely match Earth's oceans. So current thinking suggests that most of Earth's water came from asteroids, with some contribution from comets. Imagine that. Every time you drink a glass of water, you're drinking something that traveled across the solar system. Those water molecules formed in the cold outer regions, condensed onto dust grains, built asteroids, survived the violence of the early solar system, and eventually rained down on Earth as a bombardment of icy rocks. The water in your body is older than Earth itself, older than the sun, formed in the molecular clouds between stars. You are, quite literally, carrying around pieces of the ancient cosmos. Saturn's rings are one of the most iconic features in the solar system. They're beautiful, elegant, a set of impossibly flat structures that make Saturn instantly recognizable. You'd think something so prominent would be ancient, formed when Saturn itself formed, 4.6 billion years ago. But evidence is mounting that the rings might be much, much younger. Data from the Cassini spacecraft, which orbited Saturn for 13 years before plunging into the planet's atmosphere in 2017, suggests the rings could be only 100 million years old. That's young, cosmically speaking. It's recent. Dinosaurs still walked the Earth 100 million years ago. The rings might be younger than the Tyrannosaurus rex. How can we tell? The rings are too clean. They're mostly pure water ice, with very little rocky material or dust mixed in. But over billions of years, the rings should have been contaminated by micrometeorite impacts, which would darken them, and by dust swept in from interplanetary space. The fact that they're so pristine suggests they haven't been around long enough to accumulate significant contamination. So if the rings are young, where did they come from? The most likely scenario is that they formed when a moon or a large comet wandered too close to Saturn and crossed the Roche limit, the distance within which tidal forces from the planet become strong enough to tear an object apart. The moon or comet was shredded, its material spread out into a disk that became the rings. This means Saturn hasn't always had rings. For most of its history, it might have looked like Jupiter, a giant planet with a few faint, dusty rings. Nothing dramatic. The rings we see today might be a temporary feature, something that will last a few 100 million years before dispersing, before the particles spiral inward and rain onto Saturn, or escape outward and drift away. We're lucky, in a sense. We live in an era when Saturn has magnificent rings. They won't last forever. In a few 100 million years, they might be gone. And Saturn will be just another gas giant, still beautiful, but missing that iconic feature. For now, though, the rings are there, young, bright, pristine, a fleeting adornment on a giant world. About 4 billion years ago, the inner solar system experienced a cataclysm. For a period of perhaps 200 million years, Earth, the Moon, Mars, Venus, Mercury, all the inner worlds, were bombarded by asteroids and comets at a rate far higher than before or since. This period is called the Late Heavy Bombardment, and it left scars that are still visible today. On the Moon, which has no atmosphere or plate tectonics to erase its surface, the evidence is stark. Nearly every large crater on the Moon dates to this period. The lunar maria, those dark, smooth plains you can see with the naked eye, are vast pools of lava that erupted after enormous impacts cracked the Moon's crust. The bombardment was so intense that it melted and reshaped large portions of the lunar surface. Earth was hit too, probably harder than the Moon because Earth is larger and has stronger gravity. But Earth's surface is dynamic. Plate tectonics recycle the crust. Weathering erodes craters. Life colonizes and transforms the landscape. Very few traces of the late heavy bombardment remain on Earth, but if you could see Earth as it was 4 billion years ago, it would have been a hellscape. Impacts constantly lighting the sky, massive craters glowing red hot, oceans boiling away from the largest collisions, then condensing again once things cooled. What caused the bombardment? The most widely accepted explanation comes from something called the Nice model, named after the French city where it was developed. According to this model, the giant planets, Jupiter, Saturn, Uranus, Neptune, were originally in more compact orbits. But gravitational interactions between the planets and the remaining disk of planetesimals caused their orbits to shift. Jupiter moved inward slightly. Saturn, Uranus, and Neptune moved outward. This reshuffling destabilized the Kuiper Belt and scattered countless icy bodies inward toward the Sun. Many of those bodies collided with the inner planets, creating the Late Heavy Bombardment. If this model is correct, then the bombardment was an aftershock of planetary migration, a delayed consequence of the solar system's ongoing rearrangement. And it had profound effects. On Earth, it might have delayed the origin of life, or even reset it entirely if early life had already emerged, by sterilizing the surface with impacts. Or perhaps it delivered the final ingredients necessary for life: water, organic molecules, the building blocks that would eventually assemble into cells. The bombardment was destructive, but destruction and creation are often intertwined. Sometimes you need to break things apart before something new can begin. Earth doesn't spin upright. Its axis is tilted at about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is why we have seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight, and it's summer. 6 months later, when the northern hemisphere is tilted away, it's winter. The southern hemisphere experiences the opposite. Summer when the north has winter, winter when the north has summer. Without this tilt, Earth would have no seasons. Every day would be roughly the same length everywhere, and the sun would trace the same path across the sky year-round. The equator would be hot, the poles cold, and every region would stay in a kind of permanent equilibrium. Life would still exist, probably, but it would be different. Many ecosystems depend on seasonal changes, migrations, breeding cycles, plant flowering and fruiting, all synchronized to the rhythm of the seasons. But here's the interesting part. Earth's tilt is unusually stable compared to other planets. Mars's tilt, for example, varies wildly over millions of years, swinging between about 15 degrees and 35 degrees, possibly even more extreme in the distant past. This happens because Mars has only small moons, Phobos and Deimos, both tiny captured asteroids, that exert almost no stabilizing influence. So Mars's tilt is buffeted by gravitational perturbations from other planets, and it wobbles chaotically. Earth's tilt is stabilized by the moon. The moon is large and close enough that its gravitational pull acts like a gyroscope, damping out the perturbations that would otherwise cause Earth's tilt to vary. Without the moon, Earth's tilt might swing between 0 degrees and 85 degrees over tens of millions of years. Imagine the climate chaos that would cause. Periods where the equator is the coldest place and the poles are tropical, followed by periods where the tilt is nearly 0 and there are no seasons at all. So the moon doesn't just give us tides and light up the night sky. It stabilizes our climate, makes our seasons predictable, and creates an environment where complex life can evolve and thrive over hundreds of millions of years. Without the moon, Earth might still have life, but it would be simpler, more resilient to rapid climate swings, less diverse. The moon, formed in violence, now serves as a stabilizer, a silent guardian that keeps Earth's axis from wobbling too wildly, keeps our seasons in their rhythms, keeps the world habitable in ways we rarely think about. The sun is not constant. It's changing, slowly but inevitably, as it ages. When the sun first ignited nuclear fusion about 4.6 billion years ago, it was dimmer than it is now, about 70% of its current brightness. Over billions of years, it has gradually brightened. Today, it's about 10% brighter than when Earth formed, and it will continue brightening. Why? Because the sun is running out of hydrogen in its core. As fusion converts hydrogen to helium, the core's composition changes. Helium is heavier than hydrogen, so the core becomes denser. To maintain the pressure needed to support the sun's weight, the core must get hotter. And as the core gets hotter, fusion speeds up, releasing more energy. More energy means the sun shines brighter. This gradual brightening has implications for Earth. Early in our planet's history, the sun was dimmer, so Earth should have been colder. There's a puzzle called the faint young sun paradox. Geological evidence shows liquid water existed on Earth's surface 4 billion years ago, but with a dimmer sun, the oceans should have been frozen solid. The solution probably involves a thicker atmosphere back then, with more greenhouse gases trapping heat, compensating for the weaker sunlight. But the brightening continues. In about 1 billion years, roughly a fifth of the time that's already passed since Earth formed, the sun will be about 10% brighter than it is today. That might not sound like much, but it's enough to tip Earth's climate into a runaway greenhouse effect. Oceans will evaporate, water vapor will fill the atmosphere, and water vapor is itself a greenhouse gas, trapping even more heat. Temperatures will climb until Earth resembles Venus, a scorched, lifeless world. Long before the sun becomes a red giant and engulfs the inner planets, long before it runs out of hydrogen entirely, Earth will become uninhabitable. Not from a dramatic disaster, but from a slow, inexorable brightening. The sun that gives us life will eventually take it away, not through malice, but simply by aging, by doing what stars do. In 1 billion years, if humans or our descendants still exist, they'll need to find another home. The sun won't stop shining for us. It will keep shining, brighter and brighter, until Earth is no longer a place where anything can live. If you want to touch something older than Earth, you don't need a time machine. You just need a meteorite. Meteorites are rocks from space, fragments of asteroids, occasionally pieces of the Moon or Mars, that survive the journey through Earth's atmosphere and land on the surface. And many of them are ancient. The oldest meteorites, called carbonaceous chondrites, date to about 4,567 billion years old. They formed in the earliest days of the solar system, before planets existed, when the protoplanetary disk was just beginning to coalesce into larger bodies. These meteorites are time capsules. They preserve the original materials of the solar nebula, dust grains, minerals, even organic molecules, largely unchanged. On Earth, no rocks this old exist. Our planet has been geologically active for billions of years. Plate tectonics recycle the crust. Erosion wears down mountains. The oldest rocks on Earth, found in remote regions of Canada and Australia, are about 4 billion years old, and even those have been altered by heat and pressure. There's nothing truly pristine left from Earth's formation. But meteorites? They've been sitting in the vacuum of space, in the cold and dark, for 4,567 billion years. They haven't melted. They haven't been buried and cooked under pressure. They're fossils from the solar system's birth, carrying information about conditions in the protoplanetary disk, about the processes that built planets, about the chemistry of the early solar system. Some meteorites even contain presolar grains, tiny dust particles that are older than the sun itself. These grains formed around other stars, stars that lived and died before our solar system existed. When those stars exploded as supernovae or shed their outer layers as planetary nebulae, they released these grains into interstellar space. Eventually, they drifted into the cloud of gas and dust that would become our solar system, and they were incorporated into asteroids. Now they're here, in meteorites, literal stardust that predates the sun. Holding a meteorite is a strange experience. It looks like a rock. It feels like a rock. But it's older than mountains, older than oceans, older than Earth's core. It's a piece of the beginning, a fragment from the moment when the solar system was just a cloud starting to collapse. And now it's in your hand, bridging billions of years, connecting you directly to the origins of everything around you. Jupiter is often called the guardian of the inner solar system, and there's truth to that. Its immense mass, more than twice the mass of all other planets combined, creates a gravitational influence that extends far beyond its immediate vicinity. And that influence shapes the orbits of countless smaller objects, particularly comets coming from the outer solar system. When a comet's orbit brings it close to Jupiter, the giant planet's gravity can dramatically alter the comet's trajectory. Sometimes Jupiter captures comets entirely, pulling them into orbit around itself, or even causing them to crash into its atmosphere, as happened with comet Shoemaker-Levy 9 in 1994. Other times, Jupiter flings comets outward, sending them into the outer solar system, or even ejecting them from the solar system entirely. And sometimes, Jupiter deflects comets that were heading toward the inner planets, nudging their orbits just enough that they miss Earth, Venus, or Mars. Without Jupiter, the inner solar system would experience more impacts. Comets from the Kuiper Belt and the Oort cloud, perturbed into sun-crossing orbits, would have a clearer path to reach Earth. Studies suggest that Jupiter reduces the impact rate on Earth by perhaps a factor of a few, maybe 2, maybe 5, depending on the assumptions. That's significant, though not as dramatic as some popularizations suggest. Jupiter doesn't eliminate impacts, but it does reduce their frequency. This has implications for life. Large impacts can be devastating, potentially causing mass extinctions, as happened 66 million years ago when an asteroid struck Earth and ended the age of dinosaurs. If Jupiter reduces the impact rate, it might make it easier for complex life to evolve and persist by extending the time between catastrophic collisions. In this sense, Jupiter might have played a role in making Earth habitable over long time scales, not by directly affecting Earth, but by patrolling the outer reaches, intercepting some of the threats that would otherwise reach us. But Jupiter's influence isn't entirely benign. Sometimes it scatters objects inward, increasing the impact rate temporarily, especially during periods of orbital reorganization, like the late heavy bombardment. Jupiter gives, and Jupiter takes away. It's a guardian, but also an unpredictable one, whose effects depend on the complex choreography of orbits and gravitational interactions that define the solar system's evolution. When we think about planets forming, we might imagine a slow, gradual process, materials accumulating grain by grain over hundreds of millions of years. But the reality is surprisingly fast. Once the solar nebula began collapsing, the planets assembled rapidly, perhaps in just 3 to 10 million years. 3 to 10 million years. That sounds like a long time, and by human standards it is. It's longer than our species has existed, but in cosmic terms, it's a blink. The solar system is 4.6 billion years old. The planet formation period was less than 0.25% of that age. If you compressed the entire history of the solar system into a single year, planet formation would be over in less than a day, maybe just a few hours. Why so fast? Because once the process begins, it accelerates. Dust grains stick together through static electricity and molecular forces, forming larger particles. These particles settle into the midplane of the protoplanetary disk, creating a dense layer where collisions are more frequent. Pebbles accumulate into planetesimals, boulder-sized to mountain-sized objects. And once planetesimals reach a certain size, their gravity becomes significant. They start pulling in nearby material actively, not just waiting for random collisions. Growth accelerates, the big get bigger, runaway accretion takes over. Within 1,000,000 years, you have planetary embryos, objects the size of the Moon or Mars. Within a few million years more, these embryos collide and merge, building the terrestrial planets. The giant planets form even faster in their cores, racing to accumulate enough mass to capture gas from the surrounding nebula before the nebula dissipates, blown away by the young sun's intense radiation and stellar wind. This rapid time scale has been confirmed by studying meteorites, which preserve isotopic signatures that act like timestamps. We can measure how long it took for different objects to cool, to solidify, to lock in their chemical compositions. And the answer is always the same: fast. The solar system went from a diffuse cloud to a set of planets in less time than it takes continents to drift a few 100 kilometers. It's a reminder that the universe, when it decides to build something, doesn't dawdle. Forces conspire: gravity, collision, chemistry, and worlds emerge from the chaos quickly, decisively, as if the cosmos is impatient to see what comes next. Mars today is cold and dry, with an atmosphere so thin you could barely call it one. The atmospheric pressure at the surface is less than 1% of Earth's, so low that liquid water can't exist. Any water exposed to the Martian atmosphere either freezes or evaporates almost instantly. But it wasn't always this way. Billions of years ago, Mars had a thicker atmosphere. Evidence is written across its surface: ancient river valleys, lake beds, minerals that only form in the presence of liquid water. Mars once had rain. It had rivers that flowed for extended periods, carving channels into the bedrock. It had lakes, maybe even a northern ocean. The climate was warmer, wetter, more Earth-like. And then slowly, the atmosphere disappeared. Why? 2 reasons: weak gravity and no magnetic field. Mars is smaller than Earth, so its gravity is weaker. Lighter gases can escape more easily, especially when energized by solar radiation. On Earth, our stronger gravity holds onto our atmosphere more tightly. But even that wouldn't be enough without our second defense: a magnetic field. Earth's magnetic field, generated by the churning of molten iron in our core, extends far out into space, creating a protective bubble called the magnetosphere. This field deflects the solar wind, the stream of charged particles constantly flowing from the sun. Without this protection, the solar wind would slam directly into Earth's atmosphere, stripping away atoms and molecules, slowly eroding the air we breathe. Mars once had a magnetic field too. Evidence from magnetized rocks suggests that early Mars had a global magnetic field, generated by a liquid iron core. But Mars is smaller, so it cooled faster. Eventually, the core solidified, or at least stopped convecting vigorously enough to generate a magnetic field. The field died, and without it, the solar wind began stripping away Mars's atmosphere directly. This process, atmospheric stripping, happens slowly, over hundreds of millions of years, but it's relentless, atom by atom. molecule by molecule. The solar wind carries Mars's atmosphere away into space. What remains is a thin remnant, a ghost of what once existed. Mars transformed from a potentially habitable world into a frozen desert, not because of a single catastrophe, but because of a slow bleed that it couldn't stop. The lesson here is haunting. A planet's habitability depends not just on its distance from the sun, not just on having water, but on being able to hold on to an atmosphere. Mars had everything it needed for life, perhaps, but it couldn't maintain those conditions. The atmosphere leaked away, the water froze or evaporated, and the surface became the cold, barren place we see today. Mars's story is a reminder that habitability is fragile, that planets can lose what makes them livable, and that protection, gravity, a magnetic field, matters as much as resources. Beyond Neptune, beyond the realm of the 8 official planets, lies a vast ring of icy objects called the Kuiper Belt. It's a cold, dark region stretching from about 30 astronomical units, 30 times the Earth-Sun distance out, to perhaps 50 or 55 AU. In this frigid zone, temperatures hover just a few dozen degrees above absolute zero, and sunlight is dim, barely distinguishable from starlight to the human eye. The Kuiper Belt is populated by leftovers. When the solar system formed, not everything got incorporated into planets. Beyond Neptune, the material that condensed from the protoplanetary disk remained scattered, never accumulating into a large planet. What exists there now are hundreds of thousands of icy bodies, maybe millions, maybe more, ranging in size from a few kilometers across to objects as large as Pluto. These bodies are pristine in a sense. They've been frozen in place for billions of years, barely altered since they formed. No geological activity melts them or recycles their surfaces. No thick atmospheres weather them. They're time capsules, preserving the original composition of the outer solar nebula. When we study Kuiper Belt objects, we're studying the raw materials that built the outer planets, the same ice and rock that would have formed Neptune and Uranus if there had been more of it. Pluto is the most famous Kuiper Belt object, though it was discovered long before we understood the Kuiper Belt existed. When New Horizons flew past Pluto in 2015, it revealed a world far more complex than anyone expected. Mountains of water ice, plains of nitrogen ice, an atmosphere that freezes onto the surface during winter and evaporates during summer. Pluto isn't just a frozen rock, it's a geologically active world, shaped by processes we're still working to understand. And Pluto isn't alone. There's Eris, slightly more massive than Pluto, whose discovery in 2005 led to Pluto's reclassification. There's Makemake, Haumea, Quaoar, Sedna, each with their own strange properties, their own stories. Haumea spins so fast it's stretched into an ellipsoid, and it has rings. Sedna's orbit takes it far beyond the Kuiper Belt, into a region we barely understand, hinting at influences from passing stars, or perhaps a distant, undiscovered planet. The Kuiper Belt is a frontier, a region we're only beginning to explore. Every new discovery changes our understanding of the solar system's architecture, of how planets form, of what kinds of worlds can exist in the cold and dark. And beyond the Kuiper Belt lies the even more mysterious Oort cloud, a theoretical sphere of comets extending perhaps halfway to the nearest star. The solar system doesn't end at Neptune. It extends far, far beyond, fading gradually into the space between stars, filled with icy wanderers that remember the beginning. Jupiter has 95 known moons, and counting, but 4 of them stand out, so prominent that Galileo Galilei could see them with his crude telescope in 1610. These are the Galilean moons, Io, Europa, Ganymede, and Callisto. Each is large, each is unique, and together they form a miniature solar system, a laboratory for understanding how worlds evolve. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Its surface is constantly resurfaced by lava flows, so it has almost no impact craters. The volcanism is powered by tidal heating. Jupiter's immense gravity stretches and squeezes Io as it orbits, generating friction inside the moon that melts rock. Io's volcanoes spew sulfur and sulfur dioxide, giving the moon its yellow and orange coloration, like a cosmic pizza. It's violent, active, constantly changing. Europa, the next moon out, is the opposite. Its surface is ice, smooth and bright, crisscrossed with dark streaks and cracks, but almost no craters. Beneath the ice likely lies a global ocean, liquid water, perhaps twice the volume of all Earth's oceans combined. Europa is also tidally heated, though less intensely than Io. The heating keeps the subsurface ocean liquid, and the ice shell above it fractures and shifts, creating the patterns we see. Europa is one of the most promising places to search for life beyond Earth. The ocean is in contact with a rocky core, potentially providing minerals and chemical energy. And where there's liquid water, energy, and chemistry, there might be life. Ganymede, the largest moon in the solar system, larger than Mercury, has its own magnetic field, the only moon known to have one. Its surface is a mix of old, dark, heavily cratered terrain, and younger, brighter grooved terrain where tectonic activity has resurfaced the ice. Ganymede probably has a subsurface ocean too, buried beneath several layers of ice. It's a complex world with geology, magnetism, and possibly an ocean, a reminder that moons can be as intricate as planets. Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system. Its surface is ancient, barely altered since the late heavy bombardment. Unlike the other 3, Callisto shows little sign of internal activity. It's cold, inert, a museum of impacts, and yet there's evidence it too might have a subsurface ocean, though buried deep and isolated from the surface. 4 moons, 4 stories. Io tells a story of volcanic fury driven by tidal forces. Europa tells a story of a hidden ocean, sealed beneath ice, tantalizingly close yet frustratingly inaccessible. Ganymede tells a story of complexity, of a world with multiple layers and a magnetic personality. Callisto tells a story of stillness, of a surface that remembers the violence of the past but has moved on. Together they show how different paths can emerge from similar beginnings, how worlds diverge based on their distance from their planet, their internal composition, the resonances they're locked into. The Galilean moons are a reminder that even in a single planetary system, diversity thrives. The sun has been shining for 4.6 billion years, and it will continue shining for another 5 billion, give or take. It's roughly halfway through its main sequence lifetime, the stable period when a star fuses hydrogen into helium in its core. In human terms, the sun is middle-aged, past its youth, but not yet approaching old age. This is comforting in a way. The sun isn't going to die anytime soon. It's not going to suddenly flicker out, leaving the solar system dark and frozen. There's time, billions of years of time, before the sun exhausts its hydrogen and begins the next phase of its life. But that next phase will be dramatic. When the hydrogen in the sun's core runs out, fusion will stop there. The core will contract, heating up, while hydrogen fusion continues in a shell around the core. This shell burning will cause the sun to expand enormously, swelling into a red giant. Its outer layers will extend beyond the orbit of Mercury, possibly beyond Venus, perhaps even reaching Earth. The sun will become hundreds of times larger than it is now, cooler at the surface but vastly more luminous overall. During this red giant phase, the sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. At the center, the core will remain, a hot, dense ember called a white dwarf. This white dwarf will be roughly the size of Earth, but contain about half the sun's current mass. It will shine with leftover heat, gradually cooling over trillions of years, eventually fading to a cold, dark black dwarf, a stellar corpse that emits no light. But all of that is far in the future. For now, the sun is stable, steady, fusing hydrogen in its core at a rate that produces just enough energy to balance gravity's inward pull. It's been doing this for billions of years, and it will continue doing it for billions more. The sun is patient. It burns slowly, carefully, ensuring its fuel lasts as long as possible. And in the meantime, it provides the light and warmth that makes life possible, that drives weather, that powers photosynthesis, that allows worlds to be more than frozen rocks in the darkness. The sun is middle-aged, but that's okay. Middle age is a good time, stable, reliable. The sun has found its equilibrium, and it's content to stay there, shining for eons to come. When Earth first formed, it was hot, tremendously hot. The process of accretion, millions of collisions, each one releasing kinetic energy as heat, melted much of the planet. Add to that the heat from radioactive decay, particularly from short-lived isotopes that were abundant in the early solar system, and Earth became a ball of molten rock and metal, a magma ocean, possibly thousands of kilometers deep. In this molten state, something important happened: differentiation. Heavier elements, primarily iron and nickel, sank toward the center, pulled by gravity. Lighter elements, silicon, oxygen, magnesium, floated toward the surface. Over time, this separation created Earth's layered structure: a dense iron-nickel core, a thick mantle of silicate rock, and a thin crust on the surface. The core itself is divided into two parts. The inner core, at the very center, is solid, a ball of crystallized iron about 1,200 kilometers in radius, under such immense pressure that it remains solid despite temperatures exceeding 5,000 degrees Celsius. The outer core, surrounding the inner core, is liquid iron mixed with lighter elements. This liquid outer core is about 2,200 kilometers thick, and it's in constant motion, driven by heat escaping from the core and by the Earth's rotation. That motion is crucial. The flowing, electrically conductive liquid iron generates Earth's magnetic field through a process called the geodynamo. Convection currents in the outer core, combined with Earth's rotation, create complex patterns of flow that generate and maintain the magnetic field. Without this process, Earth would have no magnetic field, and without a magnetic field, Earth would be vulnerable to the solar wind, just like Mars. Our atmosphere might have been stripped away billions of years ago, so Earth's iron core isn't just a dense lump of metal sitting at the center. It's an active, dynamic system that protects us, that makes the planet habitable. The core formed through differentiation, through the simple process of heavy things sinking, But that process had profound consequences. It created a shield, invisible but essential, that allows Earth to maintain an atmosphere, that deflects radiation, that makes life on the surface possible. The core is hidden, buried beneath thousands of kilometers of rock, but it's working for us every moment. A planetary engine that's been running for billions of years. If you could view the solar system from above, you'd notice something remarkable. All the planets orbit in nearly the same flat plane. There's some variation. Mercury's orbit is tilted at 7 degrees, and Pluto's, though no longer a planet, is tilted even more. But the major planets all stay within a few degrees of the same plane, called the ecliptic. This isn't a coincidence. It's a consequence of how the solar system formed. When the solar nebula, the cloud of gas and dust that would become the sun and planets, began collapsing under its own gravity, it was spinning. And as it collapsed, it spun faster. Just like an ice skater spins faster when they pull their arms in. But the nebula couldn't collapse equally in all directions. The spinning prevented collapse in the direction perpendicular to the spin axis. Material could fall inward along the spin axis, but perpendicular to that, the centrifugal effect from rotation resisted collapse. The result was that the nebula flattened into a disk, thick at first, but gradually thinner as material settled into the midplane. This disk is called a protoplanetary disk, and it's where planets form. Dust grains in the disk collide and stick together. Larger objects sink toward the midplane, where collisions are more frequent. Planets assemble in this midplane, inheriting the disk's flatness. So when we see all the planets orbiting in roughly the same plane, we're seeing the fossil record of the protoplanetary disk, the original structure from which everything formed. This flatness is common. When we observe young stars with protoplanetary disks, we see the same thing, flat, spinning disks. When we discover exoplanets around other stars and map out their orbits, we often find they orbit in the same plane. It's a signature of formation from a disk, a pattern that repeats throughout the universe. There's something elegant about this. The solar system isn't random. Its structure, the way planets orbit, the plane they share, reflects its origin. The disk that existed 4.6 billion years ago is gone, dispersed or incorporated into planets, but its shape is preserved in the orbits we see today. The past left a mark, a geometric memory, that we can still read in the arrangement of worlds around the sun. Comets are wanderers. They appear in the inner solar system, seemingly from nowhere, growing bright tails as they approach the sun, then fading as they retreat. For much of human history, comets were mysteries, omens, portents, objects of fear and wonder. We know better now. Comets are icy bodies from the outer solar system, and they come from two main reservoirs. The first is the Kuiper Belt, which we've already discussed, a ring of icy objects beyond Neptune. Comets originating from the Kuiper Belt are called short-period comets. Their orbits are relatively predictable, taking less than 200 years to complete. Halley's Comet, perhaps the most famous comet, is a short-period comet with an orbital period of about 76 years. These comets stay relatively close to the ecliptic, the plane in which the planets orbit, because they come from the Kuiper Belt, which is also aligned with that plane. The second reservoir is the Oort cloud, a hypothetical spherical shell of icy bodies surrounding the solar system at its outermost edge. The Oort cloud is thought to extend from about 2000 AU to as far as 100,000 AU from the Sun, halfway to the nearest star. It's so distant that the Sun's gravity is incredibly weak there, and the objects in the Oort cloud are barely bound to the solar system. Passing stars, or the gravitational tide from the Milky Way galaxy itself, can perturb these objects, nudging them onto trajectories that bring them plunging toward the inner solar system. Comets from the Oort cloud are called long-period comets. They can have orbital periods of thousands or even millions of years. They can arrive from any direction, not just from the ecliptic, because the Oort cloud is spherical, not disc-shaped. When one of these comets enters the inner solar system for the first time, it's often fresh, pristine, never before heated by the sun. It outgasses furiously, creating spectacular tails. The Oort cloud has never been directly observed. It's too far, and the objects there are too small and dark to detect with current telescopes. But its existence is inferred from the orbits of long-period comets, which consistently point back to this distant region. It's a hidden part of the solar system, a vast reservoir holding perhaps trillions of icy bodies, remnants from the solar system's formation that were scattered outward by gravitational interactions with the giant planets. So when you see a comet, you're seeing something ancient, something that has spent almost its entire existence in the cold and dark, far from the sun. It's a visitor from the edge, carrying ice and dust that date back to the solar system's birth, and after its brief moment in the sunlight, growing a tail, shining brightly, it will retreat again, back to the outer darkness, perhaps not to return for thousands of years, or ever. The Nice model, named after the city in France where researchers developed it, proposes a dramatic restructuring of the outer solar system early in its history. According to this model, the giant planets didn't form in their current positions. They started closer together, in more compact orbits, and something triggered a gravitational upheaval that sent them migrating to where they are now. Here's how it might have happened. About 600 million years after the solar system formed, the planets were interacting gravitationally with a disk of icy planetesimals left over from the formation period. These interactions caused the planets to migrate slowly. Jupiter moved inward slightly, gaining energy from the disk. Saturn, Uranus, and Neptune moved outward, losing energy to the disk. Eventually, Jupiter and Saturn crossed a critical orbital resonance, a configuration where their orbital periods were in a simple ratio, like 2:1, meaning Jupiter completed 2 orbits for every one of Saturn's. Resonances amplify gravitational interactions, making them much stronger. When Jupiter and Saturn entered this resonance, the effects on the outer solar system were catastrophic. Saturn's orbit became more eccentric, more elliptical. Uranus and Neptune were scattered outward into the disk of planetesimals. The disk itself was destabilized. Icy bodies were flung in all directions, some inward toward the inner planets, triggering the late heavy bombardment. Some outward, forming the scattered disk and perhaps replenishing the Oort cloud. Some ejected from the solar system entirely. Neptune, in particular, migrated a long way, perhaps from around 20 AU to its current 30 AU. As it plowed through the disk, it scattered objects, but it also captured some, placing them into stable orbits. Many Kuiper Belt objects we see today might have been captured by Neptune during this migration. The NICE model explains a lot. Why the late heavy bombardment happened 600 million years after the planets formed. Why Neptune is farther from the Sun than Uranus, despite being more massive. Why the Kuiper Belt has the structure it does. Why certain groups of asteroids and Kuiper Belt objects share specific orbital characteristics. But it's still a model, a hypothesis that fits the evidence but hasn't been definitively proven. There are variations and alternatives. Some researchers propose earlier or later migrations, different resonance crossings, additional unseen planets that were ejected. The details are still being worked out, but the core idea that the giant planets migrated, that the solar system restructured itself hundreds of millions of years after formation, is now widely accepted. The solar system we see today is not its original configuration. It's a rearranged version, the result of gravitational upheaval, of planets pushing and pulling on each other until they found stable positions. And those stable positions might not be permanent. Over billions more years, subtle perturbations could cause further changes. The solar system is still evolving, still settling, still searching for equilibrium in the slow dance of gravity. Magnetic fields might seem like abstract, invisible things, but they're crucial for planetary habitability. They protect atmospheres from being stripped away by the solar wind. They shield surfaces from harmful cosmic radiation. They create auroras as charged particles spiral along field lines. Earth has a strong magnetic field. The other terrestrial planets, not so much. Mercury has a weak magnetic field, but it's a mystery why. Mercury is small, and conventional wisdom says its core should have cooled and solidified long ago, shutting down any dynamo that might generate a field. Yet measurements from the Messenger spacecraft confirmed that Mercury has a global magnetic field, albeit one only about 1% the strength of Earth's. No one knows exactly why. Maybe the core hasn't fully solidified. Maybe there's some unusual composition or process that keeps it partially liquid. It's a puzzle. Venus has no magnetic field at all, at least not a global one. This is strange because Venus is nearly Earth's twin in size and composition. It should have a liquid core capable of generating a field. But Venus rotates extremely slowly, one rotation every 243 Earth days. Perhaps that slow rotation prevents the convection patterns necessary for a dynamo. Or perhaps Venus's core has solidified, or never differentiated properly. Or some ancient impact disrupted whatever field it once had. We don't know for certain. Mars once had a strong magnetic field, but it died billions of years ago. We know this because ancient Martian rocks are magnetized, frozen records of the field that existed when they cooled. But at some point, probably within the first few 100 million years of Mars's history, the field shut off. Mars's small size meant its core cooled quickly. Once the core stopped convecting vigorously, the dynamo failed. And without a magnetic field, Mars's atmosphere became vulnerable to the solar wind. Over billions of years, the atmosphere was stripped away, and Mars transformed into the cold, dry world we see today. Earth is the exception. Our magnetic field has persisted for at least 3.5 billion years, possibly longer, protecting our atmosphere, making life on the surface possible. We're lucky, in a sense. If Earth were slightly smaller, it might have cooled too quickly, like Mars. If Earth rotated slower, it might have failed to generate a field, like Venus. But Earth hit the sweet spot, large enough, rotating fast enough, with the right internal composition to maintain a protective magnetic field for billions of years. It's a reminder that small differences matter. The terrestrial planets are all made of similar materials, all formed in the same region of the solar system. But slight variations in size, rotation, and thermal history led to vastly different outcomes. Earth thrives, Mars is dead, Venus is inhospitable, and Mercury, tiny and scorched, clings to a weak field that shouldn't exist. Each planet tells a different story of how magnetic fields arise, persist, or fail, and how those fields determine a world's fate. Jupiter is so far from the Sun that sunlight there is dim and weak, only about 4% as intense as it is on Earth. You'd expect Jupiter to be cold, frozen, inert. But when we measure the heat Jupiter radiates into space, we find something surprising. Jupiter emits about 1.7 times more energy than it receives from the Sun. It's glowing with internal heat, still warm from its formation. This isn't nuclear fusion. Jupiter isn't massive enough to ignite fusion in its core. It would need to be about 80 times more massive to become a star. Instead, Jupiter's heat comes from a slower, gentler process, gravitational contraction. Jupiter is still shrinking very slowly, compressing under its own weight. As it contracts, gravitational potential energy converts to heat, warming the interior and radiating out into space. This process has been ongoing for billions of years. When Jupiter first formed, it was much larger and hotter. Over time, it's been cooling and contracting, releasing heat steadily. The contraction is tiny, perhaps a centimeter per year, imperceptible on human timescales. But over millions of years, it adds up. And the heat released is substantial, enough to power Jupiter's weather, to drive the massive storms that rage in its atmosphere, to create the swirling bands and zones that make Jupiter so visually striking. In a way, Jupiter is almost like a failed star. It formed through the same process, gravitational collapse of gas, but it stopped short of the mass needed for fusion. It's a brown dwarf's little cousin, an object caught between planet and star, massive enough to generate internal heat, but not massive enough to truly shine. It glows, but only in infrared, in heat radiation invisible to human eyes. This internal heat also affects Jupiter's moons. Io, the closest large moon, is tidally heated by Jupiter's gravity, but Jupiter's own warmth contributes to the complex thermal environment. The heat Jupiter radiates outward creates a dynamic system, a miniature solar system where the central body isn't just reflecting sunlight, but generating energy internally. Jupiter will continue cooling, continue contracting, for billions of years to come. Eventually, eons from now, it will reach equilibrium, a cold gas giant in thermal balance with its surroundings. But for now, Jupiter is still young, still warm, still slowly releasing the heat of its birth into the cold of space. Venus is a world of extremes, and its atmosphere might be the most extreme feature of all. The clouds that shroud Venus aren't water clouds like Earth's. They're made of sulfuric acid, concentrated acid droplets suspended in an atmosphere of carbon dioxide. These clouds form a complete, unbroken layer about 50 to 70 kilometers above the surface, reflecting most of the sunlight that reaches Venus and giving the planet its bright, featureless appearance. But here's what's truly bizarre. These clouds circle the entire planet in just 4 Earth days. That's super rotation. Venus itself rotates once every 243 Earth days, slowly spinning backward. But the atmosphere doesn't care about the surface rotation. It moves independently, whipping around the planet at speeds reaching 360 kilometers per hour in the upper atmosphere, faster than the most intense hurricanes on Earth. Why does this happen? No one fully understands. On Earth, the atmosphere rotates roughly with the surface because friction couples them together. But on Venus, something decouples the atmosphere from the surface. The dense lower atmosphere, heated by the intense surface temperatures, might transport energy upward in ways that drive the upper atmosphere to move faster. Tidal effects from the sun might play a role. Complex interactions between heat absorption, atmospheric chemistry, and planetary rotation create a system we're still working to model accurately. The result is a planet where the weather moves dramatically faster than the ground beneath it. If you could somehow stand on Venus's surface, protected from the crushing pressure and searing heat, and watch the clouds above, they'd race across the sky, day and night on Venus, determined by the planet's rotation, last months. But the clouds above complete their circuit in days, creating a disconnect between surface time and atmospheric time that feels almost surreal. Venus's clouds also contain mysteries beyond their composition and speed. They have dark patches that absorb ultraviolet light, creating patterns visible only in UV images. These patches might be chemical compounds, perhaps sulfur or unknown photochemical products, or even, speculatively, microbial life adapted to the acidic cloud environment. It's unlikely, but the clouds of Venus are one of the few places in the solar system where conditions might, just possibly, allow for airborne life. The surface is hellish, but high in the atmosphere, temperatures and pressures are almost Earth-like. Water is scarce and the acidity is extreme, but life has surprised us before. For now, Venus's clouds remain a frontier, a toxic, fast-moving, acid-laden atmosphere that challenges our understanding and hints at complexities we haven't yet unraveled. Venus hides beneath those clouds, invisible, mysterious, a world we've barely begun to explore. Enceladus is small, only about 500 kilometers in diameter, small enough to fit within the borders of Arizona. It's one of many moons orbiting Saturn, and for a long time, it seemed unremarkable. But in 2005, the Cassini spacecraft flew close to Enceladus and discovered something astonishing: geysers erupting from the moon's south pole, shooting plumes of water ice and vapor into space. These aren't small geysers. The plumes extend hundreds of kilometers above the surface, and they're constant, ongoing, continuously spraying material into space. Some of the water escapes Enceladus's weak gravity entirely and spreads out along the moon's orbit, supplying material for Saturn's faint E-ring. Other particles fall back to the surface, replenishing the ice and keeping Enceladus bright and reflective. But the real discovery came from analyzing the plumes. Cassini flew through them multiple times, tasting the water with its instruments. And what it found was remarkable. Water, yes, but also salt, indicating the water comes from a salty ocean. Organic molecules, complex carbon compounds, silica grains, suggesting the ocean is in contact with a rocky core, where hydrothermal activity might be occurring, and molecular hydrogen, which could serve as an energy source for microbial life. Enceladus has all the ingredients for life: liquid water, organic molecules, energy, a rocky interface where chemistry can happen. It's one of the most promising places in the solar system to search for extraterrestrial life, and we didn't even know it had an ocean until Cassini arrived. The ocean exists because of tidal heating. Enceladus orbits Saturn in resonance with another moon, Dione, which amplifies the gravitational tug on Enceladus. This constant stretching and squeezing generates heat inside the moon, enough to keep a subsurface ocean liquid, despite Enceladus being so far from the sun that surface temperatures are around 200 degrees Celsius. The geysers erupt through cracks in the ice, features called tiger stripes because of their appearance. These cracks are warmer than the surrounding terrain, and they're geologically active, opening and closing in response to tidal forces. When the cracks open, pressure from the ocean below forces water upward, and it erupts into the vacuum of space, instantly freezing into ice crystals. Enceladus is giving us a free sample of its ocean. We don't need to drill through kilometers of ice like we would on Europa. The ocean is coming to us, erupting into space where we can fly through it and analyze it. It's one of the most generous moons in the solar system, offering its secrets freely, inviting us to investigate, to wonder, to dream about what might live in the dark waters beneath its frozen shell. If you move away from a heat source, you expect things to get cooler. Stand close to a fire and you feel the heat. Step back and it fades. This is intuitive, basic thermodynamics, but the sun violates this expectation in a strange and dramatic way. The sun's surface, the photosphere, has a temperature of about 5,500 degrees Celsius. This is the layer we see, the glowing sphere that lights the day. Above the photosphere lies the chromosphere, a thin layer where temperatures rise to about 20,000 degrees, and above that lies the corona, the sun's outer atmosphere, a tenuous halo of plasma extending millions of kilometers into space. The corona is hot, not just warm, not just a little hotter than the surface. The corona reaches temperatures of 1 to 3 million degrees Celsius, sometimes even higher. You're moving away from the sun's core, away from the source of energy, and somehow things are getting hundreds of times hotter. It makes no sense, at least not intuitively. This is called the coronal heating problem, and despite decades of research, we still don't fully understand it. Energy is being transferred from the cooler surface to the hotter corona. But how? Several mechanisms have been proposed. One involves magnetic fields. The sun's magnetic field lines thread through the corona, and they're constantly moving, twisting, reconnecting. When magnetic field lines reconnect, snap and rejoin in new configurations, they release energy, heating the surrounding plasma. Another mechanism involves waves. Oscillations at the sun's surface generate waves that propagate upward into the corona, where they dissipate, converting their energy into heat. Both mechanisms probably contribute, along with others we haven't identified yet. The corona is a complex, dynamic environment, and untangling the physics requires detailed observations and sophisticated models. The Parker Solar Probe, flying through the corona, is gathering data that's helping us refine our understanding. But the fundamental mystery remains. Why is the corona so hot when it's so far from the source of the sun's energy? The corona is normally invisible from Earth because it's so much dimmer than the photosphere. The only time we can see it is during a total solar eclipse, when the moon blocks the sun's bright disk and reveals the faint, ethereal glow of the corona extending outward in streamers and loops. For a few minutes, the sun's outer atmosphere becomes visible, a ghostly halo surrounding the darkened sun, beautiful and mysterious. The corona is where the solar wind originates. The heat in the corona gives particles enough energy to escape the sun's gravity entirely, streaming outward as a constant flow of charged particles. This wind fills the solar system, shaping planetary magnetospheres, creating auroras, carrying the sun's influence far beyond the orbit of Pluto. The corona's heat, paradoxical and puzzling, powers the solar wind, connects the sun to the rest of the solar system, and reminds us that even after centuries of studying our nearest star, it still holds surprises. Titan is the only place in the solar system, other than Earth, with stable liquid on its surface. Not water, it's far too cold for that. Titan's surface temperature is around 180 degrees Celsius, cold enough that water ice is as hard as rock. But methane and ethane remain liquid at these temperatures, and Titan's surface is covered with lakes, seas, and rivers of liquid hydrocarbons. The largest of these liquid bodies is Kraken Mare, a sea of methane near Titan's North Pole. It's larger than the Caspian Sea on Earth, covering about 400,000 square kilometers. There are other seas, Ligeia Mare, Punga Mare, and hundreds of smaller lakes scattered across the polar regions. Radar images from the Cassini spacecraft show these lakes with remarkable clarity, smooth, dark patches indicating liquid, surrounded by shorelines and occasionally connected by channels where rivers flow. These rivers carve valleys into Titan's icy terrain. Rain, methane rain, falls from Titan's thick, nitrogen-rich atmosphere, collects in streams, and flows downhill toward the lakes and seas. The hydrological cycle on Titan mirrors Earth's water cycle, but with methane instead of water. Liquid evaporates from the surface, condenses into clouds, falls as rain, runs off in rivers, and collects in lakes. It's an alien world, but with weather and geography that feel strangely familiar. Titan's atmosphere is thick, thicker than Earth's, with a surface pressure about 1.5 times ours. It's mostly nitrogen, like Earth's, but with methane mixed in. The methane is constantly being broken down by sunlight, so there must be some process replenishing it. Perhaps cryovolcanism, where water ammonia slushes erupt from the interior, carrying dissolved methane. Or perhaps there are subsurface reservoirs of methane slowly leaking to the surface. The Huygens probe, which landed on Titan in 2005, recorded sounds during its descent: the whistle of wind, the rustling of methane rain. It saw pebbles on the surface rounded by erosion, made of water ice as hard as rock. It smelled organic molecules in the atmosphere, compounds rich in carbon and nitrogen, the building blocks of life, though not life itself. Titan is one of the most Earth-like worlds we've found, despite being so cold and alien. It has weather, seasons, erosion, sedimentary processes. It has seas you could sail on, though they'd be cold and toxic, and the boat would need to be designed carefully because liquid methane is much less dense than water. It has rain, though the drops would fall gently through the thick atmosphere, taking minutes to reach the ground. Some scientists speculate that Titan might host life, not life as we know it, but something adapted to liquid methane, using methane as a solvent the way Earth life uses water. It's speculative, exotic, probably unlikely, but Titan is strange enough that we can't entirely rule it out. And even if Titan is lifeless, it's a laboratory for understanding planetary chemistry, organic synthesis, and the complex interplay between surfaces, atmospheres, and liquids. Titan is a world worth returning to, worth studying, worth dreaming about. The sun is constantly shedding material, not dramatically, not violently like a supernova, but steadily, relentlessly. Charged particles, mostly protons and electrons, stream outward from the sun's corona at speeds of 300 to 800 kilometers per second. This flow is called the solar wind, and it doesn't stop at the planets. It continues outward, beyond Neptune, beyond Pluto, far into the outer solar system. The solar wind carries the sun's magnetic field with it, embedded in the flow of particles. And this creates a structure called the heliosphere, a vast bubble of solar influence surrounding the sun and all the planets. The heliosphere extends roughly 120 astronomical units from the sun, about 3 times the distance to Pluto. At that point, the solar wind runs into the interstellar medium, the gas and dust between stars, and slows down, creating a boundary called the heliopause. The heliopause is where the solar system, in a sense, ends. Inside the heliopause, the sun's magnetic field dominates. Outside, the magnetic fields of the galaxy take over. It's a transition from the sun's domain to the broader interstellar environment. Only 2 human-made objects have crossed the heliopause, Voyager 1 and Voyager 2. Voyager 1 crossed in 2012, Voyager 2 in 2018. Both spacecraft reported a sudden change in their environment. The solar wind disappeared, replaced by the denser, cooler plasma of interstellar space. Cosmic rays, high-energy particles from outside the solar system, increased dramatically. The sun's influence faded, and the galaxy's influence grew stronger. The heliosphere protects us. Cosmic rays, particles accelerated by supernova, pulsars, and other violent cosmic phenomena, are harmful, especially to biological organisms. They can damage DNA, cause cancer, degrade electronics. The heliosphere deflects many of these cosmic rays, reducing the radiation dose we receive. It's not perfect protection, but it helps. The shape of the heliosphere is still debated. Early models depicted it as a comet-like structure with a long tail pointing away from the sun's motion through the galaxy. But recent data from Voyager and other spacecraft suggest it might be more rounded, perhaps even split into multiple lobes. The exact shape depends on the interaction between the solar wind and the interstellar medium, and we're still gathering the data needed to understand it fully. The heliosphere is a reminder that the solar system isn't an isolated island. It's embedded in a galaxy, constantly interacting with the interstellar medium, buffeted by cosmic rays, influenced by magnetic fields from nearby stars. The sun creates a protective bubble, but that bubble has limits. Beyond the heliopause, the solar system fades into the interstellar void, and the influence of distant stars and the galaxy itself takes over. If Earth seems geologically active, with its earthquakes and volcanoes and shifting continents, then Io is a revelation. Io, a moon of Jupiter slightly larger than our own moon, is the most volcanically active body in the entire solar system. Hundreds of volcanoes dot its surface, many of them erupting at any given time, spewing lava and sulfur compounds into space. Io's surface is constantly being resurfaced. Impact craters, which mark the surfaces of most moons and planets, are almost entirely absent on Io. They're buried, covered by lava flows before they can accumulate. The oldest features on Io's surface are perhaps only a few million years old, a blink of an eye, geologically. The entire moon is young, perpetually renewed by volcanic activity. The volcanoes themselves are spectacular. Some erupt explosively, sending plumes of sulfur dioxide hundreds of kilometers above the surface. Others produce vast lava flows, rivers of molten rock that can travel hundreds of kilometers before cooling. The largest volcano, Loki Patera, is a lava lake about 200 kilometers across, constantly churning, releasing more heat than all of Earth's volcanoes combined. What powers this activity? Tidal heating. Io orbits Jupiter at a distance of only 422 kilometers, closer than our moon orbits Earth, but around a planet far more massive. Jupiter's gravity pulls on Io strongly, but that pull isn't constant. Io is in orbital resonance with Europa and Ganymede, which means their gravitational tugs combine in complex ways, making Io's orbit slightly elliptical. As Io moves closer to and farther from Jupiter, the tidal forces change. Jupiter's gravity stretches and squeezes Io rhythmically, flexing the moon's interior. This flexing generates heat through friction, the same way bending a wire back and forth makes it warm. The heat is enormous, enough to melt rock, to power hundreds of volcanoes, to keep Io's interior molten. Io is essentially being kneaded by Jupiter's gravity, like dough, and the friction from that kneading keeps the moon perpetually hot. The surface of Io is bizarrely colorful: yellows, oranges, reds, blacks, whites, a palette created by sulfur and sulfur dioxide in various forms. Fresh sulfur is yellow. Older sulfur, altered by radiation and heat, turns orange and red. Sulfur dioxide frost is white. Dark patches might be silicate lava, rock melted and erupted. The whole moon looks like an abstract painting, a riot of color unlike any other world. Io is hostile. The radiation from Jupiter is intense, deadly. The volcanic activity is relentless. There's no atmosphere to speak of, just a thin veil of sulfur dioxide that collapses and reforms as volcanoes erupt. But Io is also fascinating, a world where geology happens fast, where you can watch mountains being built and valleys being filled in real time, cosmically speaking. It's a reminder that not all moons are dead, that tidal forces can keep worlds active for billions of years, and that the solar system contains extremes we're only beginning to appreciate. Saturn is famous for its rings, but there's another remarkable fact about this giant planet. It's less dense than water. Saturn's average density is about 0.687 grams per cubic centimeter, while water has a density of 1.0 g cm3. This means that if you could somehow find a bathtub large enough, an ocean really, vast beyond imagining, Saturn would float. This low density tells us something about Saturn's composition. It's made mostly of hydrogen and helium, the lightest elements, with just a small rocky core buried deep inside. These gases are not very dense, especially under the relatively low pressures in Saturn's outer layers. Jupiter is also made mostly of hydrogen and helium, but Jupiter is more massive, so its gravity compresses the material more, making it denser overall. Saturn, being less massive, compresses its material less, and so it remains fluffy, low density, light enough to float. Of course, this is purely hypothetical. There's no bathtub, no ocean, no body of water large enough to hold Saturn. And even if there were, Saturn wouldn't maintain its shape. It's held together by its own gravity, and placing it in water would create bizarre, impossible scenarios involving pressure, buoyancy, and gravitational interactions that defy easy visualization. But the thought experiment is delightful. Saturn, the ringed giant, bobbing gently on the surface of an impossibly vast cosmic ocean. Saturn's low density also affects its structure. The transition from gaseous outer layers to liquid hydrogen in the interior is gradual, not sharp. There's no solid surface to land on. If you tried to descend into Saturn, you'd pass through layers of increasingly dense gas, then into liquid hydrogen, then perhaps into a layer of metallic hydrogen, where pressure is so high that hydrogen conducts electricity like a metal, and finally, maybe, to a small rocky core. But there's no distinct boundary, no place where you'd suddenly feel solid ground beneath you. Saturn is a planet of gradations, of slow transitions, a world without surfaces. The image of Saturn floating is whimsical, playful, almost cartoonish, but it speaks to the diversity of planets, to the range of compositions and densities that exist in the solar system. Saturn is a giant, but it's also, in a sense, light, airy, barely more substantial than the hydrogen and helium that fill it. It's a world that challenges our expectations, that reminds us not to assume all planets are dense, rocky, Earth-like. Some are gas and vapor, held together by gravity, so insubstantial they'd float if you could put them in water. Mercury is the closest planet to the Sun, enduring scorching temperatures that can reach 430 degrees Celsius during the day. You'd expect it to be bone dry, any water long since evaporated, or broken down by intense solar radiation. But Mercury holds a secret. It has water ice, hidden in craters at its poles. How is this possible? The answer lies in geometry and shadow. Mercury's axis is almost perfectly upright, tilted less than 1 degree. This means that at the poles, some crater floors never see sunlight, ever. They're in permanent shadow, cold traps where temperatures can plummet to 200 degrees Celsius or lower. And in these shadowed regions, water ice can exist, stable for billions of years. Radar observations from Earth and later measurements from the Messenger spacecraft confirmed the presence of ice in these craters. The ice is mostly pure water, though some regions have a darker material on top, perhaps organic compounds delivered by comets or asteroids. The ice likely came from the same sources. Impacts from comets or water-rich asteroids delivering water to Mercury over its history. Most of that water was lost immediately, vaporized by the heat, but the tiny fraction that landed in the polar craters survived, trapped in eternal darkness. So Mercury, the planet closest to the Sun, has some of the coldest places in the solar system. It's a world of extremes, where day and night differ by over 600 degrees, where the sunlit side bakes and the shadowed craters freeze. It's a reminder that location matters, that microclimates can exist even on worlds without atmospheres, and that water, precious, essential water, finds a way to persist in the most unexpected places. Mercury's ice is scientifically valuable. It's a record of ancient impacts, a reservoir of water that's been preserved for eons. Future missions to Mercury might investigate this ice, study its composition, perhaps even extract it for use by robotic explorers, or one day, human outposts. Mercury seems inhospitable, but in its shadowed craters it hides resources, waiting quietly in the dark, untouched by the fierce sunlight that dominates the rest of the planet. When Voyager 2 flew past Neptune in 1989, it photographed a large, dark oval storm in the planet's southern hemisphere. This storm, dubbed the Great Dark Spot, was roughly the size of Earth, similar in many ways to Jupiter's Great Red Spot. It rotated counterclockwise, pushed by winds exceeding 2,000 kilometers per hour. the fastest winds measured on any planet in the solar system. The storm seemed like a permanent feature, a Neptunian counterpart to Jupiter's centuries-old storm. But when the Hubble Space Telescope observed Neptune in 1994, just 5 years later, the great dark spot was gone, vanished. In its place, a new dark spot had appeared in the northern hemisphere. Neptune's storms, unlike Jupiter's, are transient. They form, rage for a few years, and then dissipate, replaced by new storms elsewhere. Why the difference? Neptune is smaller and colder than Jupiter, and its atmosphere behaves differently. Neptune's internal heat, like Jupiter, Neptune emits more energy than it receives from the Sun, drives convection and atmospheric dynamics. But the details differ. Neptune's atmosphere is more active vertically, with stronger convection cells that might disrupt long-lived storms. Or perhaps Neptune's rotation and atmospheric structure don't support the kind of stable vortices that last for centuries. Whatever the reason, Neptune's storms come and go, ephemeral features in a dynamic, ever-changing atmosphere. This tells us that planetary atmospheres are complex, that small differences in size, composition, internal heat, and rotation can lead to vastly different weather patterns. Jupiter's Great Red Spot has lasted for centuries, possibly millennia. Neptune's storms last a handful of years. Both are giant planets, both are gas giants, but their storms behave completely differently. Neptune remains mysterious. It's so far from Earth, so dim, that detailed observations are difficult. Voyager 2 remains the only spacecraft to visit. What we know comes from that brief flyby and from Hubble observations. We've seen dark spots appear and vanish. We've measured wind speeds. We've detected methane clouds and high-altitude hazes. But Neptune's atmosphere, its interior, its magnetic field, all remain poorly understood, awaiting future missions to explore. For now, Neptune is a distant blue enigma, a world of fleeting storms and furious winds, a place where weather changes on timescales short enough that we can watch it happen, if only we look closely enough. On Earth, dust devils are common in desert regions, small whirlwinds that pick up sand and dust, creating spinning columns that might reach a few 100 meters high. They're minor phenomena, interesting to watch, but not particularly threatening. On Mars, dust devils are giants. Martian dust devils can tower 8 kilometers into the thin atmosphere, 8,000 meters, taller than Mount Everest. They're visible from orbit, casting shadows on the surface, leaving tracks that persist for days or weeks. Rovers on Mars have photographed them directly, watched them approach and pass by, measured the pressure drops as they sweep overhead. Why so tall? Mars's atmosphere is thin, less than 1% the pressure of Earth's, which means there's less atmospheric mass to push against vertical motion. On Earth, dense air resists upward flow, limiting how high a dust devil can grow. On Mars, the thin atmosphere offers less resistance, so convection cells can extend much higher before dissipating. The dust devils form through the same basic process as on Earth. Sunlight heats the ground unevenly, creating temperature differences. Warm air rises, cooler air rushes in to replace it, and rotation develops through conservation of angular momentum or interaction with local terrain. The result is a spinning column of air that picks up dust and becomes visible. These dust devils play an important role in Mars's climate. They loft dust high into the atmosphere, where it can be carried by winds across the planet. Sometimes, dust devils merge or amplify into larger storms. Occasionally, these storms grow into global dust events, planet-wide storms that obscure the entire surface for weeks or months. The 2018 dust storm, which ended the Opportunity rover's mission, began as regional dust activity that escalated dramatically. Dust devils also clean solar panels. The Spirit and Opportunity rovers, designed to last 90 days, survived for years, partly because dust devils occasionally swept past and blew accumulated dust off their solar panels, restoring power. It's an ironic twist. The same dusty environment that threatens the rovers also occasionally saves them, cleaning their panels in random, unpredictable acts of Martian housekeeping. Watching videos of Martian dust devils, silent towering columns moving across rust-colored plains, is mesmerizing. They're alien yet familiar. Earth has dust devils. Mars has dust devils. The physics is the same, but the scale, the environment, the context are all different. It's a reminder that atmospheric phenomena are universal, that convection and rotation create similar structures on different worlds, adapted to local conditions. Europa's surface is strange and beautiful. It's young, almost no impact craters, indicating the surface is constantly being renewed. It's smooth, covered in water ice, but not featureless. Dark streaks, called lineae, crisscross the surface in complex intersecting patterns. Ridges rise hundreds of meters high, running for hundreds of kilometers. There are chaotic terrains, regions where the ice seems to have broken apart, jumbled, and refrozen in disordered patterns. All of this suggests activity. The ice shell is fracturing, flexing, responding to stresses. Those stresses come from tidal forces, Jupiter's gravity pulling on Europa, stretching and compressing it as the moon orbits. The ice shell, perhaps 10 to 30 kilometers thick, floats on a global ocean beneath. As tides flex Europa, the ice cracks. Water or slush from below might seep into the cracks, freeze, and create ridges. Or maybe the ice moves, plates shifting like a miniature version of plate tectonics, though driven by tidal forces rather than mantle convection. The dark streaks might be salts or minerals from the subsurface ocean, carried upward in liquid that erupts or seeps through cracks. Or they might be organic compounds, darkened by radiation. Europa sits within Jupiter's intense radiation belts, and the surface is constantly bombarded by high-energy particles that break apart molecules, alter chemistry, darken ices. The surface we see is processed, irradiated, chemically transformed from whatever originally existed there. Beneath this dynamic ice shell lies the ocean, liquid water, probably in contact with the rocky seafloor. That contact is crucial because it means there could be hydrothermal vents, places where mineral-rich water, heated by the moon's interior, erupts into the ocean. On Earth, hydrothermal vents host thriving ecosystems, communities of organisms that live off chemical energy rather than sunlight. Europa's ocean might have the same. It's speculation, but informed speculation, based on what we know about tidal heating, ocean chemistry, and the basic requirements for life. The surface of Europa is essentially a window, or rather, a barrier between us and that ocean. It's tantalizing. We know there's an ocean below, and we can see hints of it in the surface features, but we can't reach it directly. Future missions aim to change that. NASA's Europa Clipper and ESA's JUICE mission will study Europa in detail, mapping the ice shell, analyzing surface composition, measuring the thickness of the ice, searching for plumes of water vapor erupting from the surface. If plumes exist, and there's some evidence they do, though it's not definitive. They would be like Enceladus's geysers, offering a free sample of the ocean without needing to drill through kilometers of ice. Europa is one of the best places to search for life beyond Earth, and its fractured, dynamic surface is our first clue that something interesting is happening below. At Earth's distance, sunlight takes 8 minutes and 20 seconds to arrive. The sun is bright, warm, the center of our sky. But move outward, beyond Mars, beyond Jupiter, beyond Saturn, Uranus, Neptune, out to Pluto at the edge of the Kuiper Belt, and everything changes. Pluto orbits at an average distance of about 40 astronomical units from the Sun, 40 times Earth's distance. Light, traveling at its constant maximum speed, takes over 5 hours to cross that gulf. 5 hours. When you see the Sun from Pluto, you're seeing it as it was 5 hours ago, as it was in the morning if you're observing in the afternoon. But more importantly, the Sun from Pluto doesn't look like the Sun from Earth. It's not a large disk dominating the sky. It's a point of light, brighter than any star, but still just a point. The Sun's apparent size from Pluto is less than 1 arcminute, smaller than Venus appears from Earth. It looks like a brilliant star, the brightest object in the sky by far, but still a star, not a sun. And the illumination. At noon on Pluto, when the Sun is directly overhead, the lighting is roughly equivalent to twilight on Earth, about 15 minutes after sunset or before sunrise. It's dim. You could see well enough to navigate, to read, maybe, but it's not bright. The sky wouldn't be blue. Pluto's thin atmosphere, when it exists, creates a hazy glow, but nothing like Earth's vibrant sky. Mostly, you'd see stars. During Pluto's day, stars would be visible, the Milky Way arcing overhead, because the Sun simply doesn't provide enough light to wash them out. This dimness affects everything. Pluto is cold, about 230 degrees Celsius, because it receives so little solar energy. The sunlight that does arrive is weak, insufficient to melt ice, barely enough to sublime nitrogen frost into a thin atmosphere during Pluto's brief summer. Pluto's year is 248 Earth years, and for much of that time, its atmosphere freezes onto the surface entirely, collapsing as Pluto moves farther from the Sun in its elliptical orbit. Living on Pluto would mean living in perpetual twilight. The Sun would rise and set. Pluto's day is 6.4 Earth days, but day and night wouldn't differ dramatically. The Sun would be a bright point, moving slowly across the star-filled sky, casting sharp shadows but little warmth. It would be beautiful in a cold, alien way, but it would also be a stark reminder of distance, of how far you'd traveled from the warmth and light of the inner solar system. Pluto is a frontier, a world at the edge, where the Sun's influence fades and the cold darkness of interstellar space begins to creep in. Most large moons in the solar system orbit in the same direction their planet rotates. This makes sense. They formed from the same disk of material that surrounded the planet during its formation, and that disk inherited the planet's rotational direction. But Triton is different. Triton orbits Neptune backwards in what's called a retrograde orbit, moving opposite to Neptune's rotation. This tells us immediately that Triton didn't form alongside Neptune. It's a captured object, something that originated elsewhere, probably in the Kuiper Belt, and was captured by Neptune's gravity at some point in the past. The capture process would have been violent, chaotic. Triton's orbit would initially have been highly elliptical, carrying it close to Neptune and then far away. Over time, tidal forces circularized the orbit, but they couldn't change its direction. Triton remains retrograde, a permanent marker of its foreign origin. Triton is geologically active, which is surprising for a moon so far from the Sun. Voyager 2, during its 1989 flyby, photographed geysers erupting on Triton's surface, plumes of nitrogen gas and ice shooting 8 kilometers into the thin atmosphere. The moon's surface is young, with few craters, indicating ongoing resurfacing. There are strange terrains, Cantaloupe Terrain, named for its dimpled, textured appearance, and cryovolcanic features suggesting that water ammonia slushes have erupted from the interior. The activity is powered by tidal heating, though Triton's orbit is now circular, so the tidal forces are weak. Perhaps the heating is left over from when Triton's orbit was more eccentric, energy stored in the interior that's still slowly being released. Or perhaps there's some internal heat from radioactive decay, or from chemical reactions, or from phase changes in exotic ices deep below. Triton's retrograde orbit has another consequence. It's spiraling inward. Tidal interactions between Triton and Neptune are gradually draining energy from Triton's orbit, causing it to decay. Slowly, over millions of years, Triton is getting closer to Neptune. In about 3.6 billion years, Triton will cross Neptune's Roche limit, the distance within which tidal forces become strong enough to tear an object apart. Triton will be shredded, its material spreading out into a ring system around Neptune. So Neptune will gain spectacular rings, possibly more impressive than Saturn's current rings. But that's far in the future. For now, Triton orbits backwards, a captured interloper slowly spiraling toward its doom. Geologically active, mysterious, one of the most intriguing moons in the solar system. Every retrograde orbit tells a story of capture, of violence, of a moon that doesn't belong but found itself trapped by gravity nonetheless. Most asteroids are rock or a mixture of rock and ice. But Psyche, a large asteroid in the main belt, is different. Radar observations and spectroscopic measurements suggest Psyche is made mostly of metal, iron and nickel, the same materials that make up planetary cores. This makes Psyche incredibly unusual. How does a metallic asteroid form? The most likely explanation is that Psyche is the exposed core of a protoplanet, a planetary embryo that was building itself during the early solar system, but never completed the process. This protoplanet differentiated. Heavier metals sank to the center, forming a core, while lighter rocky materials formed a mantle around it. Then something catastrophic happened. A series of collisions stripped away the rocky mantle, leaving only the metal core exposed. If this is true, Psyche is a rare opportunity. We've never seen a planetary core directly. On Earth, the core is buried beneath 2,900 kilometers of mantle and crust, completely inaccessible. But Psyche offers a shortcut, a core that's been excavated for us by cosmic violence, now floating in space, available for study. NASA is sending a mission to Psyche, appropriately named the Psyche mission, scheduled to arrive in 2029. The spacecraft will orbit the asteroid, map its surface, measure its composition, study its magnetic field, if it has one, and try to determine whether it's truly a core or perhaps something else, a chunk of metal that formed differently, or a more complex mixture of materials than we expect. Visiting Psyche will help us understand planetary formation, differentiation, and the violent collisions that shaped the early solar system. It will give us insights into Earth's core, which we can model but never directly observe. And it might answer questions about how metal-rich bodies form, how impacts strip away layers, and what the interiors of planets look like. Psyche is also valuable in a more practical sense. It's made of metal, iron, and nickel, possibly platinum group metals, materials that are expensive and useful. Some people have speculated about mining asteroids like Psyche, extracting their metals for use in space construction, or even bringing them back to Earth. The total value of Psyche's metal, if you could somehow extract and sell it, has been estimated in the trillions or even quadrillions of dollars, though such estimates are mostly meaningless. Flooding the market with that much metal would crash prices instantly. For now, Psyche remains a scientific curiosity, a window into planetary interiors, a core without a planet, floating through the asteroid belt, waiting for us to arrive and study it. The Sun is 400 times larger than the Moon. It's vastly, incomprehensibly bigger, 1.4 million kilometers in diameter versus the Moon's 3,474 kilometers. And yet, from Earth's surface, they appear almost exactly the same size in the sky. This remarkable coincidence is what makes total solar eclipses possible. The reason for the apparent size match is distance. The Sun is also about 400 times farther away than the Moon. These two ratios, size and distance, almost perfectly cancel out, making the Sun and Moon appear nearly identical in angular size, each about half a degree across. This allows the Moon, during a total solar eclipse, to precisely cover the Sun's disk. Not too small, which would leave a bright ring of sunlight around the Moon. Not too large, which would block the Sun entirely without revealing the corona. The Moon's apparent size is just right to cover the Sun's bright photosphere while leaving the faint corona visible, a ghostly halo extending around the darkened Sun, visible only during totality, but this won't last forever. The Moon is slowly moving away from Earth, drifting outward at about 3.8 centimeters per year due to tidal interactions. Over millions of years, the Moon's apparent size will shrink. Eventually, the Moon will be too small to completely cover the Sun. There will be no more total solar eclipses, only annular eclipses, where the Moon passes in front of the Sun but leaves a bright ring visible around its edge. We live in a special time. For most of Earth's history, the Moon was closer, and total eclipses lasted longer because the Moon appeared larger. In the future, the Moon will be farther, and total eclipses will no longer occur. Right now, in this brief window of geological time, the size match is nearly perfect. Eclipses have been scientifically valuable. Observations during the 1919 total solar eclipse provided evidence for Einstein's theory of general relativity by showing that the Sun's gravity bends light from distant stars. Eclipses allow astronomers to study the Sun's corona without specialized instruments, observing its structure, temperature, and dynamics. They've inspired awe and fear throughout human history, marking calendars, influencing cultures, occasionally changing the course of battles and politics. There's something poetic about the coincidence. The Sun and Moon, so different in size, align perfectly by distance to create one of nature's most spectacular phenomena. It's not meaningful in a cosmic sense. The universe doesn't care about coincidences. But for us, watching from Earth's surface, it's a gift. A brief alignment that produces moments of totality. When day becomes night, stars appear, the temperature drops, and the sun's hidden atmosphere reveals itself in a glowing crown around the darkened moon. Ganymede is the largest moon in the solar system, larger than Mercury, larger than Pluto, but it's still a moon, orbiting Jupiter rather than the sun. And uniquely among moons, Ganymede has its own magnetic field. Most moons don't generate magnetic fields. They're too small, or their cores have cooled and solidified, or they lack the internal dynamo processes that create fields. But Ganymede is different. It has a liquid iron core that's still convecting, generating a magnetic field through the same dynamo process that creates Earth's field. Ganymede's magnetic field is weak compared to Earth's, about 1% as strong, but it's enough to create a miniature magnetosphere around the moon. This magnetosphere interacts with Jupiter's much larger magnetosphere, creating complex structures, magnetic field lines that connect Ganymede to Jupiter, auroras at Ganymede's poles, where charged particles spiral down field lines, regions where Ganymede's field carves out a bubble of protection within Jupiter's radiation belts. This magnetic field has implications. It means Ganymede's interior is still active, still warm enough to keep part of the core liquid and convecting. It also provides some protection from Jupiter's intense radiation. Though not complete protection, Ganymede still receives a significant radiation dose, enough to be harmful to unprotected organisms or electronics. Ganymede's surface reflects its complexity. There are two main terrain types: dark, ancient, heavily cratered regions, and lighter, younger grooved terrain where tectonic activity has resurfaced the ice. These grooved terrains suggest that Ganymede once had, or perhaps still has, some form of cryovolcanism or tectonic activity driven by internal heat. Beneath the surface lies an ocean. Like Europa and several other large moons, Ganymede probably has a layer of liquid water sandwiched between layers of ice. This ocean is buried deep, perhaps 150 kilometers beneath the surface, so it's isolated, unlikely to interact with the surface or with us anytime soon. But it exists, adding Ganymede to the growing list of ocean worlds in the solar system. Ganymede is a world of layers: an iron core, a rocky mantle, a deep ocean, a thick ice shell, a complex surface. It has its own magnetic field, its own atmosphere, thin but detectable, its own auroras. In many ways, Ganymede is planet-like, caught between being a moon and being something more. If it orbited the sun instead of Jupiter, we might classify it as a planet. But it orbits Jupiter, so it remains a moon, the largest and perhaps most complex moon in the solar system. When we think of asteroids, we usually imagine solitary rocks tumbling through space. But many asteroids have companions. About 15% of near-Earth asteroids are binary systems, two objects orbiting each other, bound by their mutual gravity, traveling together through the solar system. These binary asteroids come in various configurations. Some have a large primary and a much smaller secondary, a moon orbiting the larger asteroid. Others are more evenly matched, with similar-sized objects orbiting their mutual center of gravity, creating a true binary system. A few asteroids even have multiple companions, triple systems where three objects orbit each other in complex, intertwined dances. How do these binaries form? Several mechanisms have been proposed. Some might form from collisions, where an impact breaks a larger asteroid into pieces that remain gravitationally bound. Others might form through the Yorp effect, a subtle process where sunlight, absorbed and re-radiated unevenly, creates a torque that spins an asteroid faster over time. If the spin becomes fast enough, the asteroid can fission, splitting into two pieces that orbit each other. The asteroid Didymos, target of NASA's DART mission in 2022, is a binary system. Didymos is the larger object, about 780 meters across, with a smaller moonlet called Dimorphos orbiting it, about 160 meters across. DART deliberately crashed into Dimorphos to test whether a kinetic impact could alter an asteroid's orbit, a technique that might one day be used to deflect a potentially hazardous asteroid heading for Earth. The impact worked, changing Dimorphos's orbital period by about 33 minutes, proving that we can move asteroids if necessary. Binary asteroids are scientifically valuable because their mutual orbits allow us to measure their masses. By observing how they orbit each other, we can apply Kepler's laws and determine the system's total mass, and from that, estimate density and internal structure. This helps us understand what asteroids are made of: solid rock, rubble piles loosely held together by gravity, or something in between. Some binary asteroids are contact binaries, two objects that touch, creating a dumbbell or peanut shape. The asteroid Arrokoth, visited by New Horizons in 2019, is a contact binary formed from a gentle collision between two objects in the early solar system. They touched and stuck together, creating the bilobed shape we see today. Binary asteroids remind us that even small objects have complex relationships. Gravity binds things together at all scales, from planets and moons to tiny rocks in space, creating systems within systems, orbits within orbits, a hierarchy of gravitational connections that extends throughout the solar system. Venus's atmosphere is not just hot and toxic, it's also crushingly dense. The atmospheric pressure at Venus's surface is about 92 bar, 92 times the pressure at Earth's sea level. If you were somehow standing on Venus's surface, the pressure would be equivalent to being 900 meters underwater in Earth's oceans, deep below the surface, in a realm where only specialized submarines can survive. This pressure is intense enough to affect materials in strange ways. Lead would be soft and pliable. The distinction between gas and liquid becomes blurred. The lower atmosphere is so dense and hot that carbon dioxide is in a supercritical state, behaving like both a gas and a liquid simultaneously. The atmosphere flows more like a fluid than a gas, creating strange convective patterns and weather systems. This crushing pressure, combined with temperatures around 465 degrees Celsius, makes Venus's surface one of the most hostile environments in the solar system. Soviet Venera landers, designed with incredible robustness, survived on the surface for only a few hours at most. The longest-lasting Venera 13 functioned for 127 minutes before succumbing to the heat and pressure. The landers transmitted images, measured atmospheric composition, analyzed surface rocks, and then fell silent. Their electronics cooked, their structures slowly crushed. The density of the atmosphere also affects how Venus looks from the surface. The air is so thick that it scatters light in unusual ways, creating a diffuse, orange-tinged illumination with no direct sunlight visible. The sun would be completely obscured by the thick cloud layers overhead. Visibility would be reasonable horizontally, perhaps several kilometers, but everything would have an eerie, uniform glow, like being underwater on a cloudy day, but with an orange filter. Sound would travel differently, too. The dense atmosphere conducts sound efficiently, but the high temperature and pressure alter acoustic properties. Your voice would sound deeper, distorted, And the wind, if you could hear it, would be relatively gentle at the surface, despite the extreme conditions aloft. Surface winds on Venus are only a few kilometers per hour, sluggish because the dense atmosphere resists motion. But even slow winds at such high density carry significant force. Venus's crushing atmosphere is a result of a runaway greenhouse effect. Water vapor and carbon dioxide accumulated, trapping heat, raising temperatures, which released more carbon dioxide from surface rocks, trapping more heat, in a feedback loop that spiraled out of control. The result is an atmosphere that's almost entirely carbon dioxide, 96.5%, so thick it presses down on the surface with the weight of a deep ocean. Venus is a warning. It shows what happens when greenhouse effects run unchecked, when atmospheres thicken and trap heat until temperatures soar and pressures become unbearable. It's a vision of planetary death, not from cold and emptiness, but from heat and pressure, from an atmosphere that becomes a prison rather than a shield. We've mentioned this fact before, but it's worth dwelling on because it reveals something profound about relationships between worlds. Pluto and Charon don't behave like a typical planet and moon. They're partners, locked together, orbiting a point between them. Charon is about half the diameter of Pluto, unusually large for a moon. Most moons are tiny compared to their planets. Our moon is about 1/4 Earth's diameter, and that's already considered large. But Charon is proportionally much bigger, containing about 1/8 of Pluto's mass. This massive moon pulls on Pluto significantly, and the result is that the barycenter, the center of mass of the system, lies outside Pluto's physical body, in the space between the two worlds. Technically, this makes Pluto and Charon a binary dwarf planet system rather than a planet with a moon. They orbit each other, both moving around their mutual center of gravity. Pluto traces a larger orbit, Charon a smaller one, but both are moving, both are orbiting. They're also tidally locked to each other. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. If you stood on Pluto's Charon-facing hemisphere, Charon would hang motionless in the sky, never rising or setting, always in the same position. And from Charon, Pluto would do the same, a constant companion, fixed in the sky. This tidal lock means their rotation periods match their orbital period, 6.4 Earth days. Pluto rotates once every 6.4 days, Charon orbits Pluto once every 6.4 days, and both keep the same faces pointed toward each other. They're dancing together, perfectly synchronized, locked in an embrace that will last billions of years. There's something romantic about this, if you can apply such a word to celestial bodies. Two worlds, alone at the edge of the solar system, bound together by gravity, each always facing the other, spinning in synchrony. They'll never drift apart. They'll never look away. For as long as the solar system exists, Pluto and Charon will be together, orbiting their mutual center, two small worlds against the darkness, holding on to each other. For centuries, we've observed Jupiter's equatorial bands and zones, the swirling clouds that stripe the planet from side to side. But Jupiter's poles remained mysterious, hidden from view, because we'd only observed Jupiter from roughly the plane of its equator. Then Juno arrived, a spacecraft in a polar orbit that flies over Jupiter's poles repeatedly, and it revealed something no one expected. Jupiter's poles are covered in enormous cyclones, storms larger than Earth, arranged in precise geometric patterns. At the North Pole, There's a central cyclone surrounded by 8 others, forming an octagonal ring. At the South Pole, a central cyclone is surrounded by 5 others, forming a pentagon. These patterns are stable. They've persisted for years, possibly much longer, each cyclone maintaining its position, spinning in place while the pattern as a whole remains fixed. Why do these geometric arrangements exist? No one knows for certain. On Earth, polar cyclones tend to be singular. One large storm at each pole, like hurricanes but sustained by different mechanisms. But Jupiter has multiple cyclones at each pole, packed together, each one about the size of Earth or larger. And they're arranged in these strangely regular patterns. The cyclones don't merge. You'd expect them to collide, to combine into larger storms, but they don't. Something stabilizes them, keeps them separate. Perhaps it's the rotation of Jupiter, creating forces that prevent merging. Perhaps it's the dynamics of the jet streams that encircle them. Or perhaps there's some resonance, some mathematical relationship between their sizes, speeds, and positions that locks them into these configurations. Juno's images of the poles are stunning. Each cyclone is a swirling vortex of clouds, reds and whites and browns, spiraling inward toward a center. Together, they create patterns that look almost designed, almost intentional, like flowers or mandalas. But they're natural, emergent from the physics of fluid dynamics and planetary rotation, patterns that Jupiter has created without intention, without awareness, simply by being what it is. Jupiter's polar cyclones are a reminder that planets can surprise us. We thought we understood Jupiter. We'd been observing it for centuries, sent multiple spacecraft past it. But until Juno, we'd never seen the poles clearly, and when we finally did, we found complexity we didn't anticipate, beauty we didn't expect, geometric arrangements that challenge our models and invite new questions. The universe doesn't run out of mysteries. We answer one question, and 3 more appear. Jupiter's poles, now visible, now mapped, remain puzzling. The cyclones are there, arranged in their polygons, spinning steadily, and we're still working to understand why. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2. Their primary mission was to explore the outer planets, Jupiter, Saturn, and for Voyager 2, Uranus and Neptune. This was possible because of a rare alignment of the outer planets that occurs only once every 176 years, allowing a spacecraft to use gravity assists to visit multiple planets in a single mission. The Voyagers succeeded spectacularly. They sent back the first close-up images of Jupiter's Great Red Spot, discovered active volcanoes on Io, revealed the complexity of Saturn's rings, showed us Uranus tilted on its side, and photographed Neptune's Great Dark Spot. They transformed our understanding of the outer solar system, turning distant points of light into real, complex worlds. But the Voyagers didn't stop. After completing their planetary tours, they continued outward, powered by radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity. Slowly, steadily, they climbed out of the solar system, heading for the edge. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind stops and interstellar space begins. Voyager 2 followed in 2018. Both spacecraft reported the same thing. The solar wind disappeared, replaced by the denser, cooler plasma of the interstellar medium. Cosmic rays increased. The environment changed fundamentally. They had left the Sun's domain and entered the space between stars. The Voyagers are now in interstellar space, but they're still technically within the solar system. The Sun's gravitational influence extends much farther, out to the Oort cloud, perhaps 100,000 astronomical units away. The Voyagers are only about 150 AU from the Sun, so they have a long way to go before they truly escape the Sun's gravity. But in terms of the Sun's wind, the Sun's magnetic bubble, they've left. They're in the galaxy now, floating through the local interstellar medium. Each Voyager carries a golden record, a phonograph record with sounds and images from Earth, messages for any extraterrestrial civilization that might find them. The records include greetings in 55 languages, music from Bach to Chuck Berry, sounds of wind and rain and human laughter, images of people and places and DNA structures, their messages in bottles, cast into the cosmic ocean, unlikely ever to be found, but carrying humanity's voice nonetheless. The Voyagers will continue transmitting data until their power runs out, probably in the mid-2020s. After that, they'll go silent, drifting through space for eons. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. It won't be close enough for the star's gravity to capture it. Voyager will just drift past, silent and dark, a relic from a distant world, carrying its golden record into the depths of the galaxy. The Voyagers are humanity's farthest reach, our most distant emissaries. The first human-made objects to leave the solar system's protective bubble and venture into the wider cosmos. They're still out there, still traveling, still moving away at tens of thousands of kilometers per hour, carrying our messages, our hopes, our voices into the silence between the stars. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper proposing that a large, unseen planet might exist in the distant solar system. They weren't looking for it directly. Instead, they noticed something strange. Several distant Kuiper Belt objects, icy bodies orbiting far beyond Neptune, had orbits that were oddly aligned. The orbits clustered together, all elongated in the same direction, all tilted at similar angles. This clustering is unlikely to be random. Computer simulations suggested that a large planet, about 10 times Earth's mass, orbiting far from the Sun, could gravitationally shepherd these distant objects, aligning their orbits over time. The planet would need to be distant, perhaps 400 to 800 AU from the Sun, and on a highly elongated orbit that takes 10,000 to 20,000 years to complete. This hypothetical planet, called Planet 9, hasn't been observed directly. It would be faint. Sunlight is incredibly dim that far out, and moving slowly across the sky, making it difficult to detect among the countless faint stars in the background. Telescopes have searched for it, scanning the sky in the predicted regions, but so far, nothing definitive has been found. Some astronomers are skeptical. Maybe the clustering is a selection effect. We tend to discover these distant objects when they're closest to the Sun, at certain points in their orbits, which could create apparent clustering without requiring a planet. Or maybe the gravity from the galaxy's disk affects these objects' orbits in ways that mimic a planet's influence. But other evidence supports Planet 9. Some simulations show that it could explain not just the clustering, but also the existence of objects with extremely tilted orbits that are nearly perpendicular to the plane of the solar system. These objects are hard to explain without some large, distant gravitational influence. There's also a more exotic possibility. What if Planet 9 isn't a planet at all, but a primordial black hole? These hypothetical objects formed in the early universe rather than from stellar collapse could be as small as a grapefruit, but contain several Earth masses. Such a black hole would produce the same gravitational effects as a planet, but it would be essentially impossible to detect directly. No reflected sunlight, no heat signature, just gravity. For now, Planet 9 remains hypothetical. If it exists, it's out there somewhere, cold and distant, slowly orbiting the sun, unseen but felt through the gravitational nudges it gives to smaller objects. Future surveys, particularly the Vera Rubin Observatory, will scan the sky more comprehensively. And if Planet 9 exists, we'll likely find it within the next decade. If confirmed, Planet 9 would join the ranks of planets discovered through their gravitational influence before being seen directly, like Neptune. It would expand the known solar system, add a new giant planet to our inventory, and raise questions about how it got there, whether it formed in place or was captured from another star, whether it's the only one or just the nearest of many distant worlds we haven't yet detected. The solar system, vast and seemingly well explored, might still hide secrets. Planet 9 is a reminder that we haven't finished discovering our own cosmic neighborhood. In 2011, scientists analyzing images from the Mars Reconnaissance Orbiter noticed something peculiar. Dark streaks appearing on slopes during Martian spring and summer, then fading during fall and winter. These features, called recurring slope lineae or RSL, were dynamic, seasonal, and intriguing. The streaks appear on sun-facing slopes, growing downhill over time, then fading when temperatures drop. This behavior suggested liquid water, perhaps briny water with salts that lower its freezing point, allowing it to remain liquid in Mars's cold environment. The slopes where RSL appear are too steep for dry avalanches to match their characteristics, so something fluid seemed to be involved. If RSL are caused by liquid water, even briefly, even as seasonal briny flows, it would mean Mars has liquid water on its surface today, not just locked in ice or buried underground. This has enormous implications for astrobiology. Life as we know it requires liquid water. If water flows on Mars, even temporarily, it might provide habitats for microbial life. But the evidence is complex and contested. Spectroscopic measurements detected hydrated salts, minerals that contain water molecules, in some RSL locations, supporting the water hypothesis. But not all RSL show these signatures, and alternative explanations exist. Perhaps RSL are dry flows, granular materials like sand moving downhill, triggered by seasonal changes in frost or atmospheric pressure. Perhaps they're landslides of CO2 frost. Perhaps they involve water, but only small amounts, not enough to sustain life. Recent studies have leaned toward dry explanations, suggesting RSL might form without significant liquid water. But the debate continues. Mars is full of surprises, and features that seem simple often turn out to be complex, driven by processes we don't fully understand. RSL are part of a larger question. Does liquid water exist on Mars's surface today, in any form? Mars had abundant water billions of years ago. Evidence is overwhelming. But today, with the thin atmosphere and cold temperatures, liquid water is unstable. It should freeze or evaporate almost immediately. Yet Mars might find ways to cheat, to create transient liquid through salt brines, through subsurface flows, through microenvironments where conditions briefly allow water to exist. The search for Martian water continues. Rovers drill into rocks, looking for moisture. Orbiters map ice deposits and monitor seasonal changes. And we keep discovering hints, never definitive proof, but suggestions, possibilities, tantalizing clues that Mars might still have liquid water, hidden, fleeting, perhaps nurturing life in protected niches where we haven't yet looked closely enough. We've talked about Enceladus's geysers, its subsurface ocean, the plumes that spray water into space. But it's worth emphasizing just how promising Enceladus is for astrobiology. When Cassini flew through the plumes, tasting the water with its instruments, it found not just water and salt, but a complex chemical soup. There were organic molecules, complex carbon compounds, including formaldehyde, acetylene, propylene. There was molecular hydrogen, produced when water reacts with hot rock in hydrothermal vents on the ocean floor. There were silica grains, tiny particles that form in hot water, indicating temperatures above 90 degrees Celsius somewhere in the ocean. There were salts, suggesting a salty ocean, similar in some ways to Earth's oceans. These findings check all the boxes for habitability. Liquid water? Yes. Organic molecules? Yes. Energy source? Yes. The molecular hydrogen indicates chemical reactions that could provide energy for life, the same kind of reactions that fuel chemosynthetic ecosystems at Earth's hydrothermal vents. A rocky interface where chemistry can happen. Yes, the silica grains prove water is in contact with a hot, rocky core. Enceladus has everything life needs. It doesn't mean life exists there. We haven't found it. And the conditions might not be quite right, despite having the ingredients. But Enceladus is one of the most promising places in the solar system to search. And it's accessible. The plumes carry ocean water directly into space. We don't need to drill through kilometers of ice like we would on Europa. We can fly through the plumes, as Cassini did, and sample the ocean without landing. Future missions could carry more sophisticated instruments, designed specifically to detect biosignatures, amino acids, lipids, patterns of isotopes that indicate biological processes. There's even been discussion of sending a mission that would collect samples from the plumes and return them to Earth for detailed analysis. This would be technologically challenging, but not impossible. The plumes are Enceladus's gift to us, free samples of an alien ocean, offering clues about whether life exists beyond Earth. Enceladus is small, cold, distant. It shouldn't be geologically active. It shouldn't have an ocean. And it certainly shouldn't be one of the best places in the solar system to search for life. But it is. Tidal heating from Saturn keeps the ocean liquid. Hydrothermal vents provide energy and minerals. Organic chemistry happens in the dark waters beneath the ice, and the geysers give us a way to investigate, to search, to answer one of humanity's oldest questions. Are we alone? In 2020, NASA's OSIRIS-REx spacecraft attempted to collect a sample from the asteroid Bennu. The plan was to briefly touch the surface with a robotic arm, fire a burst of nitrogen gas to stir up dust and pebbles, and capture them in a collection chamber. The engineers expected the surface to be somewhat firm, covered with loose material, but with some resistance. Instead, the spacecraft's sampling arm sank deep into Bennu's surface, plunging almost half a meter into what felt like a pit of loosely packed particles. If the spacecraft hadn't fired its thrusters to back away, it might have sunk even farther. Bennu's surface wasn't firm at all. It was more like a ball pit or a pile of gravel barely held together. This confirmed what scientists had suspected. Bennu is a rubble pile asteroid. It's not a solid rock. It's a loose collection of boulders, pebbles, and dust held together by gravity alone. The cohesion between particles is minimal. If you stood on Bennu, which you could barely, because its gravity is about 100,000 times weaker than Earth's, the ground beneath you would feel unstable, crumbly, like standing on a pile of sand that might shift at any moment. Rubble pile asteroids form from collisions. A larger asteroid is smashed apart by an impact, creating fragments that reaccumulate under their mutual gravity, forming a loose aggregate. The result is an asteroid with lots of empty space inside, a porous structure more void than solid, with material loosely clumped together. Bennu's density is only about 1.2 grams per cubic centimeter, barely denser than water. But the rocks it's made from are much denser, about 3 GSM-3. This means Bennu is about half empty space, filled with voids and gaps between the boulders and particles. This has implications for planetary defense. If a rubble pile asteroid were heading for Earth and we tried to deflect it by slamming a spacecraft into it, the impact might not work as expected. The kinetic energy might be absorbed by the loose structure, compressing voids and shifting rubble, without imparting much momentum to the asteroid as a whole. Deflecting rubble pile asteroids might require different strategies: slow pushes over time, or gravitational tractors that gently tug the asteroid onto a different path. OSIRIS-REx successfully collected a sample from Bennu, despite the surprising surface properties. That sample returned to Earth in 2023, containing pristine material from the early solar system, including organic molecules, hydrated minerals, and possibly even pre-solar grains. Studying Bennu's material helps us understand how asteroids form, what they're made of, and how the building blocks of planets, and perhaps life, came together billions of years ago. Bennu is a pile of rubble, barely held together, tumbling through space, but it's also a time capsule, a preserved sample of the early solar system, and a reminder that asteroids are more complex, more fragile, more interesting than simple flying rocks. Planets cool, formed hot, they radiate heat into space over billions of years, gradually losing the energy they were born with. As they cool, they contract, materials become denser, volumes decrease. Earth is cooling, though so slowly and with so much internal heat remaining that the contraction is minimal and masked by plate tectonics. But Mercury is small, and it's cooling faster, and the evidence of its contraction is written across its surface. Mercury's surface is covered with features called Lobat scarps, long, winding cliffs that can stretch for hundreds of kilometers and rise 1 or 2 kilometers high. These scarps are thrust faults, created when the crust compresses and buckles, pushing one section of crust up and over another. They're wrinkles, essentially, in Mercury's skin, formed as the planet shrinks. By measuring these scarps, mapping their distribution, and estimating how much compression they represent, scientists have calculated that Mercury's radius has decreased by about 7 kilometers since the crust solidified. That means Mercury's circumference is about 14 kilometers smaller than it used to be. The planet has shrunk measurably, visibly, enough that we can see the consequences from orbit. This shrinkage is driven by the cooling of Mercury's core. Mercury has an unusually large core for its size. About 75% of the planet's radius is core, with only a thin mantle and crust surrounding it. As this iron core cools, it contracts, pulling the entire planet inward. The crust, already solidified, cracks and wrinkles under the compression, creating the scarps we see. Mercury is still cooling, still contracting. New scarps might still be forming, though very slowly. The planet is geologically dead in the sense that it has no volcanism, no plate tectonics, no active resurfacing. But it's not entirely static. It's still shrinking, still adjusting to the slow loss of heat, still wrinkling as its interior contracts. This process is universal. All rocky planets cool and contract to some degree. But on larger planets like Earth and Venus, other processes, volcanism, tectonics, atmospheric weathering, obscure or overwrite the evidence. Mercury, small and inactive, preserves its contraction scarps, a direct record of planetary cooling visible on the surface. Mercury is old, ancient, scarred by billions of years of impacts and slowly shrinking as it cools. It's a dying planet, not in any dramatic sense, but in the slow, quiet way that all planets eventually die. Cooling, contracting, fading, until they reach thermal equilibrium with space and become cold, inert, unchanging worlds where nothing new ever happens. Plate tectonics, the process where a planet's crust breaks into plates that move, collide, and recycle into the interior, is rare. On Earth, it drives earthquakes, builds mountains, creates ocean basins, and plays a crucial role in climate regulation by cycling carbon between surface and interior. But Earth seems to be the only rocky planet in the solar system with active plate tectonics. Mars and Venus don't have it. Mercury doesn't. The Moon doesn't. But Europa might. The evidence is indirect but intriguing. Europa's surface is young, very few craters, indicating active resurfacing. The surface is covered with fractures, ridges, and chaotic terrains that suggest the ice shell is mobile, breaking apart and reforming. Some regions show patterns consistent with plates pulling apart, with new ice filling the gaps, similar to seafloor spreading on Earth. If Europa has plate tectonics, it would be cryotectonic, driven by ice rather than rock. The ice shell, floating on the subsurface ocean, might break into plates that move relative to each other. Tidal heating and convection in the ocean could drive this motion, creating upwelling zones where warm water rises and new ice forms, and subduction zones where old ice sinks back into the ocean. This process would cycle material between the surface and the ocean, potentially transporting nutrients, organic molecules, and energy. If life exists in Europa's ocean, plate tectonics might help sustain it by mixing materials, preventing the ocean from becoming stagnant, and creating diverse habitats at different depths and temperatures. Europa's potential plate tectonics also makes the surface more accessible for sampling. If the ice plates are moving and recycling, relatively young material from the ocean might be exposed at the surface, reachable by a lander. We wouldn't need to drill through the entire ice shell. We might find ocean material brought up by tectonic processes, frozen into surface ice, waiting to be sampled. The Europa Clipper mission, launching in the 2024, will study Europa's ice shell in detail, mapping its thickness, composition, and structure. It will look for evidence of plate boundaries, measure tidal deformations, and search for plumes. If Europa has plate tectonics, Clipper should be able to find signatures of it, patterns in the surface features, variations in ice thickness, maybe even active venting along plate boundaries. Europa is already remarkable, an ocean moon with all the ingredients for life. But if it also has plate tectonics, it becomes even more Earth-like, more dynamic, more promising as a habitat. Plate tectonics on Earth has been crucial for maintaining habitability over billions of years. Perhaps the same is true for Europa. Perhaps plate tectonics, even in ice, is a key ingredient for complex, sustained habitability. After flying past Pluto in 2015, New Horizons continued outward, heading deeper into the Kuiper Belt. Its next target was a small, distant object officially named Arrokoth, previously called Ultima Thule. On January 1, 2019, New Horizons flew past Arrokoth, capturing images of the most distant object ever visited by a spacecraft. Arrokoth is strange and beautiful. It's about 36 kilometers long, shaped like a snowman or a contact binary. 2 lobes connected by a narrow neck. The larger lobe is about 21 kilometers across, the smaller lobe about 15 kilometers. They touch gently, joined in what appears to have been a very low-speed collision. This shape tells a story about the early solar system. Arrokoth formed from 2 separate objects that were orbiting close to each other, gradually spiraling inward due to friction with the surrounding gas in the protoplanetary disk. Eventually, they touched, merging at a speed of perhaps just a few kilometers per hour. A gentle kiss rather than a violent impact. They stuck together, forming the bilobed shape we see today. This gentle merger is exactly what theories of planet formation predict. Planets grow from countless small collisions, most of them gentle, building larger objects incrementally. But we'd never seen direct evidence of this process preserved. Arrokoth is that evidence, a pristine example of a gentle collision, frozen in time, unchanged for 4.6 billion years. Arrokoth's surface is smooth, with few craters and uniformly colored, a reddish hue caused by organic compounds altered by radiation. There are no signs of violent impacts, no cracks or shattered terrain. It's peaceful, serene, an object that formed gently and has drifted quietly through the Kuiper Belt ever since, undisturbed, untouched, waiting for New Horizons to arrive and photograph it. Studying Arrokoth helps us understand how planets form. The early stages of planet formation are hidden from us. They happened billions of years ago, and the evidence has been erased by later collisions, heating, and geological activity. But in the Kuiper Belt, pristine objects like Arrokoth preserve that evidence. They're fossils from the era of planet formation, showing us directly how small bodies collided and stuck together, how the building blocks of planets assembled themselves from dust and ice. Arrokoth is the most distant, most primitive object we've ever explored up close. It's a time capsule from the solar system's birth, a gentle collision frozen in time, a reminder that planets are built not just through violence, but through countless gentle touches, objects finding each other in the darkness and deciding somehow to stay together. Mars has ice caps at both poles, and they change with the seasons. During Martian winter, carbon dioxide from the atmosphere freezes onto the polar ice cap, forming a seasonal layer of dry ice, solid CO2, that can be a few meters thick. This layer is bright, reflective, and grows rapidly as winter progresses, covering the permanent polar cap beneath. When spring arrives, the dry ice begins to sublimate, turning directly from solid to gas without passing through a liquid phase. The CO2 returns to the atmosphere, and the seasonal cap shrinks, eventually disappearing entirely, revealing the permanent cap beneath. This permanent cap is made mostly of water ice, mixed with dust, stable year-round because Mars's poles are cold enough that water ice doesn't sublimate significantly. This seasonal cycle creates dramatic changes. The southern polar cap can grow to cover a region larger than North America during winter, then shrink to a fraction of that size during summer. The North Pole undergoes similar but less extreme changes because Mars's orbit is elliptical, and the northern and southern hemispheres experience different intensities of seasons. The sublimation of dry ice creates interesting phenomena. As the ice warms, gas trapped beneath the translucent layers of dry ice builds up pressure, then explosively vents through cracks, carrying dark dust with it. This creates dark spots and streaks on the polar cap, features that appear and change over days or weeks, looking almost like plants or mold growing on the ice, though they're purely geological. Mars's polar caps also contain layered deposits, alternating layers of ice and dust that record millions of years of climate history. These layers, visible in cross-section where cliffs expose them, are like tree rings or ice core records on Earth. They tell us about changes in Mars's orbit and tilt, about periods when more or less ice accumulated, about dust storms that deposited dark layers between ice layers. By studying these layers, scientists can reconstruct Mars's climate history, understanding how the planet's tilt and orbit have changed, and how those changes affected ice accumulation. The polar caps are dynamic features, not static. They grow and shrink with the seasons, exchange CO2 with the atmosphere, create winds and weather patterns, and preserve records of ancient climates. They're also potential resources. Water ice at the poles could be mined for drinking water, oxygen, or rocket fuel if humans ever establish a permanent presence on Mars. Mars's poles are beautiful alien landscapes, white ice caps against red plains, dark streaks appearing and fading, layered cliffs revealing millions of years of history. They're places where Mars's thin atmosphere and cold climate create processes unlike anything on Earth, where dry ice sublimates by the billions of tons each season, where the planet breathes in and out, freezing and releasing its atmosphere in a yearly cycle that has continued for eons. The sun is hot. This is obvious, but the implications are profound when you're trying to build a spacecraft that will fly close to it. For decades, we studied the sun from a distance, from Earth orbit, from spacecraft, at safe distances measured in millions of kilometers. But to truly understand the sun's corona, its magnetic field, the mechanisms that heat the corona and accelerate the solar wind, we needed to go closer, much closer. The Parker Solar Probe, launched in 2018, is designed to do exactly that. It's a car-sized spacecraft with a heat shield made of carbon composite foam, about 11 centimeters thick, capable of withstanding temperatures exceeding 370 degrees Celsius. Behind the shield, the instruments remain at a relatively comfortable room temperature, while the shield's outer surface glows red hot. Parker Solar Probe doesn't orbit the sun in a simple circle. It uses Venus for gravity assists, swinging past the planet multiple times to gradually tighten its orbit, bringing it closer and closer to the sun with each pass. At its closest approach, Parker comes within about 6.2 million kilometers of the sun's surface, well within the corona, the sun's outer atmosphere that extends millions of kilometers into space. At this distance, Parker travels at over 700,000 kilometers per hour, making it the fastest human-made object ever built. fast enough to fly from New York to Tokyo in under a minute. Fast enough that relativistic effects, the time dilation predicted by Einstein's theory of relativity, become measurable, though still tiny. Parker's instruments measure the solar wind directly, sampling the particles streaming from the sun. They measure magnetic fields, tracking how they twist and reconnect. They observe waves and turbulence in the corona, looking for the mechanisms that transfer energy from the sun's surface into the corona, heating it to millions of degrees. And Parker has made discoveries. It found that the solar wind isn't smooth but structured, with switchbacks, abrupt reversals in the magnetic field that create S-shaped kinks. These switchbacks might be a key mechanism for accelerating the solar wind, though the details are still being worked out. Parker also found that the corona has distinct boundaries, regions where the properties change sharply, helping define where the sun's atmosphere ends and the solar wind begins. Flying through the corona is like flying through fire. The environment is plasma, ionized gas, at millions of degrees, permeated by intense magnetic fields and radiation. The heat shield glows. Solar panels, normally extended to catch sunlight, retract behind the shield to avoid being vaporized. Communication with Earth is intermittent, planned around the times when Parker is far enough from the sun that its antenna can point homeward without exposing sensitive equipment to direct sunlight. Parker Solar Probe will continue its mission through at least 2025, making closer and closer approaches, gathering more data with each pass. It's touching the sun, reaching into the corona, going where no spacecraft has gone before, bringing back information that's transforming our understanding of our nearest star. There's something poetic about this. Humans, trapped on a planet, unable to physically approach the sun without being incinerated, built a machine that can withstand the heat, that can fly through the corona and survive, that can be our eyes and ears in an environment we'll never personally experience. Parker is our proxy, our explorer, our way of reaching out and touching the sun. Saturn's North Pole hosts one of the strangest atmospheric features in the solar system, a hexagon, not a circle, not an ellipse, but a nearly perfect six-sided geometric shape, a jet stream flowing at about 320 kilometers per hour in a hexagonal pattern around the pole. The hexagon is enormous, nearly 30,000 kilometers across, large enough to fit two Earths side by side. Each side of the hexagon is longer than the diameter of Earth. It's a persistent feature, observed continuously since the Voyager missions in the 1980s, and probably existing long before that. The hexagon rotates with Saturn's interior, completing one rotation every 10 hours and 39 minutes, which tells us it's anchored deep in the atmosphere, not just a surface phenomenon. Why a hexagon? No one knows for certain. Hexagons don't spontaneously form in atmospheric flows on Earth, so this is deeply puzzling. Laboratory experiments have shown that you can create polygon-shaped flows in rotating fluids under certain conditions. Specific combinations of rotation rate, fluid viscosity, and flow speeds can produce stable polygonal structures. But translating those lab results to Saturn's atmosphere, with its different scale, composition, and dynamics, is challenging. One hypothesis involves wave interactions. If you have a circular jet stream and introduce a wave, a perturbation that creates a pattern of highs and lows in the flow, sometimes the wave can lock into a stable configuration, creating straight edges instead of curves. With the right wavelength and flow conditions, you get a hexagon, but the details remain uncertain. The hexagon has a vortex at its center, a massive cyclone sitting at Saturn's north pole. Similar to the cyclones we've discussed on Jupiter, though singular rather than multiple. This central vortex spins rapidly, and clouds swirl into it, creating an eye-like structure. At Saturn's south pole, there's no hexagon, just a single large cyclone, similar to the North Pole's central vortex, but without the hexagonal jet stream surrounding it. Why the asymmetry? Why does the North Pole have a hexagon while the South doesn't? Another mystery. The hexagon changes appearance with Saturn's seasons. During northern winter, when the North Pole was in shadow, the hexagon was faint, visible mainly in infrared. But as northern spring arrived and sunlight illuminated the pole, the hexagon became vibrant, its colors deepening, its structure sharpening. This suggests that solar heating affects the hexagon's dynamics, perhaps strengthening the jet stream or altering the cloud formation within it. Saturn's hexagon is a reminder that planets create patterns we don't expect, structures that challenge our intuition. We expect circles, planets are round, orbits are elliptical, storms are typically circular or oval. But here's a hexagon, stable for decades, rotating steadily, a six-sided geometric figure etched into Saturn's atmosphere by forces we're still working to fully understand. It's beautiful, in a strange, abstract way. A natural hexagon, larger than Earth, spinning at the pole of a giant planet, created without intention, without design, simply by the physics of rotating fluids and jet streams. The universe builds geometry without architects, creates art without artists. When Galileo orbited Jupiter in the 1990s, studying the giant planet and its moons, it carried a magnetometer, an instrument that measures magnetic fields. During flybys of Europa, the magnetometer detected something unexpected. Europa had a magnetic field that varied in time, responding to Jupiter's rotating magnetic field. This wasn't Europa's own magnetic field, generated by a dynamo in its core. It was an induced magnetic field, created when Jupiter's powerful rotating magnetic field swept past Europa. A time-varying magnetic field induces electric currents in any conducting material, and those currents create their own magnetic field in response. The presence of this induced field told scientists something crucial. Europa contains a large volume of electrically conducting material. What conducts electricity well enough to create such a strong induced field? Liquid water with dissolved salts, a salty ocean. Salt water is an excellent conductor because the dissolved ions, sodium, chloride, and others, carry electric charge. Pure water ice, by contrast, is a poor conductor. The strength and behavior of Europa's induced magnetic field allowed scientists to estimate the ocean's properties. The ocean is likely global, surrounding the entire moon, and probably about 100 kilometers deep. It's buried beneath an ice shell that might be 10 to 30 kilometers thick, though the exact thickness is debated and might vary across Europa's surface. This discovery was transformative. Before Galileo, we suspected Europa might have an ocean based on surface features and tidal heating calculations. But the magnetic field data provided direct physical evidence. It wasn't speculation anymore. Europa has an ocean. We measured it electromagnetically, indirectly, but definitively. This technique, using induced magnetic fields to detect subsurface oceans, has been applied to other moons. Ganymede shows similar signatures, confirming its subsurface ocean. Callisto has weaker but detectable induction, suggesting a thinner or less conductive ocean. Even Titan shows evidence of induction, supporting the idea that it has a subsurface ocean beneath its thick, icy crust. Induced magnetic fields are now a standard tool for detecting oceans on icy moons. It's a beautiful application of physics, using electromagnetism to see beneath kilometers of ice, to detect liquid water hidden from direct view, to map oceans on worlds so distant that even the best telescopes show them only as points of light. Europa's induced magnetic field is more than just scientific evidence. It's proof that beneath the cracked icy surface lies an ocean, dark and hidden, possibly salty like Earth's seas, possibly harboring life. The magnetic field is a signal, a message from the ocean, saying, "I'm here. I exist. Come find me." Today, Mars's atmosphere is wispy, barely there, less than 1% the pressure of Earth's atmosphere. It's mostly carbon dioxide with traces of nitrogen and argon, so thin that water can't exist as a liquid on the surface. The pressure is below the triple point of water, meaning water either freezes or sublimates. There's no liquid phase. But Mars wasn't always like this. Evidence carved into its surface tells a different story. Ancient river valleys snake across the Martian highlands, some extending for hundreds of kilometers. Crater lakes show inlet and outlet channels where rivers once flowed in and out. Delta deposits, where rivers emptied into lakes, preserve layers of sediment. Minerals that form only in the presence of liquid water, clays, sulfates, carbonates, are widespread across Mars's surface. All of this points to a warmer, wetter Mars billions of years ago, with a thicker atmosphere that created greenhouse warming and allowed liquid water to persist on the surface. Estimates suggest Mars's ancient atmosphere might have been several times thicker than Earth's current atmosphere, dense enough to trap heat, to stabilize liquid water, to create a hydrological cycle with rain, rivers, lakes, maybe even seas. What happened to that atmosphere? We've discussed this partly. Atmospheric stripping by the solar wind, enabled by the loss of Mars's magnetic field. But there are other mechanisms too. Carbon dioxide can be absorbed into surface rocks, forming carbonates, locking atmospheric CO2 into the crust. Water can break down in the upper atmosphere through photodissociation. Sunlight splits water molecules into hydrogen and oxygen, and the light hydrogen escapes to space. Over hundreds of millions of years, these processes drained Mars's atmosphere away. The pressure dropped. Temperatures fell. The liquid water froze or evaporated. The river valleys dried up. The lakes emptied. Mars transformed from a potentially habitable world into the cold desert we see today. The timeline is debated. Some evidence suggests Mars had liquid water only briefly, for the first few 100 million years, then dried out. Other evidence points to episodic wetness, periods when volcanic activity or asteroid impacts temporarily warmed the planet and melted ice, creating brief wet periods lasting thousands or millions of years, followed by long dry periods. The Martian climate might have been highly variable, cycling between wet and dry states, never truly stable. If Mars once had a thick atmosphere and liquid water, did it have life? That's the question driving much of Mars exploration. Life could have emerged in those ancient rivers and lakes during the wet period billions of ago. When the water disappeared, life might have gone extinct, or it might have retreated underground into aquifers and ice deposits, surviving in protected environments where liquid water persists. We're searching for evidence of ancient life, fossils, organic molecules, isotopic signatures that would indicate biological processes. Rovers drill into ancient lake beds, analyze sedimentary rocks, look for the chemical traces that life would have left behind. So far, we've found organic molecules, complex carbon compounds, but nothing definitively biological. The search continues. Mars's lost atmosphere is a tragedy, in a sense. A planet that might have been habitable, that might have hosted life, that might have been a second Earth, lost its atmosphere and became barren. It's a reminder that planetary habitability is fragile, that atmospheres can be lost, that the protection we take for granted, our magnetic field, our thick atmosphere, is precious and not guaranteed to last forever. Ceres is the largest object in the asteroid belt, massive enough that its gravity pulled it into a spherical shape, earning it the classification of dwarf planet. For a long time, Ceres was just another asteroid. Interesting, but not exceptional. Then NASA's Dawn spacecraft arrived in 2015 and revealed a world far more complex than expected. The most striking features on Ceres are bright spots, highly reflective patches, especially prominent in Occator crater. These spots stand out dramatically against Ceres's dark, carbon-rich surface. Early speculation suggested ice, salt, or some other reflective material, but detailed analysis revealed they're deposits of sodium carbonate, a salt that forms when briny water evaporates. This tells us something profound. Ceres has, or had, liquid water beneath its surface. Briny water from a subsurface reservoir rose through cracks, perhaps driven by pressure or by impact-induced heating. When this water reached the surface, it evaporated in Ceres's vacuum-like environment, leaving behind salt deposits. The process might still be ongoing in some regions, with occasional outgassing creating transient hazes of water vapor. Dawn's data also revealed that Ceres's crust is rich in water ice mixed with rock, and there may be a buried ocean or at least extensive pockets of brine beneath the crust. The dwarf planet shows evidence of cryovolcanism, ice volcanoes that erupt slushes of water, brine, and mud rather than molten rock. Ahuna Mons, a solitary mountain on Ceres, might be a cryovolcano, built from eruptions of briny material that froze on the surface. Ceres is geologically active, or at least recently active on geological timescales. The bright spots are young, perhaps only a few million years old, indicating that Ceres hasn't been completely dead and frozen since its formation. Something keeps driving geological activity, whether it's residual heat from formation, heat from radioactive decay, or perhaps tidal heating from gravitational interactions with other asteroids. The discovery that Ceres has water, brine, and potential cryovolcanism elevates it from just another asteroid to a complex dwarf planet with active geology. It joins the list of ocean worlds, bodies in the solar system that harbor or harbored liquid water beneath their surfaces. Ceres is smaller and less promising than Europa or Enceladus, but it's also much closer, orbiting within the asteroid belt, accessible in timescales measured in years rather than decades. Some scientists have speculated about life on Ceres. If there are pockets of brine beneath the surface, if there's organic material, which is abundant on Ceres, if there's energy from radioactive decay or chemical reactions, could microbial life exist? It's unlikely, but not impossible. Ceres is cold, briny, and chemically strange, But life has surprised us in extreme environments on Earth. Ceres is a reminder that the asteroid belt isn't just a collection of dead rocks. Among those millions of fragments, there are worlds, small perhaps, but complex, geologically active, harboring water and organic material, holding secrets we're only beginning to uncover. Triton orbits Neptune backwards, retrograde, a captured Kuiper Belt object that found itself trapped by Neptune's gravity and has been orbiting ever since. But this orbit isn't stable in the long term. Tidal forces, the same forces that cause tides on Earth, are slowly draining energy from Triton's orbit. Here's how it works. Triton's gravity raises tidal bulges on Neptune. Because Triton orbits backwards, these bulges are pulled ahead of Triton, and the gravitational interaction between the bulges and Triton acts as a drag, slowing Triton down. When an orbiting object slows down, it spirals inward. Counterintuitively, losing energy causes it to move to a lower orbit. This process is gradual, imperceptible on human timescales. Triton spirals inward by perhaps a few centimeters per year, maybe less. But over millions and billions of years, it adds up. Triton is moving toward Neptune, slowly but inevitably. Eventually, in about 3.6 billion years, Triton will cross the Roche limit, the distance within which tidal forces from Neptune become stronger than Triton's own gravity, holding it together. At that point, Triton will be torn apart. Its material will spread out into a ring around Neptune, creating a spectacular ring system that might rival or exceed Saturn's rings. This fate isn't unique. Moons spiraling inward due to tidal forces is a common phenomenon. Mars's moon Phobos is also spiraling inward and will be destroyed in about 50 million years, much sooner than Triton. But Triton's eventual destruction is particularly striking because Triton is large, 2,700 kilometers in diameter, larger than Pluto, and the ring system it creates will be correspondingly massive. For now, Triton survives. It's geologically active, with geysers erupting nitrogen gas, a young surface with few craters, strange cantaloupe terrain, and temperatures reaching 235 degrees Celsius. It's one of the coldest objects in the solar system. Yet it's active, powered by some combination of tidal heating, radioactive decay, or internal chemistry. Triton's retrograde orbit also makes it unique among large moons. Most large moons formed alongside their planets and orbit prograde, in the same direction as the planet's rotation. Triton is the exception, a captured object orbiting backwards, slowly spiraling toward doom. There's a melancholy to this. Triton, a world in its own right, complex and active, will eventually be destroyed, not by collision, not by ejection, but by gravity itself, slowly pulling it closer until the forces become too strong and it shatters. But that's billions of years away. For now, Triton orbits Neptune, geologically alive, a captured wanderer making the best of its situation, spiraling slowly toward an end it can't escape. On January 14, 2005, a small probe separated from the Cassini spacecraft and plunged into Titan's thick atmosphere. This was Huygens, built by ESA, designed to parachute through Titan's atmosphere and land on the surface. It was the most distant landing humanity has ever achieved, and it worked. Huygens spent about 2.5 hours descending through Titan's atmosphere, and during that time, it transmitted data continuously. Images, measurements, sounds. Yes, sounds. Huygens carried a microphone and it recorded the audio of its descent. The recordings captured the whistle of wind rushing past the probe as it descended. They captured the rustle and snap of the parachute deploying. And near the end of the descent, they captured what sounded like rain. Droplets of liquid methane hitting the probe's exterior, creating soft, pattering sounds. This was the first time we heard sounds from another world. Beyond Mars, the first time we heard rain falling on an alien surface. When Huygens landed, it survived for over an hour on the surface, far longer than expected. It sent back images showing a landscape of rounded pebbles, water ice as hard as rock, shaped by erosion, and a flat plain that might have been a dried lakebed or riverbed. The light was dim, orange-tinted, filtered through Titan's thick, hazy atmosphere. Huygens measured Titan's surface temperature, 179 degrees Celsius. It measured the composition of the atmosphere, 98.4% nitrogen, 1.6% methane, with traces of other hydrocarbons. It detected winds, measured humidity, methane humidity, and analyzed the surface composition. The pebbles were ice. The ground was a mixture of ice and organic compounds, possibly mixed with liquid methane that had soaked into the surface. The audio recordings from Huygens are eerie. The wind sounds familiar, almost like wind on Earth, but with a different timbre, altered by the thick atmosphere's different density and composition. The rain, or whatever liquid was falling, sounds like rain but softer, gentler, because the thick atmosphere slows the droplets' fall. Listening to these recordings, you're hearing another world, not seeing it, not reading data about it, but hearing it. The wind, the rain, the creak of the probe settling onto the surface. It's intimate, immediate, more visceral than images or graphs. For a moment, you're there, on Titan's surface, experiencing it through sound. Huygens fell silent after about 90 minutes on the surface. Its batteries died. Its transmissions stopped. It remains there now, sitting on Titan's surface, a silent monument, humanity's only physical presence in the outer solar system beyond the gas giants. The wind blows past it, methane rain occasionally falls on it, and it sits, unmoving, a relic from another world, waiting for nothing, its work complete. Venus is often called Earth's twin because of its similar size and composition, but today, Venus is a hellscape. Surface temperatures hot enough to melt lead, crushing atmospheric pressure, clouds of sulfuric acid. It's hard to imagine Venus ever being habitable, yet evidence suggests it might have been once, billions of years ago. Climate models indicate that Venus could have had liquid water oceans for much of its early history, perhaps from 4.2 billion years ago, until as recently as 700 million years ago. That's a span of over 3 billion years, longer than Earth has had complex life, longer than Earth has had oxygen in its atmosphere. For most of solar system history, Venus might have been a water world, with oceans covering much or all of its surface. What happened? A runaway greenhouse effect. As the sun gradually brightened, Venus received more energy. Water evaporated from the oceans, increasing atmospheric water vapor. Water vapor is a greenhouse gas, so it trapped more heat, which caused more evaporation, which trapped more heat, a feedback loop that spiraled out of control. Eventually, the oceans boiled away entirely. Water vapor filled the atmosphere, but at high altitudes, sunlight broke the water molecules apart through photodissociation, splitting H2O into hydrogen and oxygen. The hydrogen, being light, escaped to space. The oxygen reacted with surface rocks or was lost to space as well. Venus's water was disassembled and lost, molecule by molecule, over millions of years. What remained was carbon dioxide. Venus's crust released CO2 through volcanism, and without liquid water to absorb it and form carbonates, the CO2 accumulated in the atmosphere. The pressure climbed. The greenhouse effect intensified further. Temperatures soared. Venus locked itself into a hot, high-pressure state from which it can't escape. If Venus had oceans for billions of years, could life have emerged there? It's possible. Life on Earth appeared quickly once conditions allowed, within the first few 100 million years. Venus had billions of years of potentially habitable conditions. Life could have arisen, evolved, perhaps even thrived. But if life existed on Venus, it's gone now. The runaway greenhouse sterilized the surface, boiled away the oceans, destroyed any ecosystems that might have existed. Venus's surface is now hostile to any known form of life. Even extremophiles that survive in Earth's harshest environments wouldn't survive on Venus's surface. However, some scientists speculate about life in Venus's clouds. High in the atmosphere, around 50 to 60 kilometers altitude, temperatures and pressures are Earth-like. Clouds at that altitude are sulfuric acid, which is harsh, but not necessarily fatal. Earth has microbes that tolerate acidic environments. If life once existed on Venus's surface, perhaps it adapted when the oceans boiled away, retreating into the clouds, evolving to survive as airborne microbes floating in acid droplets. It's speculative, unlikely, but tantalizing. Missions to Venus might search for biosignatures in the atmosphere, patterns of chemicals or structures that would be hard to explain without biology. For now, Venus remains a mystery, a world that might have been habitable, might have hosted life, might still harbor remnants in its clouds. Or maybe it's simply a dead world, a warning of what happens when greenhouse effects spiral out of control. Saturn's rings are beautiful but unstable. Left alone, ring particles would slowly spread out, diffusing inward and outward until the rings lost their sharp edges and became a diffuse disk. But Saturn's rings have sharp edges. Some gaps in the rings have crisp boundaries. How do they maintain the structure? The answer is shepherd moons, small moons orbiting within or near the rings, using their gravity to confine ring particles. The most famous examples are Prometheus and Pandora, two small moons that orbit on either side of the F ring, Saturn's outermost narrow ring. Prometheus orbits just inside the F ring, Pandora just outside. Their gravitational influence herds the ring particles, preventing them from spreading. Prometheus's gravity pulls particles inward, Pandora's pulls them outward, and the combined effect confines the F ring to a narrow band between the two moons. But the interaction isn't simple. Prometheus and Pandora don't orbit at exactly the same speed as the ring particles, so they periodically overtake the ring, creating waves and disturbances. The F ring shows braids, kinks, and clumps, structure created by these gravitational interactions. Occasionally, Prometheus dips close enough to steal material from the ring, creating dark channels and streamers visible in Cassini images. Other shepherd moons exist throughout Saturn's ring system. Pan orbits within the Encke Gap, a division in Saturn's A ring. Pan's gravity clears particles from the gap, creating the empty space. Daphne's does the same in the Keeler Gap. Both moons create waves at the gap edges, scalloped patterns where their gravity disturbs nearby particles, creating vertical waves that cast shadows visible in backlit images. These small moons are typically just a few tens of kilometers across. Prometheus is about 86 kilometers long, Pan only about 35 kilometers. They're tiny, irregular, more like flying mountains than proper moons. But their gravitational influence is significant enough to shape the rings, creating structure that would otherwise dissipate. The Shepherd moon concept is an example of orbital resonance, gravitational relationships, where orbits are related by simple ratios, creating repeated interactions that amplify effects. These resonances can clear gaps, create waves, or stabilize orbits. They're ubiquitous in the solar system, shaping not just Saturn's rings, but asteroid orbits, the Galilean moon's orbits, and countless other configurations. Saturn's rings are a laboratory for studying these gravitational interactions in real time. We can watch shepherd moons at work, see waves propagating through the rings, observe how gravity sculpts structure from chaos. The rings won't last forever. They're slowly raining onto Saturn, particles spiraling inward and falling into the planet's atmosphere. But for now, the shepherd moons maintain order, keeping the rings sharp, beautiful, structured, a testament to gravity's ability to organize matter on scales ranging from atoms to galaxies. The asteroid belt occupies the region between Mars and Jupiter, roughly 2 to 4 AU from the Sun. It's natural to wonder, why didn't these objects coalesce into a planet? There's enough material, though not much, as we've discussed, and the region seems favorable for planet formation. What prevented it? The answer is Jupiter. When Jupiter formed, it became the dominant gravitational force in the outer solar system. Its immense mass created resonances, orbital relationships, where asteroids complete a certain number of orbits for every orbit Jupiter completes. These resonances destabilized asteroid orbits, preventing the calm, orderly accumulation needed for planet formation. Imagine trying to build a tower of blocks while someone keeps shaking the table. You might get a few blocks stacked, but before you can build higher, the shaking knocks them apart. Jupiter's gravitational influence was like that, constantly perturbing asteroid orbits, speeding them up, sending them on elliptical paths where collisions became destructive rather than constructive. Instead of gentle collisions that allowed objects to stick together and grow, the asteroid belt experienced high-velocity impacts that shattered objects into fragments. The belt became a grinder, grinding down planetesimals into smaller and smaller pieces rather than building them into larger bodies. Ceres, the largest object in the belt, represents the upper size limit that could survive in this environment. Anything larger would have either accreted more mass and migrated out of the belt, or been scattered by Jupiter, or been ground down by collisions. Ceres is what's left, a fragment of what might have become a planet, preserved by luck and location. The asteroid belt is often described as the failed planet, but that's not quite right. It's more accurate to say the asteroid belt is where a planet failed to form. The material was there, the conditions seemed right, but Jupiter's influence prevented accretion. Instead of a planet, we have millions of asteroids, remnants of planetesimals, fragments from collisions, a museum of objects that date back to the solar system's formation. The asteroid belt is also a source of meteorites. Collisions in the belt create fragments that spiral inward toward the Sun. Some of these fragments eventually cross Earth's orbit, entering our atmosphere as meteors or landing as meteorites. Studying these meteorites gives us direct samples of asteroid material, allowing us to understand their composition, age, and history. Jupiter shaped the asteroid belt, but it didn't empty it. The asteroids remain, orbiting between Mars and Jupiter, a permanent feature of the solar system's architecture. They're leftovers, yes, but they're also witnesses, carrying information about the solar system's formation, about the processes that built planets, and the processes that prevented one from forming where they orbit. The sun's magnetic field is complex, dynamic, constantly changing. And every 11 years, it does something remarkable. It flips. The north magnetic pole becomes the south magnetic pole. The south becomes the north. The entire field reverses polarity, then gradually builds back up over the next 11 years until it reverses again. We know this happens. We've observed it repeatedly. But despite decades of study, we don't fully understand the mechanism. The sun doesn't have a solid surface or a simple, stable interior. It's a roiling ball of plasma, ionized gas, where magnetic fields are generated by the motion of charged particles. This process, called the solar dynamo, creates the sun's magnetic field, but the details are fiendishly complicated. The sun rotates differentially. The equator spins faster than the poles, completing a rotation in about 25 days, while the poles take about 35 days. This differential rotation stretches and twists magnetic field lines, wrapping them around the sun like rubber bands, wound tighter and tighter. Eventually, the field becomes so tangled that it erupts through the surface, creating sunspots and active regions where the magnetic field is especially strong. But how does this process lead to a complete reversal of polarity? The models suggest that as the field becomes increasingly disordered, the old field weakens, and a new field with opposite polarity emerges, building up until it dominates. The transition happens gradually over the course of solar maximum, when the sun's activity is at its peak and the magnetic field is most chaotic. The reversal isn't instant or uniform. Different parts of the sun reverse at different times. The process is messy, with mixed polarities coexisting for months or years during the transition. But eventually, the new polarity stabilizes, and the cycle begins again. This 11-year cycle affects everything in the solar system. Solar storms, flares, and coronal mass ejections are more common during solar maximum. The solar wind structure changes. Earth's upper atmosphere expands and contracts with the cycle. Auroras are more frequent and intense during active periods. Cosmic ray intensity varies, modulated by the sun's magnetic field strength. Understanding the solar cycle is important for practical reasons. Predicting space weather helps protect satellites, power grids, and astronauts. But it's also a fundamental problem in astrophysics. The sun is the only star we can study in detail, and its magnetic field behavior offers clues about how stellar magnetic fields work generally. Many other stars show cycles similar to the sun's, and understanding our sun helps us understand them. The sun's magnetic field is a reminder that even our closest star, studied for centuries, observed daily, remains mysterious in key ways. We can describe what happens, track the cycle, predict its phases, but the deep mechanism, the full dynamo process that generates and reverses the field, is still being worked out. The sun, familiar and ever-present, still guards its secrets. The Oort cloud is thought to be a vast, spherical shell of comets and icy bodies surrounding the solar system at its outermost edge. It begins perhaps 2000 AU from the Sun and extends out to maybe 100,000 AU, roughly halfway to the nearest star. It's enormous, containing perhaps trillions of objects, possibly more mass than all the planets combined, though spread across such a huge volume that the density is incredibly low. But we've never seen it. Not a single Oort cloud object has been directly observed. The Oort cloud is purely theoretical, inferred from the orbits of long-period comets that seem to originate from this distant region. When a long-period comet enters the inner solar system, we can trace its orbit backward, calculating where it came from. These comets arrive from all directions, not just from the ecliptic plane where the planets orbit, but from above and below, from all angles. This spherical distribution suggests a spherical source, the Oort cloud. The Oort cloud is thought to have formed from planetesimals that were scattered outward during the solar system's early history. As the giant planets formed and migrated, their gravity flung countless icy bodies outward, some escaping the solar system entirely, others falling into distant orbits that form the Oort cloud. These objects are barely bound to the Sun. The Sun's gravity at that distance is incredibly weak, and passing stars or the gravitational tide from the Milky Way can easily perturb their orbits, sending some plunging inward toward the Sun as long-period comets. Why haven't we seen Oort cloud objects directly? Because they're too small, too far, and too dark. At 50,000 AU, an object the size of a small mountain, or even a large city, would be completely invisible to our telescopes. Sunlight is incredibly dim out there, and reflected light from such a distant object would be impossibly faint. We can only see Oort cloud objects when they venture inward and develop cometary tails that reflect sunlight. Some astronomers have proposed searching for Oort cloud objects through occultations, watching for them to pass in front of distant stars, briefly blocking the starlight. This technique has been used to discover small objects in the Kuiper Belt. But the Oort cloud is so vast and its objects so widely separated that finding one through occultation would require an enormous survey, monitoring millions of stars continuously. The Oort cloud remains hypothetical but widely accepted. The evidence, the orbits of long-period comets, strongly suggests it exists, and the theory, gravitational scattering during planetary formation, provides a plausible formation mechanism. But until we directly observe an object at Oort cloud distances and confirm its orbit, the Oort cloud remains an inference, a shadow cast by the comets that occasionally visit us, hints of a vast frozen realm at the edge of the Sun's influence. It's humbling to think that the solar system extends so far beyond the planets we know, that there's a region larger than all the planetary orbits combined, filled with countless icy bodies, completely invisible to us, known only through its effects. The Oort cloud is the solar system's halo, its outermost boundary, the place where the Sun's gravity fades into the gravitational influence of other stars, the transition zone between our solar system and the wider galaxy. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close, and water boils away. Too far, and it freezes. Earth sits comfortably within the Sun's habitable zone, at a distance where water can exist as a liquid, where oceans can form, where life as we know it can thrive. But the habitable zone isn't fixed. As stars age, they brighten. The sun is about 10% brighter now than when it formed, and it will continue brightening. As it brightens, the habitable zone moves outward. The inner edge, where planets become too hot, moves farther from the sun. The outer edge, where planets are too cold, also moves farther out. Earth is currently in the habitable zone, but we're not far from the inner edge. In about 1 billion years, possibly sooner, the sun will be bright enough that Earth will cross the inner boundary. Temperatures will rise. Oceans will begin evaporating. Water vapor will accumulate in the atmosphere, trapping more heat, triggering a runaway greenhouse effect similar to what happened on Venus. Eventually, Earth will lose its oceans, its atmosphere will become thick with steam, and the surface will become inhospitable to life as we know it. Meanwhile, Mars, currently outside the habitable zone and frozen, will move into it. As the sun brightens, Mars will receive more energy. Temperatures will rise. If Mars still has subsurface ice, which it does, that ice might begin to melt, releasing water, and possibly creating a brief window where liquid water can exist on Mars's surface. Mars might become more habitable just as Earth becomes less so. This is cosmic irony, or perhaps just the nature of stellar evolution. Stars don't stay constant, they change, and as they change, the conditions for life shift. Civilizations that want to survive long-term must adapt, either technologically or by migrating to different planets as their homeworld becomes uninhabitable. In the even longer term, about 5 billion years from now, the sun will exhaust its hydrogen fuel and expand into a red giant. The habitable zone will move far outward, perhaps to the orbits of Saturn or Uranus, assuming those planets' moons retain their atmospheres. But by then the inner planets, Mercury, Venus, possibly Earth, will be engulfed by the expanding sun, vaporized, destroyed. The habitable zone is a reminder that habitability is temporary. Earth has been in the habitable zone for billions of years, and it will remain there for perhaps another billion, but not forever. The conditions that make Earth livable are a temporary alignment of distance, stellar brightness, and planetary properties. Eventually, that alignment will shift, and Earth will change. Life will need to adapt, migrate, or accept extinction, but that's far in the future. For now, Earth is habitable, comfortably within the zone where liquid water exists, where life thrives. We're lucky to live during this window, this brief cosmic moment when our planet is perfectly positioned, when the sun's light and warmth are just right, when the oceans cover the surface and life fills every niche. It won't last forever, but it's lasting now, and that's enough. Planet 9, if it exists, would be a large planet lurking in the distant solar system, explaining the strange orbits of distant Kuiper Belt objects through its gravitational influence. But there's an alternative hypothesis, exotic and speculative, but not impossible. What if Planet 9 isn't a planet at all, but a primordial black hole? Primordial black holes are hypothetical objects formed in the early universe shortly after the Big Bang, from density fluctuations that caused regions of space to collapse directly into black holes without going through stellar formation. These black holes could have a wide range of masses, from tiny, less than a kilogram, to thousands of solar masses. A primordial black hole with about 5 to 10 Earth masses would be roughly the size of a grapefruit, maybe smaller. A black hole of this size wouldn't emit light. It wouldn't reflect sunlight. it would be essentially invisible, detectable only through its gravitational effects. And those gravitational effects would be identical to a planet of the same mass. Gravity doesn't care whether mass is concentrated in a black hole or spread across a planet. The orbital perturbations we observe in distant Kuiper Belt objects could be caused by either. So how would we tell the difference? One possibility is searching for the black hole's accretion signature. As the black hole moves through space, it would occasionally capture gas or dust, which would spiral inward, heat up, and emit X-rays or gamma rays before crossing the event horizon. But space is mostly empty, and the rate of accretion would be extremely low, making detection difficult. Another approach is looking for dark matter annihilation. Some primordial black holes might be surrounded by halos of dark matter, particles that accumulate in the black hole's gravity well. If dark matter particles are their own antiparticles, they would occasionally collide and annihilate, producing gamma rays. Telescopes like Fermi might detect these signals, though distinguishing them from other sources is challenging. The primordial black hole hypothesis is speculative, unlikely, but scientifically intriguing. It's taken seriously enough that searches are ongoing. If Planet 9 is a black hole, it would be the first black hole in our solar system, the closest black hole to Earth by far, and a unique laboratory for studying black hole physics. Most scientists still favor the planet hypothesis. It's more straightforward, requires fewer exotic assumptions, but the black hole possibility remains open. Until we directly observe Planet 9, until we see reflected sunlight, or detect its thermal emission, or photograph it moving against the background stars, we can't rule out alternatives. The idea that our solar system might harbor a black hole, silently orbiting the sun at the edge of known space, is both unsettling and thrilling. It's a reminder that the universe contains objects and phenomena stranger than we usually imagine, and that even our own cosmic neighborhood might hide surprises that challenge our assumptions about what exists and where. We've touched on this before, but it's worth contemplating more deeply. The sun doesn't just emit light and heat. It emits particles, the solar wind, a constant stream of charged particles flowing outward in all directions. This wind carries the sun's magnetic field with it, creating a structure called the heliosphere, a bubble of solar influence surrounding the entire solar system. The heliosphere extends far beyond the planets, out to roughly 120 AU, where the solar wind finally runs into resistance from the interstellar medium, the gas and dust between stars. At this boundary, called the heliopause, the solar wind slows, compresses, and stops. Beyond the heliopause is interstellar space, where the sun's direct influence ends and the galaxy's environment takes over. The heliopause isn't smooth or spherical. It's shaped by the sun's motion through the galaxy. As the solar system moves through the interstellar medium at about 26 kilometers per second, the heliosphere gets compressed in the direction of motion, creating a bow shock, and stretched out behind, possibly forming a tail. The result is a comet-like shape, though recent data from Voyager and other spacecraft suggests the structure might be more complex, possibly split into multiple lobes or lacking a distinct tail. Crossing the heliopause is a significant milestone. It's the boundary between here and out there, between the sun's domain and the rest of the galaxy. When Voyager 1 crossed in 2012, followed by Voyager 2 in 2018, They became the first human-made objects to enter interstellar space. The environment changed immediately. Solar wind disappeared, cosmic ray intensity increased, the plasma density increased. They had left home, in a sense, and entered the larger cosmos. The heliopause protects us. Cosmic rays, high-energy particles accelerated by supernovae, pulsars, and other violent cosmic events, are partially deflected by the heliosphere. Inside the heliopause, cosmic ray intensity is lower than in interstellar space. This protection matters for life. High-energy cosmic rays can damage DNA, cause mutations, increase radiation doses. The heliosphere acts as a shield, not perfect but helpful, reducing the radiation that reaches Earth. The heliopause also defines, in a practical sense, where the solar system ends. Gravitationally, the Sun's influence extends much farther, out to the Oort cloud, perhaps 100,000 AU. But in terms of environment, in terms of being within the Sun's wind and magnetic field, the heliopause is the boundary. It's a permeable boundary, not a wall. Particles can cross in both directions. Neutral atoms from interstellar space drift across the heliopause and enter the solar system, creating what's called the interstellar breeze. And solar wind particles, deflected at the heliopause, can leak outward into interstellar space. The heliopause is dynamic, expanding and contracting with the solar cycle. During solar maximum, when the solar wind is stronger, the heliopause pushes outward. During solar minimum, it contracts. This breathing, expanding and contracting over an 11-year cycle, affects the entire heliosphere, changing its size and shape in response to the Sun's activity. Understanding the heliopause helps us understand how stars interact with their environments, how stellar winds carve out bubbles in the interstellar medium, how different environments transition from one to another. The heliopause is a boundary, but also a bridge, a place where two regimes meet and interact, creating a unique environment that exists nowhere else. Miranda is tiny, only about 470 kilometers in diameter, small enough to fit comfortably within the borders of Spain. It's one of Uranus's moons, orbiting the tilted ice giant in the cold and distant outer solar system. You'd expect it to be a boring, cratered ice ball, geologically dead for billions of years. But when Voyager 2 flew past in 1986, it revealed one of the strangest surfaces in the solar system. Miranda's surface is a patchwork of wildly different terrains. There are ancient, heavily cratered regions, dark, old, untouched for eons. And then there are coronae, bizarre, younger regions with ridges, grooves, and strange polygonal patterns, looking almost like someone took pieces from different worlds and stitched them together into Miranda's surface. The most dramatic feature is Verona Rupes, a cliff that drops about 20 kilometers, the tallest cliff known in the solar system, 20 kilometers. For comparison, the Grand Canyon's deepest point is about 1.8 kilometers. Verona Rupes is more than 10 times deeper. If you fell off the top, you'd be in free fall for over 10 minutes before hitting the bottom, because Miranda's gravity is so weak, about 1% of Earth's. Why does Miranda have such extreme terrain? No one knows for certain. One hypothesis suggests Miranda was shattered by a massive impact, broken into pieces that later reaccumulated under mutual gravity. As the pieces came back together, they created the jumbled, mismatched terrain we see. Different fragments with different surface ages and compositions assembled into a single moon, creating the patchwork appearance. Another hypothesis involves tidal heating. If Miranda once had a more eccentric orbit, perhaps due to resonances with other Uranian moons, tidal forces would have heated its interior, driving geological activity that resurfaced parts of the moon. When the orbital resonance broke, the heating stopped, and Miranda froze in its current configuration, preserving the evidence of its active period. Or perhaps Miranda underwent differentiation, heavier materials sinking toward the center, but the process was incomplete or disrupted, creating density variations that caused parts of the surface to sink or rise, forming the coronae and cliffs. We don't have enough data to decide definitively. Voyager 2's flyby was brief, and Miranda has never been visited again. Most of what we know comes from a few dozen images taken during those brief hours in 1986. Miranda remains mysterious, its dramatic terrain unexplained, a puzzle waiting for future missions. There's something haunting about Miranda. It's such a small world, so far from Earth, visited once for a few hours, photographed briefly, then left alone again in the darkness. It spins around Uranus, its cliffs and canyons and strange terrains unseen, unobserved, waiting silently for someone to return. Maybe one day we'll send another spacecraft to Uranus, and Miranda will reveal more of its secrets. Until then, it remains one of the solar system's most enigmatic worlds, a tiny moon with a face that shouldn't exist, telling a story we've only begun to read. Saturn's rings are unstable, at least in theory. Ring particles orbit independently, colliding constantly, exchanging momentum. Over time, you'd expect these collisions to cause the rings to spread, some particles gaining energy and moving to higher orbits, others losing energy and spiraling inward toward Saturn. The rings should gradually diffuse, losing their sharp edges, becoming a broad, faint disk. But they don't. Saturn's rings maintain sharp boundaries. Some ring divisions, gaps between rings, have crisp edges. Individual ringlets within the rings are narrow and well-defined. Something prevents the rings from spreading, keeps them confined, maintains their structure. We know part of the answer: shepherd moons, orbital resonances, and self-gravity. Small moons like Prometheus and Pandora confine the F ring. Resonances with larger moons like Mimas create gaps like the Cassini division. Ring particles' mutual gravity can cause them to clump temporarily, creating transient structures. But these mechanisms don't explain everything. The details of how particles interact, how they collide, stick together, bounce apart, depend on their sizes, compositions, and the dynamics of granular materials in microgravity. This is complicated physics, not fully understood even in laboratory conditions, let alone in Saturn's rings, where we can't directly sample or experiment. Computer simulations have helped. Researchers model millions of ring particles, simulate their orbits and collisions, and watch how structure emerges. These simulations reproduce many observed features: spiral density waves, sharp edges, narrow ringlets, but they require fine-tuning parameters, making assumptions about particle properties that we can't verify directly. Cassini provided unprecedented data, imaging the rings at high resolution, measuring their composition and structure, observing how they change over time. But even after 13 years orbiting Saturn, even after flying through the gap between Saturn and the rings during its final orbits, Cassini left questions unanswered. One mystery is the rings' longevity. If the rings are ancient, billions of years old, They should have accumulated more dust and darkened over time. But they're bright, relatively clean, suggesting they're young, perhaps only 100 million years old, as we discussed earlier. Yet if they're young, where did they come from? A shattered moon? A captured comet? The mechanism isn't clear. Another mystery is the fine structure within the rings. Images show intricate patterns, waves, wakes, propellers, small gaps created by embedded moonlets, braids, and clumps. Some of these features change on timescales of hours or days, driven by processes we're still working to understand. Saturn's rings are a natural laboratory for studying disk physics, how particles in a flat, rotating disk interact and organize themselves. This has implications beyond Saturn: protoplanetary disks around young stars, accretion disks around black holes, even spiral galaxy disks. All involve similar physics, though at vastly different scales. Understanding Saturn's rings helps us understand these other systems, but the rings remain partly mysterious, their behavior not fully explained, their structure maintained by mechanisms we've only partially identified. They're a beautiful puzzle, spinning around Saturn, constantly changing yet somehow stable, a reminder that even familiar, well-observed systems can hold secrets. Mars had water, this is certain. River valleys, lake deposits, deltas, minerals formed in water. The evidence is overwhelming. Mars also had a thicker atmosphere, warmer temperatures, and a magnetic field, at least early in its history. For hundreds of millions of years, possibly longer, Mars had conditions where liquid water could exist on the surface, where chemistry could happen, where life, if it emerged, could survive. But did life actually arise? We don't know. We've searched for decades, sending landers and rovers analyzing rocks, drilling into ancient lake beds, looking for biosignatures, organic molecules, isotopic ratios, structures that would indicate biological activity. We've found organic molecules, complex carbon compounds, but nothing that definitively points to life. The challenge is that biosignatures are ambiguous. Organic molecules can form through non-biological processes. Certain isotopic ratios favor biological activity, but aren't proof. Structures that look biological can be created by geology or chemistry. To prove life existed, we need multiple lines of evidence, patterns of data that are hard to explain without biology. The Viking landers in the 1970s carried experiments designed to detect microbial life. Some results were puzzling, reactions that could indicate metabolism, but also could be explained by Martian chemistry. The scientific consensus is that Viking didn't find life, but the results were ambiguous enough that debate continues. More recent missions have focused on understanding Mars's past, habitability rather than directly searching for life. Curiosity rover has analyzed ancient lake beds in Gale Crater, finding evidence that the lake existed for millions of years, with conditions, neutral pH, low salinity, chemical energy sources, suitable for life. But suitable doesn't mean inhabited. Perseverance rover, currently exploring Jezero Crater, is collecting samples for eventual return to Earth. These samples, analyzed in sophisticated laboratories, might finally answer the question: if ancient Martian life existed, traces might be preserved in those rocks, fossils, biomarkers, chemical signatures that unambiguously indicate biology. There's also the possibility that life arose on Mars, survived for a time, and then went extinct when Mars lost its atmosphere and water. Or perhaps life retreated underground, into aquifers and subsurface ice deposits, where liquid water might still exist in protected environments. Martian life, if it exists, might be deep beneath the surface, unreachable by current rovers. Some scientists have even proposed that life on Earth originated on Mars. Early Mars might have been more habitable than early Earth, and meteorites blasted off Mars by impacts could have carried microbes to Earth, seeding our planet with Martian life. This idea, called panspermia, is speculative but scientifically plausible. The question of Martian life is one of the most profound in science. If Mars ever hosted life, it would mean life arose twice in one solar system, suggesting life is common in the universe. If Mars, despite having favorable conditions, never developed life, it would suggest life's emergence is rare, requiring factors beyond just water and chemistry. We're close to answering this question, closer than we've ever been. Samples are being collected. Missions are planned to drill deeper, to explore subsurface environments. Within the next few decades, we might know. Until then, Mars remains a tantalizing mystery, a world that could have hosted life, that might still host life, but that hasn't yet revealed whether it ever did. Earth has experienced ice ages, periods when ice sheets extended far from the poles, covering much of North America and Europe. The most recent ice age ended about 11,700 years ago. Before that, ice ages occurred repeatedly over the past few million years, cycling every 40,000 to 100,000 years. You might think ice ages are caused by changes in the sun's brightness. If the sun dims slightly, Earth cools, ice expands. If it brightens, Earth warms, ice retreats. Simple, right? But the sun's luminosity variations are far too small to explain ice ages. The sun's output varies by only about 0.1% over the 11-year solar cycle, and there's no evidence for larger, longer-term variations that would cause ice ages. Instead, ice ages are driven primarily by Milankovitch cycles, variations in Earth's orbit and tilt that change how sunlight is distributed across the planet. These cycles don't change the total amount of sunlight Earth receives, just when and where it falls. Three main cycles contribute. Eccentricity. Earth's orbit becomes more or less elliptical over about 100,000 years. When the orbit is more elliptical, seasons are more extreme. Summers hotter, winters colder, because Earth's distance from the sun varies more over the year. Obliquity. Earth's axial tilt varies between about 22.1 and 24.5 degrees over 41,000 years. Greater tilt means more extreme seasons. Less tilt means milder seasons. Precession. Earth's axis wobbles like a spinning top over about 26,000 years, changing which hemisphere has summer when Earth is closest to the sun. These cycles combine in complex ways, creating periods when high-latitude regions receive more or less summer sunlight. When summer sunlight decreases, snow and ice from winter don't fully melt, accumulating year after year, building ice sheets. When summer sunlight increases, ice melts faster than it accumulates, and ice sheets retreat. But even Milankovitch cycles don't fully explain ice ages. The orbital changes are gradual and relatively small. Something amplifies them, turning small changes in sunlight distribution into large climate shifts. That something is feedback loops, processes that enhance the initial change. Ice albedo feedback is one. Ice reflects sunlight, so when ice expands, Earth reflects more sunlight, cooling further, causing more ice to form. Greenhouse gas feedback is another. Colder temperatures reduce atmospheric CO2, through absorption by colder oceans and other processes, which reduces the greenhouse effect, cooling the planet further. These feedbacks amplify the Milankovitch cycles, creating the large temperature swings we observe in ice core records. But the details, how feedbacks interact, what triggers the transitions between glacial and interglacial periods, why the cycle length changed from 41,000 years to 100,000 years about 1,000,000 years ago, are still being worked out. The sun plays a role, but indirectly. Small variations in solar output, combined with orbital changes and feedback loops, contribute to the complex dance of Earth's climate. It's not a simple, single cause. It's a system, with multiple components interacting, amplifying small changes into large effects. Understanding ice ages helps us understand climate generally, how sensitive Earth's climate is to small changes, how feedbacks can amplify forcing, how the planet's systems are interconnected. This understanding is crucial now, as human activities alter atmospheric composition and temperatures rise faster than at any time in Earth's recent geological history. The lessons from ice ages, about feedbacks, about tipping points, about how quickly climate can shift, are lessons we need to remember. When you hold a meteorite, you're holding something ancient. Most meteorites are 4.567 billion years old, formed in the earliest days of the solar system. They're older than Earth, older than the Moon, older than any rock you'll find on our planet's surface. But some meteorites contain materials even older. Embedded within them, scattered among the minerals and metals, are tiny grains, microscopic dust particles, that predate the solar system itself. These are presolar grains, formed in the atmospheres or ejecta of stars that lived and died before the sun existed. These grains are identified by their isotopic compositions. Isotopes are versions of elements with different numbers of neutrons. Different stellar environments produce different isotopic ratios. Presolar grains have isotopic ratios that are wildly different from solar system materials. Signatures that match what we'd expect from red giant stars, supernovae, or other stellar environments. When those ancient stars died, some exploding as supernovae, others gently shedding their outer layers as planetary nebulae, they released these dust grains into interstellar space. The grains drifted through the galaxy, carried by stellar winds and supernova shock waves, until they encountered the molecular cloud that would collapse to form our solar system. They were incorporated into the protoplanetary disk, survived the heat and violence of planet formation, and ended up in asteroids, which occasionally break apart and send fragments to Earth as meteorites. Some of these grains are older than the solar system by hundreds of millions of years, possibly billions. They're literally stardust, materials forged in other stars, survivors of cosmic violence, now resting in laboratories where scientists study them with electron microscopes and mass spectrometers. Each grain tells a story. Silicon carbide grains, common presolar grains, likely formed in the outflows of carbon-rich red giant stars. Tiny diamonds, found in some meteorites, might have formed in supernova shockwaves. Oxide grains could come from oxygen-rich stars. By analyzing these grains, scientists learn about stellar nucleosynthesis, how stars create elements, how different types of stars produce different mixtures of isotopes. There's something poetic about presolar grains. They're immigrants to our solar system, carrying memories of stars that died before the sun was born. They've traveled across the galaxy, survived for billions of years, and ended up here, on Earth, in our hands, connecting us directly to the cosmic cycle of stellar birth and death that preceded our existence. Carl Sagan famously said, "We are made of star stuff. Pre-solar grains are the proof." They're not metaphorically star stuff. They're literally, physically, tangibly star stuff, formed in other stars, now part of our world, part of the materials that built the solar system, part of the heritage we carry from the galaxy's deep past. Where did Earth's water come from? It's a simple question with a surprisingly complex answer. Earth formed inside the frost line, where temperatures were too high for water ice to condense. So the materials that built Earth should have been dry. Yet we have oceans, vast quantities of water covering more than 70% of the surface. How? The answer involves delivery from outer solar system objects, asteroids and comets, that formed beyond the frost line where water ice was stable. These objects, perturbed by gravitational interactions, migrated inward and bombarded Earth, delivering water over millions of years. But which objects delivered how much? Comets seem like obvious candidates. They're icy, and we see them releasing water when they approach the sun. But isotopic measurements show a problem. Most comets have deuterium to hydrogen ratios, DH ratios, that are too high compared to Earth's oceans. Deuterium is heavy hydrogen, an isotope with 1 proton and 1 neutron. The DH ratio is a fingerprint, telling us about the conditions where water formed. Earth's oceans have a specific DH ratio, and most comets don't match. Asteroids, particularly carbonaceous chondrites, are a better match. Meteorites from these asteroids contain water locked in mineral structures, and their DH ratios closely match Earth's oceans. So current thinking favors asteroids as the primary source of Earth's water, with comets contributing perhaps 10 to 20%. But there are complications. Some Earth water might have been delivered during the planet's formation, incorporated into the rocky materials that built Earth, released later through volcanism and degassing. Some water might have come from the solar nebula itself, hydrogen from the nebula reacting with oxygen in minerals to form water. And Earth's water isn't uniform. Different reservoirs, oceans, mantle, atmosphere, have slightly different isotopic signatures, suggesting multiple sources or fractionation processes that separated isotopes. Water in the mantle, for example, might have a different origin than surface water, possibly trapped during Earth's formation or delivered by different types of impactors. Recent studies of lunar samples suggest the moon also has water, preserved in minerals, with isotopic signatures similar to Earth's. This supports the giant impact hypothesis. If the moon formed from Earth's mantle material, it should have inherited Earth's water signature. But it also raises questions about how water survived the giant impact, which should have vaporized volatile elements. The origin of Earth's water is still being unraveled. It's not a single source, but a mixture. Contributions from asteroids, comets, the solar nebula, and volcanic outgassing combined over Earth's early history. Each drop of water you drink has a complex heritage, a journey through the solar system, a story that touches asteroids, comets, volcanic eruptions, and the formation of planets. Water made Earth habitable. Without it, Earth would be a lifeless rock, perhaps like Mars. Understanding where water came from, how it was delivered, how it survived Earth's violent formation, these questions are central to understanding habitability, not just on Earth but on exoplanets around other stars. If we can understand Earth's water, we can better predict which planets will have oceans, which will be dry, and where life might arise. Ganymede is the solar system's largest moon, and like Europa and several others, it likely has a subsurface ocean. But Ganymede's ocean might be more complex, more layered than others we've discussed. Magnetic field measurements and models suggest Ganymede's interior is structured in multiple layers. At the center is a metallic iron core, responsible for Ganymede's magnetic field. Surrounding that is a rocky mantle. Above the mantle is a layer of liquid water, the ocean. And above the ocean is an ice shell, possibly 150 kilometers thick. But here's where it gets interesting. The pressure at the bottom of a deep water layer can be high enough to form exotic high-pressure ices, phases of ice that don't exist at Earth's surface. At high pressure, water molecules arrange themselves into denser crystal structures, creating ice phases with names like Ice 3, Ice V, and Ice Vias. These high-pressure ices are denser than liquid water, so they sink. This means Ganymede's ocean might be sandwiched between layers of ice. A low-pressure ice shell above, ordinary ice Ike, the ice we're familiar with, and high-pressure ice layers below. There might even be multiple ocean layers, separated by ice layers, creating a stratified structure like a cosmic layer cake. This layering has implications for Ganymede's habitability. If the liquid ocean is isolated between ice layers, it's harder for material to circulate between the ocean and the rocky core below, which could limit chemical exchange and energy sources for life. On the other hand, the boundaries between ice phases might create interesting environments. Regions where different phases coexist, where chemistry happens in unusual ways. Ganymede's complex interior is part of a broader pattern. Many icy moons and dwarf planets in the outer solar system likely have layered internal structures with multiple ice phases. Understanding these structures helps us predict how oceans behave, how long they last, how they interact with rocky cores, and ultimately, whether they could support life. The existence of high-pressure ices also challenges our terrestrial intuitions. On Earth, ice floats. Frozen water rises to the surface of liquid water. But in Ganymede's deep ocean, ice sinks, creating inverted stratification, where the ocean sits below ice layers. It's alien oceanography, governed by physics we can explore in laboratories, but don't experience in nature on Earth. Ganymede's ocean is hidden, buried beneath kilometers of ice, possibly sandwiched between ice layers, inaccessible to direct exploration with any current technology. But magnetic measurements, gravitational studies, and models allow us to infer its existence and structure. We're mapping an ocean we can't see, on a world we've barely visited, using physics and mathematics to peer beneath the ice and understand the complex, layered interior of the solar system's largest moon. We've mentioned isotopic ratios before, particularly deuterium to hydrogen ratios, DH ratios, which serve as fingerprints for water's origin. Earth's oceans have a specific DH ratio, and scientists compare this to potential sources, comets, asteroids, the solar nebula, to identify where Earth's water came from. The problem is that Earth's DH ratio doesn't perfectly match any single source. Most comets have DH ratios about twice as high as Earth's oceans, suggesting comets can't be the sole source. Some carbonaceous chondrite asteroids have DH ratios very close to Earth's, making them strong candidates. But very close isn't identical, and variations exist even among meteorites from the same asteroid type. This mismatch suggests Earth's water is a mixture. Perhaps 80% came from asteroids with DH ratios slightly lower than Earth's, and 20% from comets with higher ratios, blending to produce the observed value. Or perhaps there were multiple populations of asteroids, each with slightly different DH ratios, contributing water over Earth's history. There's also the possibility of fractionation, processes that change isotopic ratios after water arrived. Water can undergo isotopic fractionation during evaporation, condensation, or chemical reactions. Lighter isotopes, hydrogen, evaporate more easily than heavier ones, deuterium. So processes that involve water vapor can shift the DH ratio. Early Earth was hot, with a magma ocean and a thick steam atmosphere. As the planet cooled, water vapor condensed into oceans. This process might have fractionated isotopes, altering the DH ratio from whatever the original delivered water had. Disentangling these effects from the initial composition is challenging. Another complication is that Earth's water isn't uniform. Different reservoirs, oceans, mantle, atmosphere, have slightly different DH ratios. The mantle's water is enriched in deuterium compared to the oceans, suggesting it has a different origin or underwent different fractionation processes. Atmospheric water vapor has even higher DH ratios because hydrogen escapes to space more easily than deuterium, leaving the atmosphere enriched in the heavier isotope. The isotopic puzzle of Earth's water is a reminder that simple questions don't always have simple answers. Where did Earth's water come from? The answer is multiple sources, mixed in proportions we're still determining, possibly fractionated by processes we're still identifying, resulting in a complex distribution of isotopes across different reservoirs. It's not a mystery we've solved. It's a mystery we're slowly unraveling, piece by piece, measurement by measurement, as we analyze meteorites, model Earth's early history, and compare our findings with observations of water in comets, asteroids, and the interstellar medium. Understanding Earth's water isn't just academic curiosity. It informs our search for habitable exoplanets. If water delivery is common, if most rocky planets receive water from outer system objects, then oceans might be widespread and habitability might be common. If Earth's water delivery was unusual, requiring specific circumstances, then ocean worlds might be rare. The isotopic puzzle of Earth's water connects to the broader question of life's prevalence in the universe. Jupiter has 95 known moons, but most of them are not like the Galilean moons. Most are small, irregular, and orbit in strange, distant paths around Jupiter. These are the irregular moons, and they tell a story of capture rather than formation. The irregular moons orbit far from Jupiter, typically between 10 and 30 million kilometers, and their orbits are highly inclined, elliptical, and in some cases retrograde, meaning they orbit opposite to Jupiter's rotation. These properties indicate they didn't form from the disk of material that surrounded Jupiter during its formation. They were captured, gravitationally snared by Jupiter at some point in the past. Capture isn't easy. An object passing Jupiter will normally just swing around and leave again, following a hyperbolic trajectory. To be captured, the object needs to lose energy somehow. This could happen through a collision with a moon or with another passing object, or through drag from gas in Jupiter's early atmosphere. or through a three-body interaction where one object is captured while another is ejected. Once captured, these moons remain in distant, eccentric, inclined orbits. They never settled into the circular, equatorial orbits that characterize moons that formed in situ. They're permanent prisoners, but they retain the orbital characteristics of their capture. Many irregular moons are grouped into families, clusters of moons with similar orbits, suggesting they originated from a single parent body that was captured and then shattered by a later collision. The Himalaya group, for example, consists of several moons with similar orbits, probably fragments from a single captured asteroid. The retrograde irregular moons are particularly interesting. They orbit Jupiter in the direction opposite to Jupiter's rotation and opposite to the Galilean moons. This makes collisions with other moons potentially catastrophic. Relative velocities are much higher when objects are moving in opposite directions. These retrograde moons are survivors, objects that were captured, survived billions of years of orbital evolution, and remain in stable, or at least long-lived, orbits despite the gravitational perturbations from Jupiter, the Sun, and the Galilean moons. Jupiter's irregular moons are diverse in composition. Some are rocky, some appear carbonaceous, some might even be cometary. They're samples of objects from different regions of the early solar system, captured by Jupiter and preserved, giving us a collection of different materials delivered to one location. Studying Jupiter's irregular moons helps us understand capture dynamics, the early solar system's chaotic environment, and the diversity of small bodies. Each captured moon is a time capsule, an object that formed elsewhere and ended up at Jupiter, carrying information about the region where it originated. They're immigrants, strangers in Jupiter's moon system, orbiting in strange paths, remnants of an era when the solar system was young and objects were still finding their places. It's easy to think of the solar system as fixed, as the center of our reference frame. The planets orbit the sun sits at the center, and everything revolves around it. But the sun isn't stationary. It's moving, orbiting the center of the Milky Way galaxy at tremendous speed. The sun, along with the entire solar system, travels at about 828,000 kilometers per hour, or roughly 230 kilometers per second, relative to the galactic center. At this speed, the sun completes one orbit around the galaxy in about 230 million years. This period is sometimes called a cosmic year or a galactic year. To put this time scale in perspective, the last time the solar system was at its current position in the galaxy, dinosaurs didn't exist yet. The Triassic period was just beginning. The supercontinent Pangaea was intact, and the first dinosaurs were still millions of years in the future. One galactic year ago, Earth's continents, climate, and biology were completely different. The solar system has completed about 20 galactic orbits since it formed 4.6 billion years ago. That means the sun has circled the galaxy 20 times, passing through different regions, experiencing different densities of interstellar material, encountering different numbers of nearby stars, possibly even passing through spiral arms where star formation is active and supernova rates are higher. These galactic orbits might influence Earth's history. Some researchers have suggested that passing through spiral arms could trigger increased comet impacts or elevated cosmic ray exposure, potentially affecting Earth's climate or biology. The evidence for such effects is debated, but the idea illustrates how the solar system's motion through the galaxy connects to events on Earth. The solar system doesn't just orbit the galactic center. It also oscillates up and down relative to the galactic plane, bobbing above and below the Milky Way's disk with a period of about 60 million years. Currently, we're near the plane, moving upward. This oscillation changes our exposure to different galactic environments, denser regions near the plane, sparser regions above and below. The galactic orbit also means the sun's neighborhood is constantly changing. Stars that are nearby now won't be nearby in a million years. The constellations we see are temporary configurations, patterns that exist only during this brief moment of the sun's 230 million year journey. In a few million years, the stellar neighborhood will look completely different. There's something humbling about realizing the solar system is in motion, that our entire frame of reference, sun, planets, everything we know, is hurtling through the galaxy at nearly 1 million kilometers per hour, orbiting a black hole at the galactic center that we can't even see directly, following a path that takes 230 million years to complete. We're not stationary, we're travelers, passengers on a small planet orbiting a star that's orbiting a galaxy, moving through the cosmos on timescales that dwarf human history. On Earth, atmospheric circulation is driven by heat from the equator being transported toward the poles. This creates Hadley cells, large-scale circulation patterns where air rises at the equator, flows poleward at high altitude, sinks at mid-latitudes, and returns toward the equator near the surface. Earth has multiple Hadley cells in each hemisphere, plus additional circulation cells at higher latitudes, creating a complex pattern of winds and weather. Venus, despite being similar in size to Earth, has a completely different atmospheric circulation pattern. Venus has one giant Hadley cell in each hemisphere, extending from the equator to the pole. Air rises at the equator, flows all the way to the poles at high altitude, sinks at the poles, and returns to the equator near the surface. This single-cell circulation is partly due to Venus's slow rotation. Earth rotates once every 24 hours, but Venus rotates once every 243 Earth days. Slow rotation weakens the Coriolis effect, the apparent force caused by rotation that deflects moving air. On Earth, strong Coriolis effects break up Hadley cells at mid-latitudes, creating multiple circulation cells. On Venus, weak Coriolis effects allow the Hadley cell to extend all the way to the poles. Venus's thick atmosphere also plays a role. The atmosphere's enormous mass and pressure allow it to store and transport heat efficiently, maintaining relatively uniform temperatures across the planet. Day-night temperature differences on Venus are minimal, and equator-to-pole temperature differences are surprisingly small, only about 10 degrees Celsius from equator to pole at the surface, compared to over 100 degrees on Earth. This global circulation pattern contributes to Venus's superrotation, the phenomenon where the atmosphere circles the planet much faster than the planet rotates. The Hadley cells, combined with momentum transport and wave interactions in the atmosphere, accelerate the upper atmosphere to speeds exceeding 360 kilometers per hour. The details of how superrotation is maintained are still being researched, but the single-cell circulation pattern is a key component. Venus's atmospheric circulation is a reminder that small differences, rotation rate, atmospheric thickness, can lead to vastly different climate systems. Earth and Venus started with similar conditions, but they diverged. Venus's slow rotation, runaway greenhouse, and thick atmosphere created a circulation pattern unlike any other planet we know. It's a different way of distributing heat, a different solution to the problem of atmospheric dynamics, an example of how planetary atmospheres can organize themselves in unexpected ways. For much of the 20th century, Mars was the focus of astrobiology in the solar system. Mars had water in its past, evidence of ancient rivers and lakes, conditions that might have supported life. The Viking missions in the 1970s specifically searched for microbial life on Mars's surface. But Mars's surface today is harsh, cold, dry, bathed in ultraviolet radiation, exposed to cosmic rays. If life exists on Mars, it's likely deep underground, in aquifers or ice deposits, protected from the hostile surface environment. Searching for subsurface life on Mars is challenging. We'd need to drill deep, access protected environments, and even then, finding life would be difficult. Meanwhile, our understanding of the outer solar system has evolved. We've discovered that several icy moons, Europa, Enceladus, Ganymede, Titan, have subsurface oceans. These oceans are vast, deep, protected by ice shells from radiation and impacts, and in some cases, in contact with rocky seafloors where hydrothermal vents might exist. Europa and Enceladus, in particular, have emerged as prime targets. Europa's ocean likely contains twice as much water as Earth's oceans, and tidal heating keeps it liquid. Enceladus's plumes give us direct access to ocean water without needing to drill through ice. Both moons have the ingredients for life: liquid water, organic molecules, energy sources, chemical gradients. The focus of astrobiology has shifted accordingly. Mars remains important, but the moons of the outer solar system have become equally, if not more, promising. Future missions are being planned to Europa and Enceladus, orbiters that will map their surfaces, measure ice shell thickness, search for plumes, and analyze chemistry. There's even discussion of sending landers, submarines, or ice-penetrating probes to directly sample subsurface oceans. This shift reflects a broader understanding. Habitability isn't just about being in the traditional habitable zone around a star. Tidal heating can keep subsurface oceans liquid even far from the sun, in regions where surface conditions are frozen and inhospitable. Life doesn't need sunlight if it can use chemical energy. It doesn't need a planet's surface if it can thrive in oceans beneath ice. The ocean worlds of the outer solar system represent a new frontier in the search for life. They're among the most promising places in the solar system, maybe in the galaxy, to find extraterrestrial organisms. And they're within reach. Challenging to explore, yes, but not impossible. Within the next few decades, we might know whether Europa's ocean harbors life, whether Enceladus's hydrothermal vents support microbial ecosystems, whether we're alone in the solar system or sharing it with distant relatives living in hidden oceans. When we search for life in the solar system, we're typically looking for microbial life. Simple, single-celled organisms, perhaps forming mats or colonies, but not complex, multicellular, and certainly not intelligent. The conditions in the solar system, except on Earth, don't seem favorable for complex life, let alone intelligence. But what if we're wrong? What if intelligence arose elsewhere in the past, and we simply haven't found evidence yet? This is speculative, bordering on science fiction, but it's worth considering. Mars, during its wet period billions of years ago, might have had conditions suitable for life to emerge and evolve. If Martian life had 1 billion years or more, the time it took for complex life to evolve on Earth, could it have produced something complex, perhaps even intelligent? It seems unlikely. Mars's habitable period was probably brief, perhaps only a few 100 million years, and then conditions deteriorated. Life, if it emerged, probably didn't have enough time to evolve beyond simple forms before Mars's environment became inhospitable. But suppose it did. Suppose intelligent life arose on Mars, built a civilization, and then went extinct when Mars lost its atmosphere and water. Would we find evidence? Possibly. Artifacts, structures, even ruins might survive for billions of years in Mars's dry, low-erosion environment. But we've explored only a tiny fraction of Mars's surface. If Martian ruins exist, they could be anywhere, buried under dust, eroded beyond recognition, or simply in regions we haven't visited. Venus, if it had oceans for billions of years, also might have developed life, perhaps even complex life. But Venus's runaway greenhouse would have destroyed any surface artifacts. If a Venusian civilization existed, evidence would be erased by heat, pressure, and volcanic resurfacing. The moons of Jupiter and Saturn, less likely. Their habitable environments are subsurface oceans, isolated from the surface, dark, cold. Life might exist there, but it would be adapted to deep ocean conditions, unlikely to develop technology or intelligence as we understand it. The scientific consensus is that intelligence probably hasn't arisen elsewhere in the solar system. Earth seems unique in having maintained stable, habitable surface conditions for billions of years, allowing complex life to evolve, diversify, and eventually produce technological intelligence. The other worlds, while fascinating and potentially harboring simple life, don't seem to have had the right combination of conditions and time. But the question remains open. We haven't explored enough to definitively rule out past intelligent life, especially on Mars or Venus. It's unlikely, but not impossible. And the fact that we're asking the question at all, whether intelligence arose elsewhere in our solar system, shows how far we've come in understanding our cosmic neighborhood and how much we still have to learn. The Sun has about 5 billion years left before it exhausts its hydrogen fuel and begins dying. When that happens, it will expand into a red giant, swelling to perhaps 100 times its current size, possibly engulfing Mercury, Venus, and Earth. The outer planets will be pushed farther out by the Sun's mass loss. The solar system's structure will be completely transformed. But long before this final transformation, the Sun's gradual brightening will change the planets. We've mentioned that Earth will become uninhabitable in about 1 billion years as increasing solar luminosity triggers a runaway greenhouse effect. Venus is already in that state. Mercury will continue to bake, its surface possibly melting as the Sun brightens. Mars might become more habitable temporarily. As the Sun brightens, Mars's frozen CO2 caps might sublimate, thickening the atmosphere, creating greenhouse warming. Subsurface ice might melt, bringing liquid water back to the surface for a brief period, perhaps a few 100 million years, before the Sun's continued brightening evaporates that water too. The outer solar system will warm. Jupiter's and Saturn's moons, currently frozen, will receive more heat. Europa's ice shell might thin, making the subsurface ocean more accessible. Titan's methane lakes might evaporate, altering its atmosphere. The habitable zone will move outward, encompassing regions that are currently too cold for liquid water. This is the solar system's slow transformation, driven by the sun's aging, occurring over billions of years. It's not a sudden disaster, but a gradual change, giving life, if it exists elsewhere, if it survives on Earth, time to adapt, migrate, or escape. Eventually, the sun will enter its red giant phase. The inner planets will be destroyed or sterilized. The outer planets will lose their atmospheres to the intense stellar wind. Jupiter and Saturn might survive as cores, their gas stripped away. Their moons, if they survive, will be scorched, lifeless. After the red giant phase, the sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. At the center will remain a white dwarf, Earth-sized but incredibly dense, gradually cooling over trillions of years. The solar system, as we know it, will be gone. What remains will be a vastly different configuration, a cooling white dwarf surrounded by whatever remnants of planets survive, a quiet, dark system slowly fading into the black. But that's billions of years away. For now, the solar system is vibrant, active, filled with planets and moons and complexity. The sun shines steadily, the planets orbit, life thrives on Earth, and the future, though ultimately finite, is measured in timescales so long they're almost unimaginable. The solar system's eventual end is a reminder that nothing lasts forever, that all systems evolve and change, that even the sun, which has been the constant center of our existence, will one day transform and die. But it's also a reminder to appreciate what we have now, this moment, this era, when the sun is in its prime, when Earth is habitable, when we're here to witness the beauty and complexity of the solar system we call home. This is where we return to the beginning, to the origin of everything. The solar system is 4.6 billion years old, born from a collapsing cloud of gas and dust. But that cloud wasn't primordial. It wasn't made of hydrogen and helium from the Big Bang alone. It contained heavier elements: carbon, nitrogen, oxygen, silicon, iron, elements that could only have been created inside stars. Stars are element factories. In their cores, nuclear fusion combines light elements into heavier ones. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Larger stars continue the process, creating neon, magnesium, silicon, and eventually iron. But fusion can only produce elements up to iron. Anything heavier, copper, gold, uranium, requires even more extreme conditions. Those conditions exist in supernovae, the explosive deaths of massive stars. When a star exhausts its fuel and collapses, the core rebounds, creating a shock wave that tears the star apart. In those brief moments, in the intense heat and pressure of the explosion, elements heavier than iron are forged. Neutrons slam into atomic nuclei, building heavier and heavier elements, creating the entire periodic table. The explosion scatters these elements into space. The debris expands, mixing with interstellar gas, enriching it with the products of stellar nucleosynthesis. Over time, this enriched gas collects into new molecular clouds, which eventually collapse to form new stars and planetary systems. Our solar system formed from one such cloud, a cloud enriched by the deaths of previous generations of stars. The iron in Earth's core, the oxygen you breathe, the calcium in your bones, the carbon in your cells. All of it was created in stars that died before the sun was born. You are made of stardust, quite literally. atoms that were forged in stellar cores, and supernova explosions billions of years ago. This connection to the cosmos is profound. We're not separate from the universe, not external observers studying it from outside. We're part of it, made of it, products of the same processes that create stars and galaxies. The atoms in your hand were once inside a star, undergoing fusion, glowing with nuclear fire. They were scattered in a supernova, drifted through space, collected in the solar nebula, formed into planets, and eventually became part of you. The solar system isn't just a collection of worlds orbiting the sun. It's a story, a narrative that begins with the Big Bang, continues through stellar birth and death, and culminates in the formation of planets, moons, and, on at least one world, life. You're part of that story. Every breath you take, every thought you think, connects you to supernovae, to stars, to the deep history of the cosmos. This is the final fact, but also the most encompassing. We are made of star stuff. The solar system is made of star stuff. Everything we know, everything we've discussed, the planets, the moons, the rings, the asteroids, the comets, all of it traces back to stars that lived and died, that created the elements, that made everything possible. We're stardust contemplating stardust, atoms arranged into patterns complex enough to look up at the night sky and wonder where we came from, where we're going, and what it all means. And maybe in that wondering, in that contemplation, we find a kind of meaning. We're temporary, yes, our lives, our civilization, even our solar system will eventually end. But we're also connected to something vast, something ancient, something that extends back to the birth of the universe and forward into an unimaginable future. We're part of the cosmos, and the cosmos is part of us. And with that thought, perhaps you can rest. We've traveled together through 100 facts about our solar system. We've visited planets near and far, moons with hidden oceans, asteroids that remember the beginning, comets that drift in from the darkness. We've touched on mysteries, why Venus spins backward, what creates Saturn's hexagon, whether life arose on Mars, and we've marveled at the beauty and complexity of the cosmic neighborhood we call home. The solar system is vast, but it's also intimate. Every world has a story. Every object carries history. Every orbit traces a path shaped by gravity, time, and chance. We're learning to read these stories, to understand the forces that built the planets, the processes that sustain them, the changes that will eventually transform them. And perhaps, as you drift toward sleep, you'll dream of distant worlds, of Europa's hidden ocean, where tides flex the ice and water flows in darkness, of Titan's methane rain pattering softly on alien shores, of Enceladus's geysers shooting ice into space, carrying the ocean's secrets upward, of Mars's ancient rivers, now dry, their valleys remembering water that flowed billions of years ago. These worlds exist. They're out there, orbiting the sun, spinning through space, waiting for us to return, to explore, to understand. And every night, when you look up at the sky, you're seeing them. Venus shining bright in the evening, Mars glowing red, Jupiter hanging like a bright star, Saturn with its rings invisible to the eye, but there nonetheless. You are part of the solar system. The atoms in your body came from the same cloud that formed the sun and planets. You share your origin with Jupiter, with Europa, with every grain of dust in Saturn's rings. In a very real sense, the solar system isn't just where you live. It's what you're made of. And so, as you close your eyes, know that you're resting on a planet spinning through space, orbiting a star that's orbiting a galaxy, moving through the cosmos at hundreds of kilometers per second, held gently by gravity's invisible hand. You're safe here, on this small world, protected by atmosphere and magnetic field, warmed by a sun that has shone steadily for billions of years and will shine for billions more. Sleep well, traveler. The solar system will still be here when you wake. The planets will continue their orbits. The moons will spin, the sun will rise. And you'll have another day to live, to wonder, to learn, to appreciate the vast, beautiful, intricate cosmic neighborhood you call home. Good night.